হ্যালো।
হ্যাঁ, Dipankar da.
হ্যাঁ।
Hi.
হ্যাঁ,
We are just testing the YouTube live streaming.
হ্যাঁ,
So
ওকে।
we are just coming to you after a while. Yeah.
হুম, শিওর শিওর।
So welcome.
Hello.
Welcome.
Yeah.
We are just testing the YouTube live stream.
Okay.
We'll get you back in application short while.
Yeah, that's fine. Thanks.
Yeah, Professor Kakre, you can share your screen.
Okay.
Yeah.
Let's see. Share screen. Yeah. Can
Yeah.
you?
Yes. Yes.
Okay.
So Professor Dipankar Ghosh will be the chair of this session.
Yeah.
Welcome, Professor Dipankar Ghosh.
Yes, hi. Hi.
Hi.
Hello.
So we'll be starting at 10.
Yeah. Thank you. You just see the slides, right? Even if I move back and forth between different screens.
Yeah, you can
Yes,
try.
yes.
Okay.
Yeah, you just shared that window, I guess, on the document.
Yeah.
We
I
can.
just wanted to make sure that it was working the way
Yeah,
I
yeah.
needed it to work.
Yeah, it's working.
No, we can only see the
Slides.
first
Yeah,
slide.
that's what I
No,
want.
I think he only meant that.
Okay. Yeah.
Shomo, can you make Professor Mahesh Kagde the co-host? Hilbert's 12 Brumer-Stark conjecture.
Yeah, I would request all the participants to mute yourselves.
So we can start exactly at 10 o'clock, right?
Yeah, sure.
Yeah.
Sure. Yeah, so welcome everyone. Today is the second day of our conference, Virtual Math Fest 2020. For today's session, we have Professor Dipankar Ghosh as the chair of the session. We welcome him. Dipankar, sir, please carry on.
Yeah. So a very good morning, everyone. Welcome to Virtual Math Fest. Myself, Dipankar Ghosh from IIT Hyderabad. So I am honored to get this opportunity to chair this session. And this morning session, it lasts for around 3 hours, consisting of one invited talk and 5 contributory research talks. So I would like to request everyone to mute their microphone. So while the talk goes on, and though they can ask questions in the chat box, so which will be addressed after the talk. So it's a great pleasure to introduce our invited speaker, Professor Mahesh Kapri from IISc Bangalore, and he will start this session by his talk on Hilbert's 12th problem and Stark conjectures. So Professor Kapri, you may please start your talk now.
Okay, thank you. Can everyone hear me?
Yes, I think.
Yes, you are.
So, yeah. All right. Thank you. Thank you for the opportunity to speak here in these unusual times. So I hope we all get through these bleak times. All right. And have a real math conference with in person soon. Okay, so I'll talk about my recent work on Hilbert's 12th problem and Stark conjectures. Okay, so let me begin by a very classical result about abelian extensions of Q. So firstly, we all learn in first course on Galois theory that if n is a natural number and zeta, if I denote zeta n by the for the nth root of 1, then the Galois group of the extension Q zeta n over Q is Z mod nz cross. Okay. So this is one of the Galois groups we compute in the Galois theory course. So this is easy, but on the other hand, there's a remarkable result that of Kronecker-Weber from 19th century, which says that if you take any abelian extension of Q, then it is in fact contained in one of the cyclotomic extensions. Okay, so there is a positive integer n such that K is contained in Q zeta n. Another way of saying this is that the maximal abelian extension of Q ab, is union of all the cyclotomic extensions. Okay, so this is a 19th century theorem. Kronecker first stated it in 1850s, and Weber gave a proof in 1880s, which had a flaw, which was discovered nearly 100 years later. And the first correct proof, as far as we know, is due to Hilbert from 1890s. Okay, this is called Kronecker-Weber theorem. Okay, but the upshot of this is that all abelian extensions of Q are generated by values of analytic functions at rational numbers. So the function is e to the power 2 pi I x. Okay, so if you put x equal to a rational number, you get a root of unity, and you adjoin all those values, and you get abelian extension of Q. Okay. Okay, why does this? Okay. Another example of this sort is again a theorem that began in that's from 19th century. So if you take imaginary quadratic field Q square root of minus d, where d is a positive square free integer, then you can we know how to explicitly get the maximal abelian extension of f. Okay, so what you do is you take you take an elliptic curve with complex multiplication by the ring of integers of f. Such a thing always exists, not necessarily over Q, but over what is called the Hilbert class field of f. Okay, and you you take the J invariant, the J function, which is the modular form, the well-known modular form G2 cube divided by delta scaled appropriately, so by 1728. So you take this J function and evaluate it at E. So that's one thing you adjoin to F. And the other things you adjoin are values of what are called Weber function at torsion points of E. Okay, so so E is an elliptic curve. It has a group structure, and you take the torsion points of E and torsion points, and you evaluate the Weber function at these torsion points, and you get abelian extensions of F, and you get all abelian extensions like this. So again, this was this goes back to Eisenstein, Kronecker, and so on. A lot of people contributed, and I think it was finally completely settled by Takagi in the early 20th century, so 1920s. Okay. A remark that I would like to make here is that Q and imaginary quadratic fields are the only number fields which have finitely many global units. Okay, if you take any other number field, the group of global units, as we learn in Dirichlet's unit theorem, is infinite. So so somehow when you have infinitely many global units, that causes a lot of difficulty, it seems, in the questions that we are going to address in this talk. Okay, I don't know exactly why, but this is what happens. Okay. Okay, so Hilbert's 12th problem, what is it? So in his ICM talk in 1900 in Paris, Hilbert listed 23 problems, and the 12th of these problems was generalizing the Kronecker-Weber theorem and the theorem of complex multiplication for imaginary quadratic field to any number field. So he says, finally, the extension of Kronecker's theorem to the case that in place of the realm of rational numbers or of imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. Okay, so so that's what Hilbert wrote about this problem, and it's there are many attempts to do this. Okay, so one of the attempts is through Stark's conjectures. Okay, so there's a partial result in this direction from the second half of 20th century, 1950s, 1960s. So let me recall that. So F is called a totally real field if all its embeddings into C are actually contained in R. So for instance, a real quadratic field, which you get by adjoining square root of a positive square-free integer. Okay. So that's a totally real field, just what you would imagine it to be. And a CM field is a totally imaginary quadratic extension of a totally real field. So what you do is you take a totally odd, totally negative element of a totally real field. So you have all the embeddings of your field F into R. So and you take an element of F such that in each embedding it's a negative element. So that's a totally odd element, and you adjoin its square root. So that gives you a CM field. Okay, so these are all the CM fields. Okay, then Shimura Taniyama, using their theory of complex multiplication, they constructed abelian extensions of CM fields. So just like in the case of imaginary quadratic field, where you used elliptic curve, they used abelian varieties with complex multiplication. Okay, and then you adjoin what is called a moduli, so that kind of replaces J of E, and then you adjoin all the torsion points of these abelian varieties in some way, and you get abelian extensions of K. Okay, unfortunately, unlike the case of imaginary quadratic field, in general, you don't get all the abelian extensions of K. Okay. In fact, you can show precisely the extensions which you cannot get. This was proved by a student of Milne in 1970s, I think, that the extensions that Shimura and Taniyama miss out are precisely the extensions coming from the maximal totally real subfield of K. Okay, so and this is the topic of my talk today: how to get abelian extensions of totally real fields. Okay, so what I'm going to talk about complements this theory of complex multiplication. Okay. All right. So Stark's conjectures. Okay. So Stark made in a series of papers in 1970s, at least 4 in Advances of Mathematics. He made many conjectures where he proposed existence of certain special elements, which we now call Stark units, which are related to the leading term of L functions of f, okay, Artin L functions of f, at s equal to 0 or at s equal to 1. Okay. So at first, Stark's motivation was you take this Dirichlet's class number formula, which gives you the leading term of the Dedekind zeta function at s equal to 0, and it gives a formula for that in terms of the class number, a regulator, and the number of roots of unity in that field. Now, Dirichlet zeta function, using Artin formalism, it decomposes as product of other L functions, and he wanted to decompose the other side of the equation also into some factors so that the factors match up. But then, so he proposed existence of certain units in that factorization so that the factors match up. But it turned out that these Stark units actually generate abelian extensions of number fields. So that was quite amazing that you could generalize 2 very classical 19th century things. So you could generalize Kronecker-Weber, and you could generalize Dirichlet's class number formula using these conjectures that Stark made. Okay. So a canonical reference for reading about Stark's conjectures is a book of Tate by the name of Stark's conjecture. Okay, so he not only sort of gave a very nice exposition of these conjectures, he made them more precise. He related it to a conjecture of Brumer. That's the first place where sort of the relation appears explicitly, though I guess people knew about this all along. Okay. Okay. So along the same line, so Gross gave a p-adic refinement of these conjectures using p-adic L functions. So he used p-adic L functions to refine these conjectures. And then finally, sort of about 15 years ago, my collaborator Samit Dasgupta, he refined conjectures of Gross and proposed a precise p-adic analytic formula for these so-called Brumer-Stark units. Okay, so as we'll soon see, Stark conjectures, they postulate, I mean, they postulate existence of certain elements, but they don't tell you exactly how to construct one, even if you know their existence. Dasgupta's conjecture actually gives you a formula if you can prove the conjecture. Okay, so here's the setup. Okay, so again, F is a totally real field. H is a CM abelian extension of F, but need not be quadratic. Okay, H over F need not be quadratic. It could be a bigger extension, but it's abelian and finite. And I denote by G the Galois group of H over F. And S is the set of primes that ramify in H. Okay, precisely the set of primes that ramify in H. Okay, throughout my talk, I'll not have infinite places. Okay, so otherwise I should ideally put infinite places in the set S. Okay, so for any character of G, I can find it's finite order because it's for a finite group. For any character of G, I define the L function this way, as usual by Dirichlet series. It also has an Euler product like this. Okay, so a priori this makes sense for real part of S bigger than 1. But as we all know, this has a meromorphic continuation to the whole complex plane minus 1. And also at 1 if chi is not the identity character, which it won't be because I assume chi is odd. So it has a analytic continuation to C. Okay, and I modify it in a certain way. So this last line is perhaps not that familiar. So I multiplied by these finitely many factors, 1 minus chi of L, norm of L to the 1 minus S. Okay, so this makes everything integral. Otherwise, we have to deal with denominators and we can't make integral theory. So this thing has some significance, but it doesn't matter what non-empty finite set T we choose. It just has to be large enough and disjoint from S, and things work. Okay. All right. So oops, sorry. Okay. So Stickelberger element. Okay. I can put all these L functions evaluated at 0 together and make a group ring element. Okay, so CG is the group ring with complex coefficient and on the group ring G. Okay, so theta is the element that, so it's a group ring element. So I can evaluate it at any character chi of G, and I get this LST chi inverse comma 0 out of it. Okay. Okay, I just realized a typo, but I'll come to that a little later. Okay, so this is these E chi are the idempotents. Okay, the group ring idempotents. Okay. So a priori this has complex coefficients, but sort of celebrated theorem of Ziegel and Klingen and Shintani, so they proved this fact independently, the three of them, says that this theta in fact has coefficients in Q. Okay, so it belongs to the group ring over Q. For this theorem of Ziegel, Klingen, and Shintani, you don't need this set T. As you see, T is kind of almost a rational number, right? It's an algebraic number, and so you don't need it. You can divide by that thing. It's a non-zero algebraic number, and you can divide by it, and you still have this theorem. The T is needed for the next theorem, which is a refinement of the first theorem proven independently by Deligne-Ribet and Cassavetes. It says that this theta, St, so T is important here, is actually an element in Zg, not just in Qg, but it has coefficients in integers. Okay, all right. Okay, so that this is an important object for us. Okay, so this theta you should think of just as some kind of L function, but a group ring valued L function rather than L value actually, because I have already evaluated at S equal to 0. So you should think of it as an L group ring valued L value. Okay, so that's one side, right, in all for my results. The other side is some kind of arithmetic objects. Okay, so on one side I have some analytic object, and on the other side I have some arithmetic object. Okay, all right. So what's the arithmetic object? Well, the arithmetic object that I have for stating this conjecture of Brumer and Stark is the class group. Okay. So what kind of class group do I take? Well, I don't take the usual class group. I take something slightly bigger. So I take the T smoothened version of it, right? So I have this set T on the analytic side. So I should have it also on the arithmetic side. So what I do is I take the quotient of all the fractional ideals of H, which are co-prime to S union T, by principal fractional ideals. So if I just stop there, I would get the usual class group. But I only take principal fractional ideals which have a generator congruent to 1 mod every element of T, 1 mod every prime in T. Okay. So if you like, an alternate way of saying this is you take the Galois group of the maximal abelian extension of H, which is unramified outside T, and at T it's at most tamely ramified. Okay, so you allow some ramification. If you take the ideal class group, you have unramified, everywhere unramified extension. But in this T-smoothen thing, you allow tame ramification at primes in T. Okay, so it's slightly bigger. Okay. So what does the Brumer-Stark conjecture say? So this was Brumer never. So this is the version that Brumer is due to Brumer. He never wrote it down, as I learned while writing this paper, but he gave lectures on this. So one of his student Rideout, he wrote a version in his thesis in a special case, and he proved weak results towards it. That was his PhD thesis. So this version is due to Brumer. It says that the Stickelberger element annihilates the class group. Okay, so the Galois group of H over F acts on the class group, and so ZG acts on it, and you can talk about annihilators inside ZG, and the Stickelberger element annihilates it. Okay. Now, why is it called Stickelberger? Because there is a classical theorem of Stickelberger from 1890, which is precisely this result when F is equal to Q. Okay. So Brumer's conjecture was an attempt to generalize Stickelberger's theorem from Q to any totally real field. Okay. So what do we know about this Brumer-Stark conjecture? It was more or less completely open until recently. So there were some cases known due to, so Wiles had this ingenious horizontal Iwasawa theory argument, which leads to proof of this Brumer-Stark conjecture for so-called nice extensions, but that's quite restrictive. Okay, so the result, so the main theorem of today, but I'll not talk about its proof except very, very briefly at the end, is that Brumer-Stark conjecture holds up to 2 part. Okay, so this is a conjecture over Z. We cannot prove it over Z. We can prove it once you invert 2. Okay, so up to sort of 2 part of the class group, theta annihilates the class group. Okay. In fact, we prove a stronger version. So this fit is the fitting ideal, and fitting ideal is contained in annihilator ideal. So fitting ideal is a smaller ideal, which means that we prove something stronger about theta. So yeah, there is a typo. There should be H over F here, and there should be some decoration pound here. Yeah, so that's the typo I was referring to because of the way I defined theta. But this theta belongs to the fitting ideal. Now I don't take the class group itself. I have to take this V, which is the Pontryagin dual of the class group, and I have to take the minus part of it. But that's okay because theta is 0 on the plus part, so it doesn't matter. And because I have inverted 2, I can take the minus part. To take minus part means complex conjugation of H over F acts as -1. Okay. So if you don't, I mean, you can just think about the annihilation statement if you are not familiar with the fitting ideals, but the proof has to go through a stronger version somehow. We can't just prove the annihilation statement, as I'll say at the end. Okay. So that's the result. And in fact, one of the main obstructions in proving this at 2 is we don't know precisely what this stronger statement should be in terms of fitting ideals. So that's one of the obstructions why our proof doesn't yet work for p equal to 2. Okay, so at 2. All right, so that's the Brumer part of the Brumer-Stark conjecture. I should also tell you what the Stark part is. Okay, so an equivalent statement. Okay, so what these conjectures of Stark always depend on choosing a place of F that splits completely in H. Okay, the place could be a finite place. The place could be an Archimedean place, an infinite place. For me, in this talk, it's going to be a finite place. So I take a prime P of F that splits completely in H. Remember, H over F is a finite extension. F is totally real. H is CM. And I take a prime in the ground field that splits completely in H. I fix a prime in H above it. So these things will depend on this choice of the prime, but they are all equivalent if you choose a different one, quite trivially. Okay. Then Brumer-Stark conjecture is equivalent to existence of certain P unit. Okay. So these are, even though they are called units, they are not really global units. They are P units. So they're units away from P. So Brumer-Stark conjecture is equivalent to existence of a P unit U, which is congruent to 1 mod T. And it is related to the Stickelberger element theta in this particular way. Okay, so if I take odd of sigma U scale, and then sigma is the element of the Galois group. Okay, so this odd is the p-adic odd, right? The usual sort of p-adic odd. So this is an integer. And if I stick this integer in front of this element of the Galois group, I get an element in ZG. Okay, so this sum is an element in ZG. And the statement says that there exists a U such that when you make this construction, you get your theta. Okay, so it means that this equivalent statement gives you L value using odd of sigma U. Okay, so this, or another, or the other way of seeing this is that it gives you the formula for odd of sigma U in terms of L values, right? Because this theta was defined in terms of L values. Okay, so to go from one to other is slightly tricky because you have to use these partial zeta functions. Okay, but you can write partial zeta functions in terms of L functions and L functions in terms of partial zeta functions. So it's all the same. Okay, so how do we get this equivalence? Well, I'll not tell you how to go from this statement to the other one, but I'll tell you how to go from the other statement to this one. So you have the annihilation statement. Okay, so theta annihilates some class group. So what I do is I take this P, capital P, in the ideal of H, and I look at its class in the T-smoothed class group, the CLT. Okay. Now, if I let theta act on it, that annihilates it. Okay, so I get the trivial class, and trivial class is by definition, it means that I get a principal fractional ideal. Okay, so I get this U. Okay, which is congruent to 1 mod T and so on. So that's the U that I want. Okay, just by definition. Okay, so that's how you go from the annihilation statement to existence of this Brumer-Stark unit. So I'll call this the Brumer-Stark unit. Okay, so the theorem that I stated on the previous page, it says that this U exists up to taking 2 powers. Okay, I may have to take 2 powers to because I don't have the theorem at p equal to 2. All right. Okay, so there's a higher rank version of this where instead of just taking 1 prime, you take R distinct primes that split completely in H. And this leads to what is called the Rubin-Brumer-Stark element. Okay, that lives in, so it doesn't quite, it's not quite in H. It's what called the Rubin lattice. Okay, so in the end, I'll mention this once. So here's the remark. But if you like, you can just think about rank 1 case. Okay, so what's the application to Hilbert's 12th problem? Let me quickly say this. So what I do is I take an integral ideal F of my totally real field F, and I choose a prime P, which is co-prime to this integral ideal F. And I let H be the maximal abelian CM extension of F of conductor this math frac F, okay, in which P splits completely. So sometimes I call this Gross-Stark unit, but I meant here Brumer-Stark unit. Okay, So then there is this Brumer-Stark unit UF comma P, and one can show that that unit actually generates H. So H is F adjoint this unit. Okay. Now, if I vary my F and if I vary my P over all possible choices, I almost get F ab, not quite. There's issue of some signs. What I get is the maximal abelian CM extension of F. Okay. And now to pass from maximal abelian CM extension to the maximal abelian extension, I have to adjoin some square roots. So square roots of the signs. Right? Okay. So, so all these Brumer-Stark units, so remember, I'm just using the rank 1 case here. That's why I did not state the higher rank case precisely. So just using the rank 1 case, I get I get the maximal abelian extension of F. Okay. But remember, Brumer-Stark conjecture only gives me a formula for odd of these units. Okay. So our theorem only gives the formula for odd of these units. It doesn't tell me how to construct these units. So this is not quite what Hilbert asked for, because we want an explicit construction of these units. Now we know that they exist. We don't know how to construct one. So if I give you F, if I give you math frac F and P, then I can tell you that this UF comma P exists. But Brumer-Stark conjecture doesn't tell me how to construct this U. So it doesn't give me a formula for it. Okay, so in 1980s, Gross gave some refinements of this. So starting with Gross-Stark conjecture and what is called the Tower of Field conjecture. So it gives us more information about these units. It still doesn't tell me exactly how to construct it. And that exact formula for these Brumer-Stark units was conjectured by my collaborator Samit Dasgupta. Okay, so I'll come to that in a minute. Okay, so let me come to the p-adic refinement by Gross. Okay, so remember, F is my totally real number field. H is a finite abelian CM extension still, and chi is a totally odd character of G, which is the Galois group of H over F. Okay, so this theorem of Deligne-Ribet and Castelnuogas that I mentioned earlier, in fact, it gives me a p-adic analytic function, the p-adic L function as it's called, p-adic L function LP, from ZP to CP. Okay, so from p-adic integers to the completion of QP bar, such that it interpolates these L values. Okay, these are the classical, so the right hand side here is the complex L function as defined earlier. And my p-adic L function, when I evaluate it at S equal to a negative integer congruent to 1 mod p minus 1, I get this. Okay, usually it's sort of odd negative integers, but then you have some powers of this Teichmüller character omega coming in here, which I did not want to mention. So this omega on the left hand side you can just think of as notation. Okay, this determines it uniquely, so it doesn't matter if I tell you its values at more integers, it's still the same function. Okay, but for this I must say that S should contain all primes above P now. Okay, so now S means something slightly different than before. So S was precisely the set of primes of F which ramify in H, but now in addition they contain all primes above P in F. Okay, so Gross made two conjectures about this. One was about the order of so here this S, remember the definition of L function. So you remove all Euler factors at primes in S. And so in fact, you can show that whenever there is a prime above P that splits in H, so chi of P is 1, this L function is 0 at S equal to 0. Okay, so it's easy to show that whenever you have a prime like this, so whenever R is bigger than or equal to 1, LP chi omega 0 is 0. Anything finer is much harder to say. Okay, so so Gross conjectured that the order of vanishing of this L function, p-adic L function at 0 is precisely R. Okay, it's precisely the number of primes such that chi of p is 1. So this part 1 is completely open. We know that this order is greater than or equal to R, as I'll say on the next page. Okay, let me come to that a little later. He went further and he gave a precise formula for the leading term. So rth derivative in terms of what is called gross regulator that I'll define, and then there are some factors that you have to put in, some correction things. Okay, so not only did he conjecture about order of vanishing of this L function, he gave a precise formula for the leading term. Okay, so what do we know about this conjecture? So about order of vanishing, we know that it's at least R. So when R is 1, this is trivial. But when R is bigger than or equal to 2, this is quite non-trivial. So this follows from Weil's proof of the main conjecture, at least if P is bigger than 2. And then there's a completely analytic proof that's given by Dasgupta and Spies that works even for P equal to 2. Okay. So yesterday in Professor Balasubramanian's talk, we heard about this 6 exponential theorem and 4 exponential conjecture, and it seems that showing this precise equality is a transcendental problem of that nature. So I think if you can prove 4 exponential conjecture, the p-adic version of it, then you would get very close to proving this conjecture. Okay, so so you get a weaker result about this using the 4 exponential theorem, using the 6 exponential theorem, or rather Waldschmidt's refinement of it. Okay, so that's what we know about the order of vanishing. And then about 2 years ago, I proved with Dasgupta and Ventulo the formula, the leading term formula. Okay, so part 2 is completely known. I must remark here that part 2 is independent of part 1, because I'm not saying leading term, I'm saying rth derivative. So if one is false, and in fact the order of vanishing is bigger than R, then we show that the right hand side is also 0. So we show 0 equal to 0. So that's the content if 1 is false, and that's also non-trivial to prove. And if 1 is true, you get the formula for the leading term. Okay. All right. So what's the regulator, and what's the relation with more information about the Brumer-Stark unit? Okay, so definition, I don't know why the D became small. Sorry about that. So the definition of regulator is, I take this Rubin-Brumer-Stark element. You can think of this as wedge of R distinct units. They are actually not R distinct units. There are some small denominators, but you can, for the purpose of sort of getting the idea of how it's defined, you can just think of these as R distinct P units. And you take norm from FPI to QP. So this is a finite extension of QP. You take norm of UJ. So ith norm on jth element, and then you scale it appropriately by taking p-adic log. So this is an R by R matrix. I and J vary over from 1 to R. So this is an R by R matrix in general. And you take determinant of that. Okay, so that's the Gross regulator that appears in the statement of Gross's conjecture, okay, or our theorem. All right. So what happens when R is 1? This is simply a number. There's no I mean, it's not a matrix. It's just a 1 by 1 matrix. And so you get a formula for this log T of norm of the Brumer-Stark unit. Okay, right? Because this thing is just a number now. I mean, this is just a summation of chi sigma inverse log p of norm of sigma u. And this is the L value, and this is some other thing. Oh yeah, I should also say that when R is 1, this order of vanishing is known. So it's exactly 1. And that's again something that was mentioned yesterday. That's the work of Baker, or rather p-adic refinement of Baker's result due to Brumer. Okay, so when R is 1, we know the precise order of vanishing, and that's a deep theorem of Brumer and Baker. Okay. Oops. I don't know what's happening here. Okay. So when R is 1, this conjecture of Gross gives a formula in terms of p-adic L functions for log p of norm of sigma 1 u. Okay. Sigma u1, sorry. So R is 1, so I can call u1 u. Log p is kind of harmless, so it gives a formula for norm of norm from fp1 to qp of sigma u1. Okay. So you get more information than just odd, right? Odd just tells you something about about the p-adic odd. Now you know what the norm is in qp. Okay. But of course, this still loses a lot of information. One way to think about it is you're given a complex number and you're given just its absolute value. Okay, so it loses a lot of information. So what's beyond Gross-Stark? Okay, if I want to go further, if I actually want the unit, what else can I say? Okay, so this U actually, so it's in the p-adic completion of H. But because P splits completely, this p-adic completion of H is same as the p-adic completion of F. And again, I sometimes, I used to call it Gross-Stark unit, but recently I changed to calling it Brumer-Stark unit. And in some places, it still says Gross-Stark. But they are used interchangeably by people. So depending on their point of view. If you come from the p-adic side, you call it Gross-Stark unit. If you come from the side of Stickelberger, then you call it Brumer-Stark unit. So you should read this Gross-Stark as just Brumer-Stark. Okay, so this Brumer-Stark unit, it lives in H completed at capital P, but that's same as F completed at small p. Okay, so you can ask, can you give a formula for this U in F completed at P? Okay, and more or less in his PhD thesis, Samit gave a formula for this. So he conjectured a formula for this Brumer-Stark unit as an element of this p-adic field. Okay, so as I mentioned earlier, if you prove this conjecture about the precise formula, you get Hilbert's 12th problem, okay, or p-adic solution to Hilbert's 12th problem. Hilbert stated it in a way like you need an analytic formula, and so one way to interpret this is as a p-adic analytic formula. Okay, so you get p-adic analytic formula for generators of Abelian extensions of totally real fields. So this is my work in progress. So it's work in preparation, in fact. So we prove this conjecture of Dasgupta under very mild assumptions. So we have to stay away from finitely many p's, but that's enough for applications to Hilbert's 12th problem. Okay, so you can always stay away from a small finite set of primes for Hilbert's 12th problem. So that's beyond Gross-Stark. So so Gross-Stark tells you just what the norm is, and Dasgupta's conjecture tells you exactly what the unit is, and that's what we prove. Okay, so in the last couple of minutes, let me just give you a very, very brief sketch of how the proof of Brumer-Stark goes. Okay, so remember, I have to prove, so there should be HF here and the decoration hash. Okay, so this, which means that you send G to G, so summation AGG to summation AGG inverse, that kind of thing. But anyway, so I want to prove this inclusion. Now, so this is an ideal generated by theta in ZG. This is another ideal in ZG, or Z1 over 2G. This is also an ideal in Z1 over 2G. now I want to prove that this ideal, the left-hand side ideal, is contained in the right-hand side ideal. Okay. All the methods that we know using modular form only give you inclusion in the other direction. Okay, it will never give you inclusion in this direction directly. Unfortunately, this first inclusion can be strict. So there are many cases where the right-hand side will not be contained in the left-hand side. Okay, so this is not an equality. So remember, this is already a stronger form of Brumer-Stark conjecture. Now, you make an even stronger form of Brumer-Stark conjecture where you replace this theta by some variation. You replace this class group by some other variation. So these are called by tildes. And then you conjecture that the ideal generated by this theta tilde is same as the fitting ideal of this class group tilde. Okay. So this statement should be strong enough to give you the first inclusion. Okay, so you have to come up with such a statement, and this was done by Kurihara and by David Burns and Popescu and so on. Unfortunately, we can't directly use their version, so we had to come up with our own version, which was slight variant of all those things. But that was strong enough for us to get the strong Brumer-Stark, get the first inclusion. Okay. Now, as I said, we can use modular forms to get that the fitting ideal is contained in the theta, in the L function, right? So we can always, I mean, the modular forms will always tell you that it will give you ways of constructing elements of. So this inclusion means that you have to construct lots of elements in the class group. Okay, and modular forms give you elements of constructing, gives you a way of constructing elements of the Galois cohomology. Okay, so this is due to, it goes back to Ribet in 1970s when he proved the converse to Herbrandt's theorem. So you use congruences between Eisenstein series and cusp forms to come up with elements in the Galois cohomology group. Okay, and this is a particularly difficult case because it's what is called p indistinguishable. So the eigenvalues of the Hecke, the roots of the Hecke polynomial at p, they are equal. And Ribet's method has never been used in this case before. So, in fact, this is a sort of novel refinement of Ribet's method that is used here. Okay, so we get this inclusion, and then we bootstrap this going back to our class number formula that I mentioned earlier to show that actually, if you have this inequality in all cases for all intermediate extensions, then you actually get an equality. Okay, so you have to bootstrap this and get the equality. Once you have this equality, you can reduce the thing you want. Okay, so that's all. Thank you. If you have any questions.
Yeah, thank you, Professor Kakre. So there are some questions in the chat box.
So how do
yeah, sure. Yeah. So question from YouTube, sir, what is totally imaginary extension? I think
oh yeah, so it is just, so totally real field means that all the embeddings into C, they land inside R, and totally imaginary means that all the embeddings into C are not contained in R at all. Yeah, so they also land outside R. So for example, if you take Q cube root of 2, then that's neither totally real nor totally imaginary, because there's one embedding that lands inside R and two embeddings that don't land inside R. But if you take Q square root of minus D, where D is positive square free, then that's totally imaginary, because both embeddings are not contained in R.
So another question.
Oh, somebody already answered it actually. Yeah.
So another, so if all embeddings are non-real, yeah. And the last question. So are the Brumer-Stark units related to Ramachandra's units in the case of H mod A equal to imaginary quadratic extension of Q?
No, so these are, I mean, the Ramachandra units are related to what are called cyclotomic units. So those are on the plus side. So those are actual units actually, and these are p units. So they are not actual units. P units are somehow easier to construct in some sense than actual units. Like we don't know how to construct units. If you want to construct p units philosophically, that's kind of easy. You just take p and p bar and sort of take the ratio p over p bar. I mean, it may not be principal, so you raise it to high enough power, you get principal ideal. So you take p to the h divided by p bar to the h, and the generator of that is a p unit, and somehow that kind of thing works. So that's somehow you should. I mean, so what I do is in some sense much easier than constructing these actual units.
I have a question.
Yes.
Yeah.
So, when you defined that L function corresponding to number field,
Yes.
so their chi was a character on the Galois group.
Yeah.
So now, in the L function, you define chi of an ideal. So how are you looking at
use class field? You use the Artin map there. You go from the ideal to the element of the Galois. Yes. So it uses something quite deep, and I kind of took it as standard that you get a element of the Galois group using the Artin map.
Okay.
I have another question.
Oh, yes. Hi, Gautam.
Oh, hi, Mahesh. How are you?
I'm fine, thanks.
So this goes back to very early stages of your talk when you talk about introduce the relevance of the Stark conjecture to Hilbert's 12th problem.
Yeah.
You've probably answered my question, but I have maybe not been able to decode what you said. So I'm talking about the Stark units, okay, not the Brumer-Stark units, but the Stark units.
Mm-hmm.
So the Stark units generate Abelian extensions of number fields. But do we know what are the analytic functions of which the Stark units are values?
Yeah, so you kind of have to change. No, so we don't. You kind of have to change your point of view in some sense. That these are, I mean, Stark gives a formula for these units in terms of L values, right? L functions. And so in that sense, you get some analytic formula for these units. So you don't have one. Unlike sort of imaginary quadratic fields or rational numbers, you don't have one function, one analytic function whose values will give you everything that you want.
Okay.
So you take these L functions. So you kind of, it may not be what Hilbert had in mind, but this is the best we can do at the moment.
I see. So Hilbert's 12th problem is almost like a tactically vague statement, and it's open to interpretation. Yeah.
Yes, and I think that's why he actually did not speak about it in ICM, though I think he thought of this as an important problem, and he worked on it quite a lot. As I said, he gave a proof of his proof of Kronecker-Weber's theorem is the first sort of correct proof.
First correct proof.
No, and so I think there are problems which he spoke about it in ICM, and there are problems which he just wrote down. And this is one of the things he just wrote down because I think he couldn't make a precise statement, I suppose.
I see. Okay. Thank you.
Yeah. Is there any other questions?
I have a question. So about this p-adic analog of the Stark conjecture. Is that what is the shape of the conjecture look like? Like, do you have to choose a p stabilization, and then it's a conjecture about the L value?
P-adic Stark. I mean, this is the p-adic Stark conjecture.
No. I mean, in the last couple of slides, you mentioned that you're working on a p-adic analog of the construction of Brumer-Stark unit.
Oh, so you mean Dasgupta's conjecture, for example?
Yeah. Sure.
Yeah. So you can think. I mean. So one way to think about this is a p-adic L function is a measure on some on a global Galois group.
Yes.
So it's a so if P is inert in F, for example, then it's a measure on FP cross modulo closure of global units.
Okay.
Okay, that's the global Galois group in that.
Mhm.
I mean, in the case of Brumer-Stark conjecture. And what Dasgupta did was he lifted this measure from FP cross global closure of global units to FP cross.
Okay. Okay.
So he lifted this measure. Now this, I mean, unlike p-adic L function, which is a well-defined function, this measure depends on lots of choices. Okay, there's no unique way of lifting it. But what he showed that its value, I mean, somehow when you integrate it against a particular function, just the identity function, it gives you a well-defined quantity. And that is what he conjectured to be the Brumer-Stark unit.
I see.
Okay,
So this is
yeah,
this
so
is the analog of
that's how he removed the ambiguity that appears in Gross-Stark by lifting it.
I see.
Actually, it's a slight refinement of Gross-Stark, but yeah, he removed the ambiguity coming from the image of global units.
I see.
Yeah. And what you said about p stabilization is what sort of comes in the proof actually. So if you want to do this using p-adic modular forms, yes, you have to work with p stabilizations of certain Eisenstein series.
I see. Okay.
Yeah.
Thank you.
Yeah. Any other questions? Yeah, it seems there is no other question. So thank you so much, Professor Kakri, for this wonderful talk.
Yeah, thank you for having me here.
Yeah, thank you. So it's 10:57. Maybe we can have 2 or 3 minutes break, and then again we can start around 11 o'clock. And next we will have 5 contributory research talks.
How do I stop sharing? Stop share.
Yeah, so we can have 3 minutes break. Okay, so we'll meet around 11 o'clock.
Yeah, Shumana Hatui, you can share your screen maybe.
Yes, Sumana. Yeah.
You can see my screen, right?
Yes.
My voice is audible?
Yes.
Yes.
Yeah, so we can start the next part of this session. So we will have 5 contributory research talks, and it is 15 minutes talk. And then after each talk, we can have 5 minutes question and answer session. Yeah, so our next speaker is Dr. Sumana Hatui from ISC Bangalore, and she will speak on projective representations of Heisenberg groups. Yeah, Dr. Sumana, you may start.
Thank you, Dipankar. Okay, so good morning, everyone. So yeah, I'm Sumana Hatui. I'm postdoc fellow at ISC Bangalore. Okay, so today I will talk on projective representations of Heisenberg groups. This is a joint work with Professor Pooja Singla. Okay, so I will start with the definition. What is projective representation of a group? So a map rho from G to GLV, where V is a vector space over a field F, is called projective representation if there is a map alpha from G cross G to this F star such that rho X, rho Y is alpha XY, rho XY, and rho 1 is identity matrix. Okay. So yeah, so if you remember ordinary representation, in that case, alpha is actually 1. So ordinary representations are already included here because you can take alpha to be trivial map. And so projective representation is basically the generalization of ordinary representations. So those are already included here. Okay, and if you see this associativity property of this rho, so if you break rho X, rho Y, and then take rho Z, and if you take rho X, then you break rho Y, rho Z, then you will get this condition on alpha. So this is called 2 co-cycle condition. So, okay, so every projective representation, that means it's associated with a 2 co-cycle alpha. That means this condition is satisfied. And this rho, which is associated with this alpha, is called an alpha representation. So we say rho is an alpha representation. So that means if I take any co-cycle alpha, then I can talk about that alpha representations. Okay. So, okay. So, yeah. So these I'm saying because of these are the parallel things happens like ordinary representations. Okay. So, you know, in ordinary representation, you have this group algebra structure, right? So here also, if you want to talk about this is called twisted group algebra. For a 2 co-cycle alpha, we can define this group algebra, but it's the same thing, but the multiplication on the basis element will be defined through this alpha. So this is called twisted group algebra. Okay. And also we know, so there is bijective correspondence between ordinary representations and FG modules. And here also this is true between alpha representations and F alpha G modules. So these things happens parallelly. And similarly, if G is a finite group, you can break this CG. You know, every representation appears in the group algebra CG. So you can break in this way. This is also true here for C alpha G. For every alpha you can take. Okay. Okay. So yeah, so projective representation was started by Schur while he was studying Schur multiplier and projective representations. So this is very fundamental work by Schur. Okay. So yeah, so here I am defining this Schur multiplier, which is very much related to the projective representation of group. Okay, so we already seen what is 2 co-cycle. We have seen this alpha, if a alpha from G cross G to F star satisfies this condition, then we say alpha is a 2 co-cycle. Now we are defining what is 2 co-boundary. So 2 co-boundaries are the mapping from G cross G to C star, or you can define on F star even. But in the talk, I will talk about the complex projective representations always. Okay. So because it's algebraically closed, it's nice fit. So I will talk about that. Okay, so such that beta xy can be written in this form. So these are called 2 co-boundary, and these are already subset of the 2 co-cycles. These are already 2 co-cycles. So I defined this 2 co-cycle by 2 co-boundary. This forms Abelian group. You can just component wise you can multiply in C star. So you can define it's an Abelian group. So I can define this quotient group. Okay, so co-cycle by 2 co-boundary. This is known as Schur multiplier. But we have seen that if you want to find a projective representation, you need a co-cycle. But why we are talking about 2 co-boundary? Okay, So what is our aim in this talk mainly? So suppose suppose we know a 2 co-cycle alpha. So for every 2 co-cycle alpha, our aim is to describe irreducible alpha representations of G. Okay, so for each alpha, if you consider all irreducible alpha representations up to linear equivalence, then we will construct all projective representations. So this is basically our goal for Heisenberg groups, for finding the projective representations of Heisenberg groups. Okay, okay. So this is very important thing here. Why we are talking about up to 2 co-boundary? Why we're not talking about every co-cycle? Okay. So suppose if I give you 2 co-cycle alpha and beta, but they are same here. That means they are equal up to 2 co-boundary. So they differ by a 2 co-boundary. Okay. Then there is bijective correspondence between these irreducible alpha representations of G. Okay. So this set I am always defining for irreducible alpha representations of G up to linear equivalence. And so irreducible beta representations of G, they have the bijective correspondence. So that's why you can always take a nice co-cycle up to 2 co-boundary, because there are some nice co-cycles up to 2 co-boundary. So for example, if I say what will be the irreducible alpha representations when alpha is a 2 co-boundary? So alpha is a 2 co-boundary means I can take alpha to be trivial because they are up to differ by 2 co-boundary. So I can take alpha to be trivial, and then I can say for alpha 2 co-boundary, what will be the irreducible alpha representations of G? Just ordinary representations. So this is the thing. If alpha equals to 1, we have irreducible alpha representations, just the ordinary representations. Okay. So we will always talk about alpha up to a 2 co-boundary. Okay. So what is representation group? So okay, so suppose G is given to you. A group G star is called representation group of G if there exists a central extension in this form such that every irreducible alpha representations of G can be obtained via ordinary irreducible representations of G star. That means if you get this type of central extension such that if you want to study projectives representations of G, it is enough to study ordinary representations of the middle group via this map. So this map I have written. Okay, so that means if you can find the representation group, then you can find maybe ordinary representations, then that will be the corresponding projective representations of G. Okay, so for finite group over algebraically closed field, it's always exist, but for infinite group, it's not well known in the literature. Okay, so for example, I will start with Abelian group. What are the projective representations of Abelian groups? Okay, it's difficult. It's not like ordinary representations. Here, not always the projective representations are one-dimensional even. Okay, why? So just you remember the Schur lemma, right? How we apply Schur lemma in ordinary representation. We write rho GH equal to rho HG because it's Abelian group. Then you forget about this alpha because ordinary alpha are 1. So then you can get this rho G is a G-linear map, okay, between the irreducible modules. So that's why it's become scalar multiple. But here not, because here alpha is associated here. So now rho G is not a G-linear map now. So for Abelian group, if you want one-dimensional representation, your alpha GH has to be equal with alpha HG. And I will tell one thing, that because for cyclic groups, only the projectives are one-dimensional. For other Abelian groups, there are always higher dimensional projective representations. Okay. Okay. So this I will not explain this theorem much. So this I am saying just we have proved this result also. So if you take this type of Abelian group, so R you can take 0 or any natural number. So this type of Abelian group, if you take, then this group, this presentation I have given, so this group is a representation group of this. That means if you want to find projective representations of this Abelian group, now you can find the ordinary representations of this group. Okay. And for example, if you take this Abelian group, so if you want to study projective representation of this Abelian group, you have to study ordinary of these Heisenberg groups. And you know, Heisenberg groups are higher dimensional, has higher dimensional ordinary representations. That means it has higher dimensional projective representations. So for Abelian groups, it's not easy, okay, to find things. Okay, so here is one main theorem in our joint work. So let G be a finitely generated group And suppose you have this type of stem extension. Stem extension means this A is contained inside the commutator as well as in the center. Okay. So suppose I take a cohomology class alpha in H2G sister, which is in the image of inflation. Okay, what is image of inflation? Just you take a co-cycle here, G by A to sister, then you compose with this G, you will get inflation map. It's just a natural map. Okay, so if alpha is in the image of inflation, then I can talk about what will be the irreducible alpha representations of G. That will be the all irreducible beta representations of G here, such that these betas are going to alpha. So this tells you how the projective representations of G and which alpha representations are associated with which beta representations of G by A. Okay. So for example, if I take inflation is trivial map, that means here every co-cycle, every cohomology class going to trivial here. That means your projective, here you will get all irreducible projective representations of G by A, and here you will get irreducible representation of G. And this is actually your representation group. G is called representation group of G by A. We have seen, because these irreduced ordinaries are corresponding to the projective of this. And if your inflation is surjective map, you can see here everything is going to every alpha. That means your projective representations of G and projective representations of G by has the bijective correspondence. So this will reduce the problem that you can find the all in projectives of G by A. That will have bijective correspondence. Okay. So now let's come to the our main work, Heisenberg groups. So what are the Heisenberg groups here? So I'm taking this semi-direct product Rn plus 1, R is a commutative ring with unity, and Rn plus 1 semi-direct product with Rn with this multiplication. Okay, it's just if you take t equal to 1, these are the general Heisenberg groups. But if I take t is a not invertible element in R, these will give us non-isomorphic classes of groups. So there are many non-isomorphic classes of groups, and these type of groups we are calling t variants of Heisenberg groups. And for t equals to 1, Heisenberg groups are already included here. Okay. So for this type of groups, we will see because after abelian group, what type of group can come? That nilpotency class 2 groups, and these are the groups, Heisenberg groups. So we are talking about now. So okay, and also one thing, to study these projective representations of any group, if you want to study, the Schur multiplier is very much needed to compute this or to discuss these projective representations. Okay, so here the thing is that these Heisenberg groups for n equal to 1, that means the 3-dimensional Heisenberg groups has different type of projective representations, and for n greater than 1 they have a similar type of projective representation. So we are taking first n equals to 1, and this is giving us the Schur multiplier. So I am not discussing this thing because Schur multiplier is needed to prove this result, that how you can compute projective representations of Heisenberg. So now for this Heisenberg group, what we have proved? We have proved this presentation I have given here, and this H hat RT, this group is a representation group of this. That means if you want to study projective representations of this H3TZ RZ, you have to study ordinary representation of this H hat. And actually in H hat, it's easy to compute the ordinary representations. It's not difficult to compute. So this we have proved. And for n greater than 1, for n strictly greater than 1, we have computed what is Schur multiplier. And what we have proved? We have proved that if you want to study the projective representations of this Heisenberg group for n greater than 1, it's enough to study projective representations of this abelian group. R is a commutative ring with unity, we have seen. So it reduces to study the projective representation of this, because we have proved, we already told there, inflation, if inflation is surjective, your G and G quotient by A has bijective correspondence between projective representations. So if you want to study projective of this is enough to study projective representations of this abelian group. And how to study projective representations of this abelian group, we have already told in the abelian group part. Yeah. So so this is the thing here, and so this is joint work with Pooja, and okay. and here are some references. So this was basically by Schur, and the literature you can find in the G. Karpilovsky books, Projective Representations and Schur Multiplier. And yeah, thank you for your attention.
Thank you, Dr. Sumana. So, if there any question, is there any question? Yeah, so there is one question in the chat box. What about projective representation of integer Heisenberg groups?
Yeah, integer Heisenberg groups. Yes, you can talk integer Heisenberg groups. You means you are taking commutative ring to be Z, right? It's R, I can take Z. Yeah, I can talk about here even. I can take R to be commutative. Yeah, so this, I can take R to be 0. So then your Heisenberg groups will be over Z. So over integer coefficients you can talk about.
Any other questions? Yeah, so it seems there is no other question. So thank you so much, Dr. Sumana, for this nice talk. Yeah, so I'll request Rahul Kumar. So you can share your screen maybe. And
Rahul, yeah.
are you speaking, Rahul? It's not audible.
It's not audible. If you are speaking, we cannot hear you. And you kindly share your screen. Initially, it was okay. Just open the file that you want to present, right? Yeah. So now you go to the full screen mode. That's perfect. Now just unmute yourself and speak. Yeah.
Yeah, left side. Yeah, left corner.
I guess there is some problem with his audio.
Yeah, it is.
Maybe you can use a headphone or microphone.
Oh, so he is using headphone. Don't know. Maybe you can sign out and you can come back. And that.
Yeah, maybe.
Rahul, can you sign out and sign in again? So he's trying with other device.
Rahul, what you can do is you can just stop your share screen sharing, and then you try it again. You just give it another shot. Yeah, that would be the best option. Yeah.
Hello.
Yes, and now it is audible.
Now we can share your screen.
You can share your screen.
Yes. It's saying that host disable participant screen sharing.
Oh, you have Shoma?
This is Rahul Sharma.
Shoma, could you make him a co-host?
Yeah, so you are now co-host.
Okay.
Yeah. So can you share your screen?
Yes.
Yeah, so go to full screen mode.
Yes.
Yes, perfect. Yeah. So our next speaker is Rahul Kumar from IIT Gandhinagar, and he will speak on a connection between Hurwitz-Zeta function and Lomel functions and a new proof of Hurwitz formula. Yeah. So Rahul.
Yeah. Thank you, sir, for the introduction. So I will welcome everyone. Good morning. So I will talk about a connection between Hurwitz-Zeta function and Lomel functions and a new proof of Hurwitz's formula. This is joint work with Professor Atul Dikshit. So this is outline of my talk. First, we will discuss some basic facts about Riemann-Zeta function and Hurwitz-Zeta function. Then I will talk about our recent work on Hurwitz-Zeta function. So let us start with the definition of Riemann-Zeta function. It is, as we know, that it is initially defined by this infinite series in this right-half plane, where it defines an analytic function. And moreover, zeta function can be analytically continued to the entire complex plane, except for a simple pole at h equal to 1, right? And Riemann also given this following beautiful functional equation for the Riemann-Zeta function, which actually relates the value of Riemann-Zeta function at s and at 1 minus s. It is actually, you can observe that s is just going to 1 minus s. So one more important generalization of Riemann-Zeta function is Hurwitz-Zeta function, which is actually initially also defined by this infinite series in the right-half plane real part of s greater than 1, and you have to fix a in this slitted complex plane. Okay, and if you take a equal to 1 in this Hurwitz-Zeta function definition, you will get back to Riemann-Zeta function, right? For real part of s greater than 1. And like Riemann-Zeta function, Hurwitz-Zeta function can also be analytically continued to the entire complex plane, except for a simple pole at h equal to 1. So now let me give you one fundamental result in the theory of Hurwitz-Zeta function. It is valid. It is known as Hurwitz's formula, and it is valid for real part of s less than 0, and a has to be between 0 and less than equal to 1. So here you can see that you have this so-called cosine Dirichlet series and sine Dirichlet series. And if you take a equal to 1 here in this formula, you will see that this series will be gone to 0, and this series will be reducing to Riemann-Zeta function. So you are getting back to the Riemann's functional equation for Riemann-Zeta function. So what we did recently, we provided a new proof of this formula, And our proof is unique in some ways. I will talk more about our proof, but before that, let me give you one more important formula in the theory of Hurwitz-Zeta function, which is known as Hermite's integral. So it is actually valid for real part of a greater than 0 and s has to be in complex numbers except s equal to 1. So this is the integral representation for Hurwitz-Zeta function. This formula is valid in the sense that this formula gives you analytic continuation of Hurwitz-Zeta function for whole complex plane except s equal to 1. How? That this integral can be shown that it is an entire function of s. Okay, and you can see that this first term is also an entire function of s, and this second term is an analytic function except s equal to 1, right? So this is telling you that Hurwitz-Zeta function has an pole at s equal to 1 with the residue 1, right? So what we did recently, that we proved Hurwitz's formula that I have mentioned in the last slide by using this Hermite's integral. So the novelty of this proof is that it reveals a connection between Hurwitz-Zeta function and the Lommel functions, which to the best of our knowledge seems to have been unnoticed before. So I will talk more about these Lommel functions, but these Lommel functions arise in the theory of differential equations. So this connection is important because it is giving you a connection between two special functions which are coming from two different branches of mathematics. One is coming from analytic number theory and one is coming from differential equations. Although there are many proofs of Hurwitz's formula in the literature, but no proof reveals this connection and makes use of Hermite's integral. Okay, so before going in the proof details of the proof of our result, let me give you some existing proofs from the literature. So Hurwitz himself obtained this Hurwitz's formula by transforming the Mellin transform representation for Hurwitz-Zeta function as a loop integral, and he then evaluates that loop integral. And this proof can be found out in this book. And later, Model also given one proof by using the Poisson summation formula. And in 1972, Bund found a short proof of this formula, Hurwitz's formula, by using the boundedly convergent Fourier series for this function. Okay, and later Kanemitsu et al. Also found one proof of Hurwitz's formula. Their proofs makes use of this formula, which contains the incomplete gamma function in the series, and then they invoke Fourier series of Dirac delta function. So these are the some existing proofs in the literature of Hurwitz's formula. So now let me talk about Lommel functions. What are these Lommel functions? So as we know that Bessel functions are the solutions of Bessel differential equations. And this Bessel differential equation is nothing but the second order homogeneous differential equation, right? And Lommel functions are the solutions of an inhomogeneous form of Bessel differential equation. You can see this is the inhomogeneous part in this Bessel differential equation. So to define Lommel functions, let me give you one definition of generalized hypergeometric functions. So they denoted by this PFQ function, and they defined by this infinite series. You can see that P number of parameters will be coming in the numerator, and these Q number of parameters will be coming in the denominator. And this notation is nothing but the shifted factorials. Okay, so having this definition in mind, we can define a small Lommel function in terms of this 1f2 function, which is generalized hypergeometric function. And for new non-integral values, we can define capital Lommel function in terms of small Lommel function, and these are the Bessel functions. And for new integer values, this Lommel function can be defined in a similar way. Okay, so these are the definitions of Lommel functions. So now in our paper, we proved this lemma, which is saying that you have this integral evaluation in terms of the Lommel functions, and it is valid for every k and natural number and a is greater than 0. So now let me give you some applications of these Lommel functions in the mathematics. So also outside of mathematics, Lommel functions have been found to be very useful in physics as well as in mathematical physics. In mathematics, Lewis studied a special case of Lommel function by defining a new function CSZ, and you can see this is the special case of Lommel function, and he represented it in terms of the incomplete gamma function for his studies. And later, Lewis and Jagier also used an infinite series involving this function CSZ in the study of mass waveforms. So these are for these two applications, we can see these two references. So moving forward, let me now give you some little proof of this lemma, which is not that straightforward, but can be proved using the Cauchy-Residue theorem. So this is the well-known inverse Mellin transform representation for exponential function. By this notation, we will be meaning this line integral in the complex plane. Okay. And for this range of Xi, we have this well-known result from the literature also. So if you use Parseval's identity for these two identities, we will be having our integral that we are wanting to evaluate in terms of this line integral. So our now goal is to evaluate this line integral, and we evaluate this integral by using Cauchy-Darcy theorem. So we first evaluate this more general integral, right? Here you have 2 pi ik, but we first evaluate this integral with z and complex number. So what we do, we have now line of integral right now on this C, but now we shift this line of integral to another line integral on minus lambda. But while doing that, we are encountering poles of gamma function, gamma s plus xi and gamma 1 plus xi by 2. And these poles are coming at these points, where m is running between these limits and n running from between these limits. To avoid the same double order pole in this contour, we are forcing that real part has to be between -1 and 0. So that means we will first prove our result for this range of S, and then we will extend it by analytic continuation. And first we will evaluate this integral also for this range of Z, and then later extend it to all Z in this selected complex plane by analytic continuation. So residue and at these poles, at these simple poles, can be calculated to these expressions. And one thing can be shown that if you take t tends to infinity along these horizontal lines, you can see that these integral along these horizontal lines goes to 0 by using Stirling formula. So by using that fact and Cauchy-Darcy theorem, this line integral can be evaluated to this expression. And one thing also can be proved here, that if you take lambda tends to infinity, this integral will also go to 0 by using some Stirling formula and calculate some calculation. So that means we have this ISZ is now in terms of this infinite series, because we are taking lambda tends to infinity. So we have now infinite sum. And it can be observed that this infinite series are analytic function in this selected complex plane. And this line integral can also be shown to be analytic in this range. So by analytic continuation, we can say that this identity holds for all Z in this region. So now we can take Z equal to 2 pi ik in this, because our Z can be anything in this plane. So upon taking Z equal to 2 pi ik in that expression, we are finding out these two infinite series. And if you use the definition of Lommel function S, you will be observe that these two infinite series are nothing but the special case of Lommel function. And we have proved our result between -1 and 0, right? So, but it can be shown by some little work that this integral is an entire function of S, and it is well known also that this Lommel function also analytic for all S. So therefore this our result holds for all S belongs to C. So this proves our lemma. So now I will go to the proof of Hurwitz's formula. So as we discussed, this is the Hermite's integral for the Hurwitz's formula, right? So what we do now, we represent this term 1 upon exponential 2 pi x minus 1 in terms of an infinite series. That infinite series is nothing but k running from 1 to infinity exponential minus 2 pi kx. Okay, so that means now after representing this term by this infinite series, we interchange the order of summation and integration. That can be justified. And we have proved that this integral is nothing but the Lommel function. So this is the connection between Hurwitz function and Lommel function, that the infinite series containing these Lommel functions are actually evaluating to the Hurwitz function. Okay, and if you now use the definition of this Lommel function, you will be observing that you are getting the same terms as we have in the Hurwitz's formula, right? These are the exactly same terms as we have in the Hurwitz's formula. That means we will be done with the proof of Hurwitz's formula if we can show that the evaluation of this infinite series cancel out these first two terms. And that can be done by using a recent result of Maserwitz. She gave the following evaluation of this infinite series. And if you now specialize the parameters here, you can see that we are getting the evaluation in terms of these two terms with a minus sign. And while doing it, we are getting two restrictions on our parameter. S has to be less than 0 and A has to be between 0 and 1. Restriction on A is coming from this fact that we are taking x equal to 2 pi A, right? And here x has to be between 0 to 2 pi. That means A equal to 1 case, we have to deal separately. And if you substitute this expression in our main expression, then you will be seeing that for s less than 0 and A between 0 and 1, we have proved the Hurwitz formula. But now you can see that these two series, infinite series, are convergent for real part of s less than 0 and also defines an analytic function. And left hand side is also an analytic function for real part of s less than 0. That by analytic continuation, this identity holds for real part of s less than 0. So for A equal to 1 case, what we do, this up to this step, this process was valid for A greater than 0. So we can take A equal to 1 here. That means this left hand side will be reducing to Riemann zeta function. That means now we have to prove the functional equation of Riemann zeta function by our approach. Okay, and if you take A equal to 1 in this expression, you will be saying that now we have to prove that this infinite series cancelling out these two terms. And Maservich also given one more result, which is valid actually for x equal to 2 pi also. Okay, so even though we can take x equal to 2 pi in this formula, but note that m has to be a natural number. But to evaluate our series using this formula, we would require m equal to 0. So what we do now, we translate this series to a new series by using this recurrence relation for Lomel functions, using this relation to evaluate another series. So we have translated our original series to a new series. And now this new series can be evaluated by using Maservich result by taking m equal to 1 and x equal to 2 pi and m equal to minus s minus 1. So that means we have this evaluation for s less than minus 1. And if you now substitute these all values and do some calculation, you will be seeing that for s less than 1 minus 1, we have proved that formula for Hurwitz zeta function. So this is the functional equation for Riemann zeta function, and we have proved it for s less than minus 1. But now observe one thing, that both sides are analytic for all complex s's, because pole at s equal to 1 of Riemann zeta function can be compensated by the pole of gamma function 1 minus s at s equal to 1. So by using analytic continuation, we can say that this identity holds for all complex numbers. So we have proved the Hurwitz formula for real part of s less than 0 and A between 0 and less than equal to 1. So I will stop here. Thank you.
Yeah. Is there any question? Yeah, if anyone has any question, they can ask directly. They can unmute their microphone and they can ask. Yeah, so it seems there is no question. So, and we are also, thank you, Rahul.
Yes, thank you, sir.
Yeah, so our next speaker is Jayatra Chattopadhyay. So, Jayatra, are you here?
Yes, sir.
Yeah. Yeah, maybe you can share your screen.
Okay. So I hope it is visible, right?
Yes, yes.
Okay.
Yeah, so we can start maybe. So our next speaker is Jayatra Chattopadhyay from Harishchandra Research Institute, and he will speak on simultaneous 3 divisibility of class numbers of imaginary quadratic fields. Yeah, Jayatra, you may start.
Okay. Thank you, sir, for the introduction. And I would like to begin by thanking the organizers for giving me the opportunity to speak here. And I also acknowledge their effort to come up with the idea of organizing this wonderful math fest amid still this pandemic. So thanks for that too. So let's begin. So the title of my talk is Simultaneous 3 Divisibility of Class Numbers of Imaginary Quadratic Fields. So before we plunge into the main topic of this talk, let us begin with the notations first. So by K, we mean So by K, we mean an algebraic number field K, which is nothing but a finite extension of the field of rationals Q. And along with this K comes the ring of integers OK, which is the integral closure of Z inside K. And we denote the discriminant of the number field K by dk. And having said this, we have the class group CLK, which is an important invariant associated to the number field K. And it's a celebrated theorem from algebraic number theory that the ideal class group is finite. And the order of this group is known as the class number of K. So this class number actually measures the obstruction of the ring of integers OK from being a principal ideal domain. So in the sense that from the definition of the ideal class group CLK, it follows that the class group is trivial. That is to say that HK is 1 if and only if the ring of integers OK is a principal ideal domain. So at this point, it is natural to ask what are the number fields K for which the ring of integers is a PID or the class number is 1. But that's a very difficult question to address, as we will see in a moment. So beyond Q, because we know that for Q, the ring of integer is Z, and that's a principal ideal domain. So class number is 1 there. So beyond Q, if we go, so the next thing that comes is the imaginary quadratic fields. So Gauss asked for a complete classification of imaginary quadratic fields with class number 1. And it has been solved in the early 60s by the works of Higner, Becker, and Stark. So they gave a complete characterization of imaginary quadratic fields having class number 1. So these are given by the precisely 9 values of D, namely 1, 2, 3, 7, 11, 19, 43, 67, and 163. But surprisingly, if we ask the analogous question for real quadratic fields, then the situation drastically changes. So for imaginary quadratic fields, we know the complete characterization of imaginary quadratic fields having class number 1. But for real quadratic fields, it is still unknown, and it is famously attributed to the Gauss class number 1 conjecture, which asserts that there exist infinitely many real quadratic fields with class number 1. So for imaginary quadratic fields, we know the complete characterization, whereas for real quadratic fields, it's still unknown. So given any integer n, if we want to characterize the number fields having class number equal to n, that turns out to be very difficult, as we can see from the Gauss class number 1 conjecture, because to classify real quadratic fields with class number 1 itself is very difficult. So number theorists consider a weaker version of this question, namely the divisibility question. So instead of exact equality, we ask for, given any integer n, whether there exist finitely many or infinitely many quadratic fields with class number divisible by that integer n. So by the work of Nagel in 1922 and followed by the works of Ankeny and Chawla in 1955, we know that this question has an affirmative answer. So for any integer n bigger than or equal to 2, there exist infinitely many imaginary quadratic fields with class number divisible by n. And by Weinberger in 1973, we also have the result for real quadratic fields. So given any integer n, there exist both real as well as imaginary quadratic fields with class number divisible by n. Now, the interesting question is, what if we consider the divisibility question of more than one number fields taken together? So towards this direction, in 1932, Scholz gave this beautiful result. So he proved that if D is a positive square free integer and R and S are the 3 ranks of the ideal class groups of the real quadratic field Q square root D and the imaginary quadratic field Q square root minus 3D, then S is either R or R plus 1. So that is to say that if the class number of Q square root D is divisible by 3, then that of Q square root minus 3D will also be divisible by 3. And this result will be crucially used in the proof of our main theorem. So having said this Scholl's reflection principle, if we combine this with Weinberger's result, which says that there exist infinitely many real quadratic fields with class number divisible by n, and if we just take n to be equal to 3, then we get this proposition that asserts that there exist infinitely many pairs of quadratic fields. One is real, q square root d, and the other one is imaginary, q square root minus 3d, such that the class numbers of all of them are divisible by 3. Now the question is whether we can replace this integer minus 3 appearing inside the square root here, or the integer 3 appearing as the divisor in the conclusion here by some other integer. So this question was considered by Komatsu in 2002, and he proved that indeed we can change this integer minus 3 by any non-zero integer m, and the divisibility question still has an affirmative answer. So precisely he proved that if we take any non-zero integer m, then there exist infinitely many distinct pairs of quadratic fields q square root d and q square root md, such that 3 divides the class numbers of both of them. So the next challenge is whether we can replace the integer 3 appearing in the divisor by some other integer. So this question again was answered by Komatsu partially in the sense because he could consider only imaginary quadratic fields. So he proved that there exist infinitely many pairs of imaginary quadratic fields of the form q square root d and q square root md, such that the class numbers of are divisible by n. So we don't have any analogous result for real quadratic fields here if we ask the question of divisibility by some integer n other than 3. Okay, so whatever problems we have discussed so far, we see that the elements appearing inside the square root, they differ by a multiple of this d. So Izuka recently considered a slight variant of this question where he considered instead of multiplicative shift of d by an additive shift. So precisely he proved that there exist infinitely many pairs of imaginary quadratic fields q square root d and q square root d plus 1, where the thing appearing inside the square root is an integer such that the class number of both the fields are divisible by 3. And he also conjectured that this phenomena is nothing special for 2 consecutive discriminants or the divisor 3, but it should hold for any prime number bigger than or equal to 3 and any consecutive, imaginary or real quadratic fields having consecutive discriminants where the discriminants vary along z. So the precise statement of his conjecture was this. So we start with an integer m, which is bigger than or equal to 1, and a prime number L, which is bigger than or equal to 3. Then there are infinitely many tuples of real or imaginary quadratic field q square root d up to q square root d plus m with d belonging to z, such that the class numbers of all of them are divisible by L. Okay. So we addressed a weaker version of this conjecture by Izuka and proved the following result. So this is a joint work with Dr. M. Subramani. So we proved that if we start with a cube-free integer k, which is positive and falls in the arithmetic progression congruent to 1 modulo 9, such that k is co-prime to 7 and 571, then there exist infinitely many triples of imaginary quadratic fields q square root d, q square root d plus 1, and q square root d plus k square, where d is in z, such that the class numbers of all the fields are divisible by 3. And to the best of our knowledge, this is the first result towards the direction of simultaneous divisibility, where 3 fields are being considered at a time. Okay, so let me just outline a brief sketch of the proof, how it goes. So to prove this result, we proved 2 parametric families of quadratic fields with class number divisible by 3. So for the first one, we considered an integer t, which is not divisible by 3. Then the class number of this quadratic field, q square root 3t times 3888t square, plus 108t plus 1, that is divisible by 3. And note that here there is no restriction on the integer t as to whether it is positive or negative. So this quadratic field is in our control. We can make it real or imaginary, whatever we like, depends on t. Okay. So, and the proposition 2, this is about the class number divisibility of an imaginary quadratic field. So this says that if m is some positive integer, then the class number of q square root 1 minus 2916 m cube, that is divisible by 3. Okay. So in the remaining time, let me give an outline of the proof. So we start with a cubic polynomial that is parametrized by a variable t. So x cube minus 27tx minus k. So note that here the k is the fixed integer with which we started in the beginning. And by rational root theorem, we know that this polynomial can be reducible only for finitely many values of t. So we can choose a large enough positive integer t naught such that beyond mod t naught, ft is always irreducible. Now we look at the discriminant of this polynomial, which is 27 times 2916 t cube minus k square. And this is a kind of equation. If we want to look at for which values of t, d of ft becomes perfect square, then actually we are asking for the solution of 27 times 2916 t cube minus k square is equal to some r square. And by Ziegel's theorem on curves, we know that it can have only finitely many values of t for which this can be a perfect square. So again, we can fix some integer t naught prime beyond which the discriminant is not a perfect square. So we just set the integer capital T to be the maximum of these two integers just constructed, modulus of t naught and modulus of t naught prime plus 1, so that for any integer t which is bigger than capital T, the polynomial ftx is both irreducible as well as the discriminant fails to be a perfect square. So now we consider this simultaneous congruence. We will see in a moment why we are considering this. So here the moduli are 9 and k. So since k is assumed to be in the arithmetic progression 1 modulo 9, so these moduli are co-prime. So by Chinese remainder theorem, we know that there exists a unique solution x naught say modulo 9k. And then we consider this set, which is the set of all solutions x naught modulo 9k, and the integer is bigger than maximum of t and k. So we are considering this because at some point of time we will consider this parametric cubic polynomial ftx, which is irreducible and the discriminant is not a perfect square. All right. So having defined this set n, we are now looking at this expression 27 times n times 3888 n square plus 108 n plus 1. So remember, this is the expression that appeared in one of our parametric families that we have considered before. Now, if we read this expression modulo k, by the hypothesis on k, we know that this is non-zero modulo k because we have assumed that k is co-prime to 7 and 571 and k is 1 modulo 9. So it is obviously co-prime to 3. Then for this choice of tn, we consider the polynomial ftnx. And we see that this polynomial is irreducible and d of ftn is not a perfect square because tn will be bigger than capital T. Now here comes an important application of a result of Lorentz and Natt that asserts that if we have an irreducible cubic polynomial whose coefficients satisfy some congruence relation, then the splitting field of that cubic polynomial over Q, that will be an unramified everywhere extension of the quadratic subfield Q square root dftn. So once we have an unramified extension, then we can embed it inside the Hilbert class field. And by class field theory, we know that the class number will be divisible by the degree, and that is here 3. So in this way, we get hold of a quadratic number field whose class number is divisible by 3. Now let us look at more closely how this D of ftn looks like. So if we plug the value of D of ftn, we get that the quadratic.
So
Yeah.
time is up. Can you please conclude your talk quickly?
Yes, sure. I'll just take just 30 seconds. Okay. So it just takes this form, and this is a real quadratic field. So by the Scholz's reflection principle, we get that after multiplying it with -3, we get hold of this imaginary quadratic field whose class number is also divisible by 3. Now, by the proposition 1 and 2 that we have considered, we get that the class number of q square root minus tn, which is 1 minus 2916 tn cube, that is also divisible by 3. So by the choice of dn equal to minus 2916 tn cube, we get that the class numbers of all of them are divisible by 3. So this ends the proof, and these are the references. So our work was inspired by the first paper by Izuka, and these are some of the references. Okay, that's all I had to say. Thank you.
Thank you. So is there any question?
Yeah, I have one.
Yeah. Yeah, you may ask directly.
Yeah. So what was the motivation behind considering the polynomial ftx, that one, like x cube minus 27tx? I mean, it seems, why did you choose that to begin with whatever you were doing?
Okay, so actually, if we look at the result by Lorentz and Natt that I have mentioned, I have written here. So this result basically tells you what are the conditions on the coefficients of the cubic polynomial, so that the splitting field of this polynomial is unramified over the quadratic subfield. So we have to choose the coefficients in such a way that the conditions of this hypothesis of Lorentz and Natt's results get satisfied. So we had to consider the coefficient 27 for that, to take care of some congruence condition, and some weird conditions on this integer k, such as it is co-prime to 7 and 571, and in the congruence class 1 modulo 9, just to satisfy the hypothesis of Lorentz and Natt's theorem.
Okay.
Because the only result we have been appealing to is the result of Lorentz and Natt and the class field theory result.
Okay. Thanks a lot.
I had a question.
Okay.
Yes, sure.
Yeah, so here this is, I mean, we can say that this is generalization of the result, that instead of there being a pair of class numbers, there is actually a triple of class numbers, such that they are divisible by some specific number. So, I mean, can we, is it possible to think of a generalized result in which we see that there exists an n tuple of class numbers coming from some quadratic extensions, such that they are divisible by a number?
No,
I mean,
actually, that's what has been precisely conjectured in the paper of Izuka. So actually, we don't know. There have been works towards that direction, and that is the best thing we could come up with.
Okay.
So far, whatever results we had in the literature, that deals with only the pairs of quadratic fields. Maybe the conjecture is true, but that may not come in the way that we have followed, like starting with the cubic polynomial and then embedding that inside some unramified extension. But that's the result we have been using.
Thank you.
Yeah. Any other question? Yeah.
Can I ask a question?
Yes.
Can I ask a question?
Yes, please.
You see, there are applications of algebraic number theory to quantum information theory, particularly symmetrically informationally complete positive operator valued measures. And there are papers by Appleby, Bankson, Flaminga, and many people. And there is an expository article by myself on archive 1804.0 08100, and you can see section 3.4 in that of relationship between these things, and Fibonacci numbers and Lucas numbers occur in that. So I would like you to see if there are applications in quantum information theory the way I have told.
Okay, I will look at it.
Thank you.
Okay, thanks.
Thank you, ma'am. Yeah, thanks, Jayatra, for this wonderful talk. Maybe we can have 5 minutes break, and then we can have 2 more contributory research talks. Yeah, thank you, Jayatra. Yeah, we will have 5 minutes break. Yeah. We can meet again at 12:05.
And what we is it clear? I have this instead of writing lambda 1 to lambda n, there may be repetition among lambda n's, right? That's why I wrote lambda 1 is
Yeah, Ashish, are you there?
Yeah, Dipankar, I am here.
So next,
Am I visible?
yeah, it's visible. So
And
since,
am I audible clearly?
yes.
Okay.
So since in the schedule it is mentioned 12:10,
Mm-hmm.
we should not start before that. Yeah, so
Yeah.
we start at 12:10.
Okay.
Yeah.
Till then, I can share my screen. Yeah. There is no problem in that.
Sure. Yeah. Yeah, it's 12:10. So welcome So the last part of this morning session, and our next speaker is Dr. Assis Misra from Federal University of Para, Brazil, and he will speak on representation theory of partition algebras for complex reflection groups. Yeah, Dr. Assis, you may start now.
Okay, thank you, Deepankar. First of all, I would like to thank organizers for this conference and for giving me this opportunity to present my work here. The results presented in this talk form a part of a joint work with Dr. Shraddha Srivastava. Please forgive me if I seem sleepy during the talk. It's 3:30 in the morning here. So let us begin. Okay. So yesterday there was a talk by Digjoy where he talked about classical Schur-Weyl duality and partition algebras. So I will not revise classical Schur-Weyl duality. Let me start with partition monoids. So partition algebras were actually defined by Jones and Martin in the early 1990s. Both defined them independently as a generalization of temporally Lieb algebras and as a generalization of Potts model from higher dimensional statistical mechanics. So let us see what are partition algebras. For a non-negative integer k, let us define ak to be the set of all set partitions of 1 up to k and 1 prime up to k prime. What we mean by this is that elements of ak are set of subsets of 1 up to k and 1 prime up to k prime. These are disjoint subsets and their union is this set 1 up to k, 1 prime up to k prime. And the elements of A can be actually depicted as graphs. It is easier to think about them in this way. And these graphs are called partition diagrams. The vertices in this graph are 1 up to k in the top row and 1 prime up to k prime in the bottom row. When we consider an element of AK, it is a set of subsets, disjoint subsets, and each subset is called a block. The elements in the block are connected by a path, and those form the edges in the graph. We will see an example in the next slide. First, I want to finish these definitions. Okay, so we can make AK a monoid with the multiplication where we multiply two partition diagrams by concatenating these diagrams, and we remove all those blocks which are entirely in the middle. Okay, and this makes it a monoid, and this monoid is called partition monoid. Let us see an example. So for these D1 and D2 are elements of A4. D1 is 1 to 1 prime, 3 3 prime, 4 to 4 2 prime, 4 prime. So let us see, this 1 to 1 prime is a block. So here these are connected. 3 3 prime is a block, 4 is a single block, and 2 prime and 4 prime are connected. And in a similar way, we depict D2 also. The lower row of D1 and the upper row of D2 are identified, and the multiplication is done. Like here, 1 to 1 prime, and this 1 prime is identified with 1. 1 goes to 2 prime, 3 prime. So in the multiplication, it is this block 1 to 2 prime, 3 prime. And in this way, we do the multiplication. But notice here that there is a block here which is entirely in the middle, 2 prime, 4 prime, and 2 4. So this block is actually removed. Okay. So this is the way of multiplication in partition monoids. Let us see what are partition algebras. Partition algebras are vector spaces with these elements of AK as basis. These elements are called partition diagrams. So this basis is called diagram basis. Okay, and the multiplication is defined using the multiplication which we defined in the partition monoid, but we have a complex number Q which denotes the deformation. So this L, so the multiplication D1 D2 is actually Q raised to power L D1 circle D2, where D1 circle D2 is the concatenation in the partition monoid, and Q raised to power L, where L is the number of blocks which are removed from the middle while computing D1 circle D2. Like in the last example, this L will be 1. So in the last example, D1 D2 will be Q D1 circle D2. This algebra is called the partition algebra. And of course, we have defined the basis, which is, we have defined it with the basis, which is the diagram basis. However, partition algebras has another important basis, which is called orbit basis. And in fact, orbit basis sometimes prove to be more useful rather than the diagram basis. So for that, first we define partial order on the partition monoid for any two elements D and D prime in the partition monoid. D prime is said to be less than equal to D if D prime is coarser as a set partition than D, which means that if I and J are in the same block in D, I and J should be in the same block in D prime, which means that blocks in D prime are obtained by union of some blocks in D. Okay, using this partial order, we define, given an element D in AK, we define the unique element XD in the partition algebra by D is equal to taking the sum over all D prime, which are less than equal to D, and the sum over corresponding XD prime. So the transition matrix between the diagram basis and these elements XD is an upper triangular matrix with ones on the main diagonal, and therefore this XD is also a basis. This is called orbit basis of partition algebra. We will see the use of it later in the talk. Okay. So Schur-Weil duality. Jones actually proved the Schur-Weil duality between the partition algebra and the symmetry group while acting on the k-fold tensor product of V, where V is the n-dimensional complex vector space. So Sn can be considered as a subgroup of permutation matrices of GL and C. GL and C acts naturally on this n-dimensional complex vector space, and therefore Sn acts. And similarly, we can define an action of the partition algebra on this V tensor K. I will not go into that definition. Okay. So symmetry groups are a particular family of complex reflection groups. What are complex reflection groups? A reflection in a complex vector space W, in a finite dimensional complex vector space W, is a linear transformation of finite order that fixes a hyperplane. A complex reflection group is generated by reflections in this vector space W, and this complex reflection group is said to be irreducible if the orthogonal complement of the fixed point space is actually irreducible. So an important question is, what is the partition algebra for the complex reflection groups? Of course, complex reflection groups include all the symmetry groups, include Weil group of type Dn, includes Weil group of type Dn, includes Weil group of type G2 also, includes dihedral group. So this is an important question. So let us see. So first of all, we define what is the group GRPN. So our parameters R, P, M, and N are positive integers, where we assume that P actually divides R and M is R by P. So GRPN can be considered as a subgroup of GL and C. It consists of generalized permutation matrices with non-zero entries being RF roots of unity, and the mth power of the product of non-zero entries is 1. Okay. There are other ways of seeing this group GRPN, but let us, for this talk, we fix this way of seeing GRPN. Okay, in 1954, Shepard and Todd classified finite irreducible complex reflection groups, and they showed that GRPN is actually the only infinite family of irreducible finite complex reflection groups. There are 34 more finite complex reflection groups, but GRPN is the only infinite family. So let us see. Let us see what was already known before our work regarding the partition algebra for GRPN. So Tanabe in 1997 described the centralizer algebra of the action of GRPN on V tensor K. And the partition algebra for GR1N was actually defined by Orellana in 2007. So what we do in our work, we actually define partition algebra for GRPN for any divisor P of R. And our work, as it was recently published in Algebraic Combinatorics, it is titled On Representation Theory of Partition Algebras for Complex Reflection Groups. Let us see the definition of this partition algebra. So let us fix a block B of a partition diagram D, and NB is the number of elements in block B in the top row of D, and MB is the number of elements in the block B in bottom row of D. Pi KR is the set of, so now we define 3 subsets of AK, which will be helpful in defining the partition algebra for complex reflection groups. So the first subset is pi KR. Pi KR is the set of all elements in AK such that for each block BI, the number of elements in the top row and the number of elements in the bottom row their difference is actually divisible by R, and this happens for each block. Then the next set is lambda k RPN. This consists of all those elements in AK which have exactly n blocks, okay, and the difference of the number of elements in the top row of each block and the number of elements in the bottom row of each block is actually divisible by m. Remember, m is r by p, but this difference is actually not divisible by r for all I. Okay. However, the difference of differences is actually divisible by r for each I and j. Okay. And then there is this theta set, theta k RPN. This consists of all elements in AK which have more than n blocks. Again, the difference is divisible by m, difference between the number of elements in the top row in each block and the number of elements in the bottom row in that block is divisible by m. However, there exists at least one block where this difference is not divisible by r. So define AKRPN to be union of these disjoint subsets of AK, phi kr, lambda krpn, and theta krpn. Now, this tkrpn is actually the complex span of orbit basis. Notice that here we take orbit basis elements corresponding to D. It's not diagram basis elements. When Orellana defined for P is equal to 1 case, she was using diagram basis elements. However, when you go for any divisor P of R where P is not necessarily 1, one has to use orbit basis. And it is important to note that for the case P is equal to 1, these two vector spaces, span of orbit basis elements and span of diagram basis elements, actually turn out to be the same. Okay, so this is the first theorem in our paper, that the vector space, this TKRPN, is actually a subalgebra of partition algebra. The multiplication of XD, or multiplication of orbit basis elements, is actually not so visible easily and it requires some work. And the multiplication of these elements was actually first published by Arun Ram in his notes, which are, those are published on his website, but not published in any journal. So this appeared in our work and also in the work of Halverson and Bankert. So we call this TKRPN Tanabe algebra in honor of Tanabe, who first worked on centralizer algebra for GRP. Okay. So in Schur-Weil duality, the usual consequence is that the representation theory of one object is actually connected to the representation theory of the other object. So both complex reflection groups and Tanabe algebras, their representation theory become connected. And actually a combinatorial object, MP necklaces of Young diagrams, play a fundamental role in their representation theory. However, we will not define it here for the lack of time. So let us see further results, which are the important results. Of course, the first important result is that this Tanabe algebra is in Schur-Weil duality with this complex reflection group while acting on k-fold tensor product. The decomposition of the centralizer algebra into irreducible modules, and then using Schur-Weil duality, double centralizer theorem, we parameterize the irreducible modules of Tanabe algebras. When we construct the Bernoulli diagram recursively for the tower of Tanabe algebras, of course, here we need more, something called half Tanabe algebras. However, since the talk, in the talk, we just focused on the partition algebra for GRPN. So in this case, the Bernoulli diagram turns out to be a simple graph. And whenever Bernoulli diagram is a simple graph, we have UC Murphy elements and Gelfand-Zetlin basis. And actually, we find out these UC Murphy elements of Tanabe algebras and give their actions on Gelfand-Zetlin basis. And finally, since the representation theory of one object is connected to the representation theory of another object, so there must be some results which were missing on the side of complex reflection groups. And for that, we actually construct a specific basis of irreducible GRPN modules using Okonoko-Werschik approach, Clifford theory, and higher spec polynomials, and apply this construction to actually determine the branching rule. Now there is a subgroup of GRPN which plays an important role in the whole theory, and we need to know the branching rule from GRPN to that subgroup. So with this, I will finish. Thank you.
Thank you, Ashish. Is there any question from the audience? Yeah, so since there is no question, so thank you, Dr. Asif.
Okay.
Thank you so much for your nice talk.
Okay, thank you.
Um,
Yeah, hello, ma'am.
very good, Ashish, very good.
Okay, thank you, ma'am.
Yeah, thank you, ma'am. Yeah. So we'll move to our next speaker. Yeah, Dishari, are you here?
Yeah, I'm here.
Yeah, so you may share your screen.
Okay. Is it visible?
Yes, yes.
Is my, just a minute, is, okay. Can I start or should I wait?
Maybe just one minute.
Okay. Just tell me when I can start, huh?
Yeah, so this will be our last talk of this morning session. And our speaker is Dr. Dishari Chaudhary from ISER Mohali. And she will speak on skew symmetric elements of rational group algebras. Yeah, you may start now.
Yeah, thank you, Dipankar. So good afternoon, everyone. I shall be speaking about skew symmetric elements of rational group algebras. But before I start, I would like to thank the organizers. And also I would like to thank Professor IBS Pasi and Dr. Abhay Soman, with the help of whom I have been able to learn this subject. Okay. So given a finite group G and a commutative ring R with identity, we can always form a group ring over G, which can be seen as a free R module with the group elements as basis elements. That is, RG consists of all the sums, formal linear sums of the form summation AGG over G, and with coefficients from the ring R. And it also has an underlying ring structure where the addition and multiplication, you can do it in the same way as you would do in case of a polynomial. Now, when you add the usual bracket operation to the group ring, to the group algebra RG, you get what is known as you get a Lie algebra. Okay. And let sigma be an involution of the group algebra RG, that is an anti-homomorphism of order 2. So for example, if you take the group map which takes every element of the group G to its inverse, and you extend it linearly to the whole of group algebra RG, you get an involution of the group algebra RG. And this involution is famously known as the canonical involution. And another example would be if you take any group automorphism and you compose it with this map, and then also you can get another involution of RG. Okay, so the elements of RG of this form, elements of RG gamma, such that sigma gamma is equals to minus of gamma, are said to be the set of skew symmetric elements of RG with respect to the involution sigma, and we denote this set by RG sigma minus. Now, with respect to the usual bracket operation, RG sigma minus becomes the Lie subalgebra of the Lie algebra RG. Now, we all know when RG is semi-simple, Then RG decomposes as a product of simple algebras. I mean, each simple algebra is a matrix algebra over a division algebra, which is famously known as the Wedderburn decomposition. Now, the Lie subalgebra of skew symmetric elements would lie somewhere in this, inside this decomposition. Okay, so whenever we have a Lie algebra or an algebra or a group, say, we always try to decompose it into smaller structures called simple groups or simple algebras or simple Lie algebras, as they form the atoms of any structure. So how do the Lie algebra of skew symmetric elements break, and how do they embed inside this Wedderburn decomposition? So Cohen and Taylor, they studied group algebras over the complex field C, and they considered the canonical involution of CG, and they showed that CG sigma minus decomposes into a sum of classical simple Lie algebras according as the irreducible characters of G are of real or symplectic or complex types respectively. Okay, and a similar decomposition was shown by Marine, but he considered a slightly more general setting where he considered group algebras over a field K of characteristic 0, such that every ordinary representation of G is defined over K. For example, you can take K to be a field containing all the nth roots of unity. And the involution which he considered over Kg was sigma G equals to alpha G, G inverse, where alpha is a multiplicative character of G. Okay, so in this situation, the Lie algebra of skew symmetric elements of Kg again decomposes according as into sum of simple classical Lie algebras according as the irreducible characters are of complex type or quaternionic type or real type respectively. Now, both these results, they use something very nice called Frobenius-Schur theory. And this is a theory which can only be applied to group algebras over algebraically closed fields or fields having very nice and rich properties like K, as we saw in the previous slide. But what about the decomposition over fields like Q or any algebraic extension of Q? Now, the theory of group algebras over fields like QG, they involve a lot of technicalities and a lot of subtleties, which make the theory very interesting over such fields. So we want to see what happens to the Lie algebra of skew symmetric elements of Fg with respect to any arbitrary involution sigma of Fg, where F is an algebraic extension of Q. But before we do that, let us recall some basic definitions. So if E be a central simple algebra over a field F with characteristic F not equals to 2, then and let M be a finitely generated right E module, and suppose that theta is an involution on E of any kind. So what we mean by kind, I'll explain it in 1 or 2 minutes. For the timing, you just assume theta is an involution of E. Then a Hermitian form on M with respect to the involution theta on E is a biadditive map H from M cross M to E, such that H of X alpha Y beta goes to theta alpha H X Y beta for all X Y in M and for all the scalars alpha beta in E. As M, we have taken it to be a right vector space over E. I have taken the scalars on the right, and HYX is equals to theta of HXY. Okay. So if the condition 2 is replaced by HYX equals to minus of theta of HXY, then this form H is said to be a skew Hermitian. And if the central simple algebra is nothing but the base field itself and the involution theta is nothing but the identity map, we get back our good old bilinear forms over finite dimensional vector space M over F, right? And the Hermitian or skew Hermitian form H on M is said to be non-singular or non-degenerate if the only element in X such that HXY is equal to 0 for all Y belonging to M is the 0 element. Now, for every non-singular Hermitian or skew Hermitian form H on M, there always exists a unique involution sigma H on the endomorphism algebra of M over E, such that sigma H and theta, they are equal on all of F. They are equal element-wise on all of F, on the base field F. And also H satisfies this relation, that is H of X Fy equals to H of sigma H of F of X Y for all xy in M and for all element in the endomorphism algebra of M over E. And this unique involution theta is called the adjoint involution with respect to H. Now there's a one-to-one correspondence between non-singular Hermitian or skew-Hermitian forms on M and involutions on the endomorphism algebra of M over E. Okay, so that means every involution on this endomorphism algebra of M over E can be written as an adjoint involution of a non-singular Hermitian or skew-Hermitian form on M with respect to an involution on E. And also this form is uniquely determined up to a central invariant factor under the involution. Now let us look at a few more definitions before we proceed. If A is a central simple algebra over a field Z, where Z is of course its center, and it is endowed with an involution sigma, such that sigma fixes F element wise, where F you can take it to be a fixed subfield of the center Z of A. It's very easy to see that this involution sigma will preserve the center Z. Okay, then sigma, when restricted to the center Z of the central simple algebra A, will be an automorphism, which will either be the identity or of order 2. And this is easy to see because sigma, I mean, involutions are anti-homomorphisms of order 2. So when restricted to anything commutative, they become automorphisms. Okay. So involutions which leave the center element-wise invariant, that is, it is the identity on the center, such involutions will be said to be of the first kind. And involutions whose restriction to the center is an automorphism of order 2 are said to be of the second kind. Now, we know that any central simple algebra A has a splitting field, and the splitting field is often, I mean, you can take it to be the separable closure of the central field Z. Okay, then A tensor, the separable closure becomes it can be written as an endomorphism algebra of some vector space V over the separable closure ZS of Z. Okay, so if you have an involution sigma of the first kind on A, then you can extend it to an involution of the first kind on A tensor ZS. So now we have an endomorphism algebra over V and some involution sigma tensor identity on it. As we have seen that such involutions are in one-to-one correspondence with non-singular forms. So that means this involution sigma tensor identity which we have got can be written as adjoint to some non-singular symmetric or skew-symmetric bilinear form B on this vector space V. Now, if the non-singular bilinear form is symmetric, then the sigma, the involution which we started with on A, is said to be of orthogonal type. And if B is skew-symmetric, then the sigma, the involution on A, is said to be of symplectic type. Okay. And as a parallel terminology, involutions of the second kind are also sometimes said to be of unitary type. Okay. So let's look at some examples quickly. So if we have a quaternion division algebra D over Q and the canonical involution gamma over that algebra, that is gamma sends I to minus I and J to minus J, then gamma will be a symplectic involution of DQ. Okay? And on the same algebra, if you consider the involution sigma, which you write as sigma x equals to I gamma x I inverse, then sigma will be an orthogonal involution of DQ. Now, if you consider a quaternion division algebra D over the field Q root D for some quadratic, for some square free integer D, then the quaternion division algebra DQ root D, it decomposes, I mean, it can be written uniquely as a tensor product of D0 and Q root D, where D0 is a unique central quaternion division algebra over Q. Okay. Now, if you have iota as the non-trivial Q automorphism of QD, that is iota sends elements of the form A plus B root D to A minus B root D. And if you define the map tau as gamma tensor iota, where gamma is the canonical involution on this D naught, then tau will be an involution of second kind on this quaternion division algebra over Q root D. Okay, so these are basic examples that are, I mean, you can check it. Now, if A is a semi-simple F algebra of the form A1 cross A2, then the semi-simple algebra endowed with an involution sigma of the second kind will be isomorphic to the semi-simple algebra A1 times A1 opposite with the exchange involution. What is the exchange involution? Exchange involution is something that sends elements of the form A, B opposite to B, A opposite. Okay. So now let us get back to our group algebra FG, where F was, recall that G was a finite group and F was an algebraic extension of the rationals and sigma is any arbitrary involution of FG. Then FG with sigma decomposes into a direct a product of central simple algebras with involution, or it decomposes as a direct, product of two central simple algebras with the exchange involution. But let us concentrate on the factors in the product of this form. Okay, so this decomposition it can be shown very easily in 2-3 steps actually. So let us consider a central simple algebra of this form M and D endowed with an involution sigma. Now M and D, where D is a division algebra, of course, it can be written as the endomorphism algebra of Dn over the division algebra D, where Dn can be seen as a right vector space over D. So you have an endomorphism algebra over Dn and an involution on it, and this is a central simple algebra, and over the center say D, say Z, we call it Z, and that center is a finite field extension of F. Okay, this F. Now as M and D is Brouwer equivalent to D, there will exist an involution say theta on D, which is of the same kind as sigma. So this is a well-known result by Hilbert. He proved it in late 1920s or 1930s. I'm not sure about the date, but yeah. So now you have an endomorphism algebra with involution. You have an involution on this base division algebra D. So because there's a one-to-one correspondence, as we have seen with non-singular forms and such involutions, there will exist a non-singular Hermitian or skew Hermitian form H on Dn cross Dn to D with respect to theta on D, such that this sigma will be the adjoint involution of H. That is, sigma will be equal, we can write it as sigma H, and it will satisfy this relation Hx Fy equals to H of sigma H of Fx y, right? So now we can choose a non-zero linear form L from Z to F that commutes with theta restricted to Z. Okay, and we can take the reduced trace map of the central simple algebra D over Z. Okay, and you can define the map S from D to F, where S is the composition of L and the reduced trace map of D to Z. Okay, so this map is something which is called involution trace, and it has very nice properties, and those properties will help us in constructing a new non-singular Hermitian or skew Hermitian form from Dn cross Dn to F, okay, with respect to theta on F, such that we call this new non-singular form S star H. S star H of xy will be equals to S of H of xy. Okay, and if H is Hermitian, S star H will be Hermitian. If H is skew Hermitian, S star H will be skew Hermitian. Okay, so now the important thing is to note here, that is the image of the Lie algebra of skew symmetric elements of Fg under the projection of Fg onto one of the factors M and D. It will consist of all those linear transformations in this division algebra, such that S star H Fixy plus S star H x Fiy equals to 0 for all xy belonging to T. Now, with all these observations and filling up all the minute details which I had to skip, we can get the final, the main results on Fg, which will be as follows. So if Fg is a group algebra, with all those assumptions as we have discussed earlier of a finite group G over a field F, which is an algebraic extension of Q, and sigma is an arbitrary involution of F, then there will exist an involution theta on F and a right F vector space M, which will be a left Fg module, okay, and a non-singular form or skew Hermitian form H on M cross M to F on M with respect to the involution theta on F, such that sigma can be written as the adjoint involution of H. And the Lie algebra of skew symmetric elements, it consists of all those elements in Fg such that this relation is satisfied. Okay, And but how does it decompose? It decomposes into something like this. So FG, you can write it as a direct sum of endomorphism algebras of V over division algebras D, where V are irreducible left FG modules up to isomorphism. Okay, and because these are central simple algebras, let its center be Z and let the degree of this central simple algebra over Z be NV. Then, sorry, FG sigma decomposes in like in this manner. Okay, so as you can see the analogy, I mean this the orthogonal type, these are the symplectic type, these are the unitary type. So what is GO tilde? Of course, the orthogonal type, that is consists of those irreducible FG modules up to isomorphism, such that sigma restricted to this endomorphism algebras over V goes to itself, and the dimension of the Lie algebra of skew symmetric elements on this central simple algebra is NV into NV minus 1 by 2, whereas G SP tilde, you can see it as symplectic type, where those irreducible modules where sigma restricted to them takes it to itself, but the dimension here is something like this, NV into NV plus 1 by 2, and NV is necessarily even, whereas the unitary type of irreducible representations, the sigma restricted to those endomorphism algebras will take it to itself or the opposite algebra, and the dimension of the central simple algebra, I mean the Lie algebra of skew symmetric elements on that central simple algebra will be NV squared. Okay, so I mean, yeah, so it's seen. So it finally it appears that the results which you have seen for complex group algebras and other nice fields will actually can be extended similarly to fields like rationals or algebraic extensions of rationals, but the theory becomes a little twisted at the same time, much more interesting too. So yeah, that's it. And these are the references which you can look at it. So yeah, thank you.
Yeah, thank you. Is there any question?
Yeah, I have a question. Can you hear me?
Yeah.
I missed the point, but you are assuming the extension to be algebraic, right?
Yeah.
Okay. So where are we exactly using that property?
Where are we using?
The extension is algebraic.
That the extension is algebraic.
Yeah.
We are not using the property as such, but I mean, it can be. It's a generalization of the result that it not just over Q, but over any algebraic extension, also the result will hold. Okay, I mean, we are not using it.
Okay, so building on that, so if I just take, let's say, a transcendental extension of Q.
Sorry, I can't hear you. Sorry.
If I take a transcendental extension of Q, for example.
Okay.
Then will the result hold true, or there will be some problems? That was.
Yeah, like you.
Okay.
Thank you. Yeah. Any other question?
Can I ask?
Yeah, sure, ma'am. Yeah.
You see, there is a concept of trivolution, where instead of rho being invertible, rho square equal to identity, you take rho cube equal to rho.
Okay.
So that is in my papers with Filali and Monfared, and also in my own paper in Studia Math 2011. The concept is given there and elaborated in my paper in Illinois Journal. And it is in a paper by Dagan. You just write Dagan and trivolutions. On page 30, definition will come.
Oh, okay.
And the Dagan's paper is on the concept of infinity.
I see.
Okay,
sure. I'll definitely have a look at it. Thank you.
Okay, thank you. Very nice talk. Very nice.
Thank you so much.
Thank you.
Thank you, ma'am, for giving this information. Yeah. Is there any other question? Seems no. So thank you, Dr. Desari, for this nice talk.
Yeah, thanks a lot. Yeah.
And with this, we will conclude this session, and our next session will start at 2 o'clock. Thank you all for joining with us.
Professor Dipankar Ghosh for chairing the session. Thanks a lot.
Thank you. Bye now.
Hello, ma'am.
Hello.
Hi. Hi.
It was mute, so I couldn't. Okay.
Yeah, so you can, so we'll wait for Dr. Manas to come. He will.
Okay. I will just share the screen and make it a lot.
Sure.
Yes,
Sure.
sure.
Is my desktop visible?
Yes. Yes.
So just to remind me once, the talk is for 45 minutes or?
Yeah, the talk is
Right.
45 minutes and then 15 minutes question answers. But you can, yeah, I mean, you can go up to 50 minutes. I mean, 5 minutes extra also if you want.
Okay, fine.
Yeah.
Yeah, maybe we can start now. Still, we have 1 minute left.
Yes.
Okay, so welcome to this afternoon session of this virtual meeting. This is very interesting virtual math space. So our first speaker in this session is Dr. Mousumi Bhaumik from IISER Pune. She will be talking about non-local scalar field equations. Yeah, please, Mousumi, continue.
Yes, thanks, Manoj. Just a little correction. So my name is Moshumi Bhakto.
Oh, sorry. Yeah. most of, yeah, sorry, yeah.
It's okay.
Yeah.
Yeah. So anyway, thank you for the introduction, and thanks a lot to the organizers for inviting me to this virtual math fest to give a talk, and many thanks to them for organizing such a nice math fest, because it was, when it was announced, it was sort of it was, I think, the kind of first in India, but then Inter-Eisenhower also happened just before it. But in these difficult times, to organizing this is in such a big scale, it's a really awesome activity. I mean, it's really big effort, and I really would like to thank the organizers, the postdocs who organized it. Big thanks to them. Okay, so I will talk about this non-local scalar field equation, and it's basically an expository article, and I have tried to keep it like elementary, keeping also in mind of for the students and the people from analysis who are not from exactly this field. Okay, so let me see. Okay, so I will just a second. Okay. So I will talk about this scalar field equation, which I denoted as E. So this is this reads as minus delta S U plus VXU equal to GXU in Rn. So I will describe each of these terms. What is this? What these terms means. So just first, Vx is a potential and Gxu is a non-linearity. I will again talk about more that what kind of non-linearity we are dealing with here, and what is this operator here? The operator what I have written as delta SU. So to define the operator, this delta SU, I need to first, I will define it on the Schwartz space function. So, and what is the Schwartz space function? So these are the rapidly decreasing C infinity functions. So by that, what I mean that suppose I say that phi is in the Schwartz space is, that means that phi is C infinity, and if you take any order derivative of phi and multiply with any order polynomial, then the product of that function, I mean, it has the property that it goes to zero at infinity. So that means it's rapidly decreasing at infinity. So it actually, there is a topology in this space which is generated by this seminum. That's a standard Schwartz space called. Okay, so on this Schwartz space, this operator, this minus delta is defined. Sorry. Yeah, it is defined in this way. So it is defined with this integration. So it's called integral differential operator, and it is defined in the principal value sense, because you see there is a singularity at x, around x. So what you need to do is that you have to take a small ball around x, and you have to remove that small ball and then take the limit. So that's how this operator is defined. And this is called a non-local operator. And why that is clear, then why it is non-local, because you see this to know the value of this minus delta SU at any point x, you need to know the value of u in the entire space Rn. So it's not just you need to know the value, like when it is s equal to 1, when it is just a Laplacian, you know that to know the value of Laplacian of u at some point, you just need to know locally u at that point. But it's not the case here. So that's why it is called non-local operator, and CNS is a constant which is given by this. Now this minus delta is actually is called the fractional Laplacian, and I will just tell in a minute that why do we actually call it as the fractional Laplacian? I mean, what's the motivation for it? Okay. So next, using this so here there is a constant. Okay, now if you see the if you study the asymptotics of this constant, then one can actually see that s goes to 1, this minus delta s u is actually approaching to minus Laplacian, and as s goes to 0, this is actually approaching to u. I mean, so you can see that there's a limit, it's actually going to as s goes to 1 is that Laplacian. And also there is another motivation behind it, calling the fractional Laplacian, which is the main motivation. So you can see that when S is in 0, 1, we can actually equivalently define fractional Laplacian or minus delta S operator. And this actually generalizes the definition of from minus Laplacian to minus fractional Laplacian. So you see this one, like when S equal to 1, this is very well known, because if you take the Fourier transformation of Laplacian, so this is inverse of the Fourier transform, so you can take it on this side. So what you can see that if you take the Fourier transform of the Laplacian, you know that what it is. So it is nothing but xi square u hat, that's xi square Fourier transform of u. So that means you can define minus Laplacian u by taking the Fourier inverse of this one when S equal to 1. So question is that can we generalize it? Yes, we can. So what we have written here, the previous definition, it can be shown that using some change of variable and Fourier transformation, that when S is in 0 and there is an equivalent definition, we can actually define it in this way. Okay, so you can to know about more about this fractional Laplacian, and that's why it's called the fractional Laplacian. So to know more about this fractional Laplacian, we can just you can just see this Hitchhiker's Guide, which is very, very well written and for the beginners actually. Okay, so now where does this fractional Laplacian appear? I mean, this appears in many, many different contexts. For example, like thin obstacle problem, optimization, finance, phase transition, crystal dislocation, soft thin films, frame propagation, etc., etc., minimal surfaces, etc. And also, fractional Laplacian provides a simple model to describe certain jump-Levy process in probability theory. Now, that's the first natural question one may ask, that what is the difference between Laplacian and fractional Laplacian? I mean, okay, it's a generalization. Are there, when we deal with the equation with fractional Laplacian, what could be the differences? What are the difficulties? Why it is different? Is it just a generalization, or there are really differences? So there are actually plenty of differences, many differences. I here just like to point out few of them. So first of all, as you first noticed itself, that when you want to define classical Laplacian, you do integrability properties of u, right? But when you want to define this fractional Laplacian, to define this, to make it well defined, one needs this integrability condition on u. Second, another condition what I can say is that, so suppose you know that Laplacian at some point is non-zero. So for example, you suppose Laplacian u0 is 1. Okay. Now, if v is close to u in C2 norm, then you can always say that Laplacian of v at that point is also non-zero. Okay. But this is not at all going to be true in when you go to the fractional Laplacian. In fact, what we can show is that when you take given any epsilon greater than 0 and bounded smooth function u, you can always find a v epsilon which is close to u, that in C2 norm, that v epsilon minus u is less than epsilon in C2 norm, but it is harmonic in B1. So this is a very, I mean, there's a striking difference with the Laplacian case. So actually in the fractional Laplacian case, what happens that almost, I mean, every function is actually locally S harmonic up to a small error. Di Piero Savin Valdinoci in 2017. So next, another we all know that suppose you use a harmonic function in B1 and u is non-negative in B1, then you know that in supremum of u in a small ball, you can actually control by the infimum in that one. Okay, but when you go to the S harmonic function, I mean S harmonic function, you need not just u greater than 0 in B1, rather you need u to be positive, I mean non-negative in the intraspace Rn. You can see the proof here in Abatangialo Valdinoci, this one. And what are the other differences? There are many, as I said. I'm just pointing out only few. So one of the another striking difference is the growth from the boundary. So roughly speaking, if you consider solutions of Laplace equation, that has Lipschitz growth, linear growth from the boundary. Whereas if you consider the solution of fractional Laplace equation, it has only Hilbert growth from the boundary. For example, suppose I take U, consider U which is continuous up to the boundary B1, and it satisfies this minus Laplacian equal to f in B1 and which is 0 on the boundary. Then one can actually show that U has this growth condition, Ux is less than equal to some, it can be controlled by 1 minus mod x. Okay, but when you go to the fractional case, I mean that S harmonic function, it changes. So you see, if you consider this simple function, x goes to xn positive, that's the to the power s. Okay, so it is S harmonic in the upper half space, but this is just a Hilbert continuous function with this Hilbert exponent s near origin. Now, another one is the global regularity in the differences. So if you consider the solution of this Laplace equation, they are smooth up to the boundary. But if you go to this fractional Laplace case, you can maximum expect the Hilbert continuity up to the boundary. So if you just go back to the where did I go? If you just go back to this equation one, this equation U, so there you can see that you can control the sup norm of gradient by this one. But in the case of fractional Laplacian, so you see this example, Ux equal to 1 minus mod x squared to the power s positive. So this is the positive part of the function. So this satisfies fractional Laplace equal to constant, but this is Hilbert continuous in B1. You cannot get more than that. And then another obvious difference which must have observed that Laplacian U, if you consider at 0 or any point or nothing about 0, so you need to know the value of U only at the coordinate axis, right? The coordinate direction. But for the fractional Laplacian, you know that it's not true. You need actually in the entire space Rn. So there are many. Anyway, I just wanted to show you just some of the few differences. Now, if I want to define what is the I go back to the original equation which I wrote first, the scalar field equation, because I will mainly talk about this equation E. So now question is that what do I mean by the solution of this equation? I will say something about weak solution, but to define the solution, I need to define something called fractional Sobolev space. So yeah, so I will define something called fractional Sobolev space. So s greater than equal to 0. For any s non-negative, I define fractional Sobolev space Hs Rn by taking all those L2 function for his j to the power s Fourier transform U. This is in L2 Rn. Okay, and this can be equivalently defined by completion of C0 infinity with respect to this norm. Since C0 infinity is that C infinity function with compact support. That is my notation C0 infinity. Since C0 infinity functions are in the Schwartz space and C0 infinity dense in HSRN, so using density argument, one can actually show that this definition, which I first wrote for the fractional Laplacian on the Schwartz space function, I wrote this definition. So it can be shown that this definition holds for any U in HSRN2. So we can extend it into the fractional Sobolev space. Okay, so now when S is in 0, 1, so actually one can show that this norm, this one is actually equivalent to this Gagliardo norm. So equivalently one can just, this is true for S in 0, 1, I repeat, for S greater than equal to 1, this is no longer true, this equivalence is no longer true. There is a counter example, and in fact this is finite only when S less than 1. So equivalently, one can define write HSRN norm of HSRN as L2 plus this Gagliardo norm. Okay, and HSRN is a Hilbert space for S in 0, 1, and you can write this. I mean, it is a Hilbert space anyway. If it is S greater than equal to 1, also it is Hilbert space. But when S is in 0, 1, you can write this inner product in HS as this L2 inner product, but plus this one because it's coming from this Gagliardo norm. Okay, now we also have a Sobolev, we also have the Sobolev inequality in HSRN. So he says that, so you take any U in HSRN, you can control the L2 star norms, 2 star equal to 2n by n minus 2s. You can control the L2 star norm by this Sobolev, a fractional Sobolev norm, okay? And this is the universal constant. This depends on n and s. Capital S depends on n and small s. So there is a very natural therefore you can actually define now homogeneous fractional Sobolev space, which is denoted by HS dot Rn. So you take all those L2 star Rn. So now I'm not taking L2 part. I'm taking all those L2 star for which this is finite. And I have the corresponding norm. And again using density, you can actually show that Sobolev on this HS dot Rn, we have the Sobolev inequality holds. So now I'm in a position so that I can define what is the weak solution of the equation E, which I just wrote, scalar field equation. What do I mean by the weak solution of that equation? So we say that U in HS dot Rn is a weak solution if this variational formulation holds. So you see U phi inner product in HS dot Rn plus integration Vx U phi equal to integral Gx U phi dx. This should hold for every phi in HS dot Rn, and if all this integration makes sense. So why did I write all this integration makes sense? Because it depends, I mean, what condition I need to put it need not be enough just in HS dot Rn. I may need to take more assumption, I mean more restriction on this. It depends on the nonlinearity G and the potential function V. So for example, suppose I take V is identically 1 and this nonlinearity. This is the polynomial one with subcritical nonlinearity. Then I need to take this solution space as HSRN. So this plus L2, right? No, so then the left hand side becomes the HS inner product, and right hand side should be finite by using Hilbert inequality and Sobolev inequality. So then my space will be, solution space will be HSRN, not HS dot Rn. So that's what I'm saying, that it depends on this V and G. Okay. So in physical context, the question is that my equation, this E, the general scalar field equation, where does it appear, or what is the, I mean, from where it comes, the equation. So this kind of equation, it appears in the fractional cases, in the non-local case, in the study of standing wave for fractional Schrodinger equation and fractional Klein-Gordon equation. In context of fractional quantum mechanics, nonlinear fractional Schrodinger equation was proposed by Lasker in 2000-2002, two consecutive paper in modeling some quantum mechanical phenomenon. In particular, it arises in evaluating Feynman path integral from Brownian-like to the Levy-like quantum mechanical paths. For more precisely, suppose you consider this is the Schrodinger equation. Okay, psi is a complex function, complex valued function defined on Rn times R. So now if you have this nonlinear, suppose you this Gx psi, this has this nonlinearity has this form, so it's homogeneous in this variable and it's continuous, it's assumed at this Gx0 equal to 0, then one can actually look for standing wave solution that psi x equal to I omega t ux. Omega is this one. If you just substitute that, then it leads actually this leads us to the finding out the solution of E. We go back to the scalar field equation. So it's enough, I mean, not enough, I should say, it's very important is that you understand this equation, E scalar field equation. Okay. Now I go back to the standard classical case S equal to 1. In S equal to 1, where this kind of equation appears in many physical contexts, for example, like statistical mechanics, false vacuum in cosmology, nonlinear optics, laser propagation, etc. And they are also called the nonlinear Euclidean scalar field equation. Mathematically, analytically, it was studied by many mathematicians, started by Beristes-Lyons in 1983, and afterwards there were many studies, like some of the famous paper in this area by Digny 1986, Barili 90, Delpino Felmar 96, Wang 93, and most of them dealt with the existence and multiplicity of solution under various assumptions on the potential function V and the nonlinearity G. In the non-local case, so in S is in 0, 1, multiplicity, existence and multiplicity have been obtained for E using various variational technique. For example, some of the quite famous paper I'm just mentioning. There are many works in this direction. So like Fellmer-Quast-Tan in 2012, they have considered the equation E when V is identically equal to 1, and nonlinearity is the nonlinearity is the superlinear nonlinearity, and it's a subcritical superlinear nonlinearity and satisfying Ambrosetti-Rabinowitz condition. Okay, so they proved that existence of solution, and they studied the symmetry of positive solution, whether the solution is symmetric or not. They have shown the symmetry. Now in Sechin 2013, he has considered the equation where the potential V satisfies certain asymptotic assumption as mod x goes to infinity, and the nonlinearity is again superlinear subcritical, and he has obtained existence of ground state solution. Then Frank Lenzman-Silvestre in 2016 in a celebrated paper, they have considered E with V identically 1. Again, G is the subcritical nonlinearity, and proves the uniqueness and non-degeneracy of positive ground state solution. So there was one paper which I forgot to mention, and in this direction, where Frank Lenzman first in I think 2014 Acta Mathematica studied the same equation in dimension 1 and proved the uniqueness and non-degeneracy. And later they, in this paper, they have generalized this in the higher dimension case, uniqueness and non-degeneracy of positive solution. But uniqueness is, the full uniqueness is still an open problem. So also, I forgot to mention that Frank Lenzman-Silvestre also have shown that any positive solution is radially symmetric, and it has this asymptotic behavior, that it at infinity it decays of this rate. It's the exact asymptotic behavior. Okay, as I was saying, that uniqueness for, so what they have established is that uniqueness of ground state solution, which is a remarkable paper and remarkable, it's a very, very celebrated technique that they got, but that is still for ground state solution. Uniqueness for this solution, the subcritical case, fractional Laplacian, it is still open. In the local case, S equal to 1, this uniqueness was proved by Nong, 1989, using ODE techniques, which does not work here. And in the non-local case, which is what uniqueness is known for this one, is one-dimensional case, n equal to 1, s equal to half, and p equal to 2, square nonlinearity. So Amick and Tolan in Acta Mathematica 1991, so they have proved this uniqueness for one-dimensional case equal to 2. Again, it was used heavily that it is a square nonlinearity, and here they used complex analysis since it's an R1, so they used complex analysis techniques, which again does not work in the higher dimensional case and general nonlinearity. So now I just, next I consider V is equivalent to epsilon. So like Vx is a small epsilon x, V is epsilon, and Gxu is this nonlinearity, okay, where Q is strictly greater than P, strictly greater than 2. So here we can include all kind of P, like it is, P could be subcritical, P could be critical, P could be supercritical, okay. And I consider this equation. Okay. So I consider this equation. So this is my P epsilon, and I will next few minutes I will just deal with this epsilon, this equation P epsilon. Okay. In the local case, S equal to 1, existence of positive ground state solution for sufficiently small epsilon was proved by first by Strauss, but they were proved in he able to prove it in certain range of this, not full range, and finally Beristisky-Lyons in 1983 proved the existence of positive solution for small epsilon in the full range. Uniqueness, okay. After small epsilon, it does not exist. Positive solution does not exist, and one can actually prove that using Pozai. So uniqueness of positive solution was proved by Serintang when S equal to 1. Again, I'm talking about in the local case using ODE technique. Complete characterization of asymptotic profile of ground state solution of this as epsilon goes to 0 was studied by Moroz-Muratov in 2014. So now I just will mention some of my result in this direction. for the non-local case, when S is in 0, 1, for this equation P epsilon. Okay, so it was a joint work with my former PhD student. So it's 2019, last year, sir. So we proved that any solution, if we take any positive solution of that equation P epsilon, that is actually a classical solution. And any positive solution has this a priori estimate that it is strictly, any positive solution is strictly less than 1. It goes to 0 at mod x goes to infinity. And not only that, we have established exact asymptotic behavior as mod x goes to infinity. And then we have proved that the existence of solution that there exists a small epsilon, there is a small value epsilon star, such that if epsilon is smaller than that, then it admits a ground state solution. So what is ground state solution? That is the minimum energy solution. Okay, and it's radially symmetric and symmetric decreasing. Then we have proved using moving plane method that any positive solution, if you consider, any positive solution, if you consider for this P epsilon, so you take any positive solution for this, we have shown that any positive solution have to be radially symmetric and symmetric decreasing. So next, we are interested that what happens to the asymptotic behavior of U epsilon, the ground state solution. As epsilon goes to 0, how U epsilon behaves. And it actually changes, it varies whether we are studying the case P is subcritical or critical or supercritical. So P equal to 2 star is called the critical case. So in the critical case, what we have proved that up to a rescaling, up to there exists a rescaling, that if you consider this rescaling, U epsilon is a ground state solution. Okay, so we know that it's a radially symmetric and decreasing. So what you can do is that without loss of generality, you can assume that the maximum of U epsilon for each epsilon, maximum of U epsilon is at 0, because if not, you just translate it, because it is translation invariant, and you know that it is radially symmetric and decreasing. So you can assume that the maximum is at 0. Now you consider those sequence of U epsilon as epsilon goes to 0, and you consider this rescaling. And what we have proved that up to this rescaling, this one V epsilon tilde actually converges to the solution of this Yamabe equation, fractional Yamabe equation in this Hilbert norm HS dot norm. And we have the exact asymptotic behavior, as I said. So we have this exact expression that lambda epsilon tilde this behaves like this, and U epsilon 0 behaves like this. Okay. And when it was for the subcritical case. Now when P is, it was for the critical case. And now if P is subcritical, that P is strictly less than 2 star. So here you notice that here it is anything, there is no restriction on Q. Q could be anything. Q could be critical, supercritical, subcritical, anything. Q is just greater than P. We have the restriction only on P. Okay. So now when P is subcritical, then again there is a scaling. Up to this scaling, we have proved that this converges to the unique ground state solution of these equations. This I mentioned that Frank Lenzman Sylvester have proved uniqueness of ground state solution for this equation. So we have shown that U epsilon up to a scaling in the subcritical case converges to the solution of this one, unique ground state solution of this one, and this is the exact asymptotic behavior. So as one can see that as we have assumed that maximum is at 0. So from this subcritical case and the critical case, so in the subcritical case, you see this, we have this U epsilon 0 is epsilon times what this sum. This is a positive exponent, right? So as epsilon goes to 0, this goes to 0 in the subcritical, and similarly in the similarly in the critical case. In the critical case also it goes to 0 as epsilon goes to 0. So so when you see that U epsilon goes to 0 as epsilon goes to 0 in the subcritical and critical case, and it is consistent with the observation that if you consider P naught, that is epsilon equal to 0, the equation with epsilon equal to 0, that does not admit any finite energy non-trivial solution when in this P is subcritical or critical and Q greater than P. So that means what happens that when we have a solution in the subcritical and critical case, but as epsilon goes to 0, it vanishes actually. And we have the exact asymptotic rate where at which rate it vanishes, goes to 0. Okay. Now, next case is that supercritical case, that P is supercritical. So in this case, if we have proved that U epsilon actually converges to a ground state solution of this equation. Okay. In Hilbert norm, HS dot norm. Here we do not have exact asymptotic behavior because here the uniqueness of this problem is not known. In other two cases, we have the uniqueness was known for the limiting problem. Here it is not yet known because it is yet open problem. So existence of ground state solution for this equation was proved with my former student, that's Devangana Mukherjee in 2017, but uniqueness is still open. And in the local case, A is equal to 1, uniqueness for this was proved by Nong, MacLeod, Pelletier, and Troy 1992 using ODE. Again, which does not work here in this case in a fractional Laplacian. So as I mentioned, for this equation P epsilon, let's go back to P epsilon. Yeah, this so here we have the in the local case A is equal to 1. One has the uniqueness of solution, as I mentioned, it was proved by Serintang. But in the non-local case, uniqueness is not known. Okay, so what based one can try to do is that at least can we establish some asymptotic uniqueness? What do I mean by that? Suppose you have two ground state solution, U epsilon and V epsilon, which has the same asymptotic behavior, that as epsilon goes to 0, it behaves same. So question is then can we say that they are actually same for a small value of epsilon? The answer, we prove that yes. So that's the local uniqueness we prove for the critical and subcritical case. So we prove that suppose you take two ground state solution which have the same asymptotic behavior, that is that with this same rescaling, it goes to that Yama solution of Yamaba equation. Then we prove that this U epsilon 1 and U epsilon 2 has to be same when epsilon is in this interval. There is a small epsilon naught for which below that they have to be same. And same thing we prove it for the subcritical case as well. But we do not, we not have this result. I mean, you could not prove this result for the supercritical case, P strictly greater than 2 star, because we do not have uniqueness for this yet known. And I need to, to prove this result, we need to have uniqueness for the limiting problem, uniqueness of ground state solution for the limiting problem. Okay, so I go back to this equation go back to this equation E, when I consider V, the potential function V is 1 and the nonlinearity again subcritical nonlinearity. So I just said that we know the uniqueness of ground state solution for this one from Franklin Sylvester for ground state solution. Now I give a little bit perturbation to this equation. So just to put a perturbation here by a function, the coefficient function AX, and put a non-homogeneous term here, okay, fx. So why I'm calling a little perturbation, because I'm taking a L infinity function, positive L infinity function, and which goes to 1 asymptotically. And f is a function in the dual space of HS. So it's the dual space non-negative functional. Okay, now what do I mean by non-negative functional? That if f acts on any non-negative function u in this, then this dual space action, so that is greater than equal to 0. So question is that, so if we give us this perturbation, does the small positive solution still survive? So that's what we want to study, okay? So here we have divided the study in a couple of cases. One condition, we study that when A is greater than equal to 1, then we study when A is less than equal to 1, then we take A equal to 0. Some few cases we try to break up this problem. So in a joint work with Devdeep Ganguly and my student Shoptik Chakraborty, first we have proved that when A is greater than equal to 1, we have this asymptotic behavior that A goes to 1 asymptotically and it's always positive and L infinity. This assumption we always have, okay? With this assumption, in additionally, suppose we assume that A is greater than equal to 1, then we should prove that Then we prove that this equation admits two positive solution. We get multiplicity, at least two positive solution when this dual space norm of this one is sufficiently small. And we give exactly how much small it is. So you see that if this dual space norm is less than this, then that admits at least two positive solution. Okay, and what happens when a less than equal to 1? So when a less than equal to 1, I need an additional assumption. We need an additional assumption on that we know that a asymptotically goes to 1, but we need additionally that in which rate it goes to 1, or the control on the rate. So suppose we assume that this asymptotic, suppose you assume this control on this rate. Then we prove that, and also infimum is strictly positive. Under that, we prove that when this dual space norm is sufficiently small, then this equation Q, it admits at least three positive solutions. Next, we studied what happens when f is identically equal to 0. Just a second, yeah. So there is something still left. It could be that a need not be greater than equal to 1, or a need not be less than equal to. It could be in between also, right? It can oscillate also. Since that is still open. And now I'm considering, suppose this equation with f identically equal to 0. So you have just only this portion. Okay. Which one? Yes. So we have now a is now here we have just a is L positive and L infinity. I do not have any assumption on greater than or less than. Is L infinity and positive function, and infimum is some a naught, which is strictly positive, and asymptotically also it goes to a naught. Under that assumption, we have proved that this problem admits at least one positive solution, admits a positive solution. Next, we go to this, I think I have 10 minutes left. Okay. So next we go to the system of equation, this scalar field equation with the, so far we were discussing about the scalar equation, single equation. Now if you go to the system of equation, weakly coupled system of equation, scalar field equation. You see here, this is the scalar field system of equation, weakly coupled, because you see here U and V both are involved. And I have the assumption that here alpha plus beta strictly less than 2 star. So it's the subcritical case. Okay. So we are interested in studying the, again, existence and multiplicity for this equation. F and G are again dual space function. So F and G belong to the dual space of Hs. So that belongs to H minus S Rn. Okay, and so what should be the solution space? The solution space is the Hilbert space, natural solution space, the Hilbert space HSRN times HSRN. So this is the Cartesian product of HSRN times HSRN, and we have the inner product, which is the, you take that pairwise inner product. So the inner product is defined in this way. You take inner product of U and phi and plus inner product of V and psi. And you have the corresponding norm in HSRN times HSRN, okay? And what do we mean by the solution, weak solution? So this is, so UV in HSRN times HSRN is said to be a solution. Just a second, please. So we said that a couple UV in HSRN times HSRN is a solution for this system of equation if U and V are positive, because we are positive, we have here, that is why. And it satisfies this variational formulation for every phi psi couple in HSRN times HSRN. So this is the inner product between this, and this is the one. Okay. And the question is that where this system of equation arise, for example, like scalar field equation, it's a scalar field system of equation or Schrodinger system of equation, this kind of system of equation, where it arises or what is the application. For that, there are some application in biological and applications and physical application, for example, like in population dynamics and nuclear reactor. And in terms, here I mentioned some of the mathematical study of elliptic system, or Schrodinger, in particular Schrodinger system, because we are interested in the scalar field system of equation, Schrodinger system. So for S equal to 1 in the local case, I mentioned this some of the paper like Mitederi 1996, Alves, Moraes, Suoto in 2000, Lin Wei 2005, Witness Suple 2004, Reichel Zhu 2000. Some of those were for S equal to 1. Now, if you go to S is in 0, 1 in the non-local case system of equations, so there are not many papers, and where this kind of system of equation in the interspace Rn were studied. So most of the paper where where the system of equation for this Schrodinger scalar field system of equations were studied were for the Dirichlet problem in the bounded domain, for the Dirichlet boundary condition that outside it is the bounded domain. So some of them I just mentioned here. So one is my joint work with my collaborator Fuktai Wayne, which appeared in this year. So there we studied system of equation, Lane-Emden system of equation in the fractional case, fractional Lane-Emden system of equation, but in the bounded domain, as I said, with Dirichlet boundary condition. But we in measured data. So it's a Lane-Emden system of equation with measured data. Measured data is in the domain. Okay, so and we have proved existence and multiplicity of solution. We prove existence, multiplicity of two positive solution. Okay, what do I mean by positive solution for a system? I just meant that to each component, if you consider the couple UV, each component is positive. Also, there are some of the very good paper in this direction for the system of equation in the fractional case with the bounded domain, were studied as Chen Squasina 2016, Costa Miyagaki Squasina Young 2015, Faria Miyagaki Pereira Squasina 2016, Giacomoni Tuina Mukherjee Srina 2018, and so there where existence and multiplicity, such kind of problem are addressed for the bounded domain. For the non-local system of equation in the entire space Rn, we refer, there are, as I mentioned, there are very, very few. We refer Fisela, Pucci, Saldi 2017, Fisela, Pucci, Zhang 2019 to paper. So, so I just go back to the system again. Yeah, so we are interested in existence and multiplicity for this equation. So what we have proved is that, so it's a joint work with Patricia Pucci and my PhD student Shoptik Chakraborty. So we have proved that if F and G are non-negative, non-trivial functional in the dual space, so they are non-trivial, you cannot take identical as 0. F and G are non-negative, non-trivial functional in the dual space with the kernel are same. With kernel of F is same as kernel of G, and if they are in the dual space, their norm is small, sufficiently small, then that system admits a solution U bar V bar such that each component is positive. And also then the question is that how do we know that U bar is not equal to V bar? If U bar equal to V bar, then it will reduce to an equation again, right? So it's it will no longer be a system. So what we show that if F is not identically equal to G, or alpha is not identically equal to beta, at least one of them should be different. Either alpha is not equal to beta or F not identically equal to G. Then we show that U bar is not same as V bar. So it's actually, it's a system, two system. So we just prove the existence here. We couldn't prove the multiplicity. Multiplicity is yet an open problem, and we do not know how to, get the multiplicity of solution in the vectorial case. Also, as far as I know, the multiplicity for this problem, even in the local case is equal to 1, it's not yet known. so we are still trying. So that's all I want to say, and thank you.
Okay. Yeah. Thank you so much. Thank you. Is there any questions or comments? Okay, I have a question actually. You are considering on the right hand side that you have a special kind of nonlinearity, like mod u to the power p minus 1 into u, something like that. So my question is like, is there, I mean, what's the motivation behind that? I mean, is there any kind of physical phenomena
Do you mean
involved there? Yes, yes, yes.
Yeah. Okay. So for
Yes.
p greater than, if you take the critical or subcritical using Pohozaev, you can show that no existence of solution. So this one, if I can you see my screen?
Right. I can see. Yes, yes.
So for the critical or subcritical, this problem does not admit any solution, and that one can show by Pohozaev identity. So when it is subcritical, so this is this problem. I mean, and as I was saying, it's the scalar field equation, and it has, I mean, existence, and why people are interested in it, the uniqueness, existence. Like as I was showing that, I mean, the unique. First of all, it has a several connection with the, I mean, scalar field equation. It comes from actually Schrodinger equation and all. So if you go back to the those kind of equation, so the limiting problem will be this one. Also, if you consider the Partab equation with this epsilon parameter, you see that you come back to this case, this equation, this kind of equation, right? So so to understand the uniqueness, it's very important to know the existence uniqueness for the stability purpose. It's really important to know. So then we can, then one can study various other problems associated with that. That's one point of.
This particular form of nonlinearity is very important, I'm saying. Yeah.
Yes.
I mean, this particular form of, for instance, in place of u on the right hand side, if you have gradient nonlinearity, for instance, gradient of modulus gradient of u to the power from p minus to gradient of u, then is this?
Yeah. So
I mean, I don't.
So there are some works. Yes, there are some works. I can say that there are some work for the gradient nonlinearity. I think it's very new and very recent work. Some going on. I think I saw a couple of papers, recent paper. But I do not remember. It is on the left hand side, it is fractional Laplacian u plus u type of term or not, or is it just fractional Laplacian type u when the gradient nonlinearity was considering? But yes, you are right that with the gradient nonlinearity need not be polynomial, but okay, to start with some gradient nonlinearity and to study that equation, mathematically it is interesting. I do not know the physical context with this left hand side is this kind of fractional Laplacian plus u that is coming from this Schrodinger or scalar field thing. From physical point of view, the interpretation, whether it is interesting or does it have any physical interpretation, that first one needs to check. Mathematically, I can say that with gradient nonlinearity it will be interesting to check, but first one check that whether it has real motivation coming from physics or somewhere else. Then one, but I am not sure that. I have to check that one.
Thanks. Yeah, just one more thing, just for you. I mean, I'm a little bit curious about that. For instance, left hand side, I'm not talking about fractional Laplacian. Let's say s equal to 1. And instead of Laplacian, if you just replace by other kind of linear operator, for example, conductivity equation like divergence A, like divergence sigma gradient. Sigma is the conductivity of the medium. Do you think all the I mean, everything will work for that equation? For instance, exactly the same equation, like in place of Laplacian, you are just replacing a minus Laplacian by some linear operator with some coefficient involved inside. For
Yes,
example, divergent sigma get.
suppose you are thinking about, say, P Laplacian first non-degenerate or just this kind of.
P Laplace is still, it is difficult for the moment. Let's say Laplacian, I am just considering any linear elliptic operator in place of Laplace. I am just replacing Laplace by linear elliptic operator. And that operator involves some coefficients and all these things. Do you think everything should work like existence? And certainly that will depend on the coefficients and the regularity of that coefficients and so on. Yeah.
Well, existent may follow, but then the question is uniqueness. Uniqueness, and also you are talking about this in the local case, right? S equal to 1.
Yeah, for instance, S equal to 1.
Yeah, because the if you go to the non-local case, S equal to 1, as I was saying, uniqueness is a very big problem, and this that is why the CPM paper of Frank Lenzman Sylvester is the kind of Bible so far in this direction, which came in 2016, which is a remarkable work, and that's the only available kind of sort of technique in this direction. So, I mean, uniqueness, non-local, I do not know at all. I do not know, but the local case, uniqueness again will be a challenging one. There one can try with ODE thing, but it will work or not, I cannot just comment. One has to really work hard to see. About the existence, I think it can be shown, but the uniqueness and other analysis, it's nothing I can just straight away comment that it will work. One has to really see that it will work or not. But it will be nice to see if
Okay.
Yeah. Hello, this is Sudhakar Chaudhary.
Yes.
I have one just doubt. I don't know how much it is meaningful. The PD which we are considering is in Rn. So what about if we consider these type of PD in bounded domain? I mean,
well, this is, as I said, that the topic is scalar field equation. So scalar field equation and coming from physics point of view, right? And Schrodinger equation, scalar field equation, it's coming from there. So that is why it is the entire Rn, this equation. Okay, and if that is why it is always Rn, because this equation coming is entire space Rn. Now, if you just want to, just mathematically speaking, if you just want to know that suppose this equation, I mean, there exists a solution or not in the bounded domain, you can immediately, what you can try to do is that check with the Pohozaev identity. In the bounded domain, you do have a solution. I think that you it does not admit a solution in bounded domain. With the you can just try with Pohozaev type of argument, Pohozaev identity. So, and Rn here is why it is it's coming from physical context, as I was saying.
Okay, thank you.
Hello, Mosumidi, this is Indranil.
Yes, Indranil, say. Please.
Yeah, I mean, I have probably a stupid question, but okay,
no question is stupid. Come on, tell. Yeah.
Yeah, I mean, so far, what you are talking about this V, the potential is only constant. So, is it like the what is the current research? I mean, it is only for the constant potential.
No. There are coefficient with the coefficient function generally. I mean, with coefficient function and certain assumption on coefficient, there are also some studies there. You can find the literature. I mean, if you want, I can send also some literature. So here,
sorry, I cannot hear you properly. Can you repeat once more?
Yeah, so there are some results on I mean with the potential function V. So I think I can send you some of the papers with the potential function V.
Okay,
And some of the existence and other studies. So here I wanted to first put a simple case that to understand, since it was the expository type of talks, I wanted to keep it simple. So I just keep that everything constant type of, but there are some works where existence have been studied, existence, multiplicity, such kind of things have been studied with the potential function.
Okay, and and one more thing. So I was looking at the norm, which is like HS dot intersection with the C2S minus sigma.
Just 1 second, let me just go to this slide. This one you are talking?
No, before that, the multiplicity result.
Which multiplicity result?
where you have a difference of two u to the power p minus 1 u minus u to the power
Okay,
q minus 1 q. Yeah, this one. Yeah, sorry.
This should be this. I mean, we show the convergence in not only just HS space but also in space.
Yeah, and this is okay. So this norm is equipped with the HS norm, or it is equipped with the C2S minus sigma?
No, it is equipped only with HS norm.
HS norm. Okay, then.
But if you have the more, I mean, if you have the convergence in the Hilbert norm also, that's much better, no?
Yeah, right. I mean that. Okay, yeah, okay. It's only on the HS norm. Okay.
HS norm, only HS norm. The way we define the variational solutions, only in HS. But solution is also class. I mean, here we showed that any positive solution is actually a classical solution.
Yeah, but with C2S minus sigma, you cannot get a classical solution. Yeah. Okay. All right. Thank you very much. It's nice talk.
Thank you.
Hello, ma'am. I am Nivedita. I have a question. Ma'am, there we take a restriction on P, that is 1 less than P less than N plus 2S divided by N minus something. Why we need?
Just a second.
In the letter? Yes, ma'am. Yes, here. And the restriction of P, that is less than N plus 2S and N minus 2S. Why we need that?
This is the subcritical case I'm talking about, because if you take P bigger than that, the solution does not exist. You can try to show that using Poset kind of argument, that Poset type of identity. So try to suppose you assume that it has a positive solution and try to get a contradiction using Poset type of argument, which is called Poset identity or non-existence result. So you can try to show that that does not admit any positive solution. If solution exists, it will be identically 0.
Okay, that is trivial solution.
Yeah.
Thank you, ma'am.
Yeah, any more questions? Yeah, if not, then we can thank the speaker. Yeah, thank you so much. Thank you, Sunidhi. Yeah.
Thank you very much also.
So we will meet at 3 o'clock. Yeah.
Dr. Abhishek, you can share your screen. Are you here, Dr. Abhishek?
Yes, I can see him. Let's see.
Just a minute before, he replied me in a private chat that he's all ready for the presentation. I reminded him of his talk.
Okay.
Okay.
Yeah, now he's speaking, I guess.
Yeah, you can share your slides, Dr. Abhishek.
Well, no. Hello.
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 Yes,
Yes.
we can hear you. Yeah.
And is my screen also visible?
No, not yet.
Okay.
Maybe you can start your video.
Yeah, now?
Yes, now it's visible.
So my screen is visible now.
Yes.
Okay.
So you may start your video if you like.
Yeah.
Hi, Abhishek. Yeah, can you share your slides?
Hello.
Yes, it's visible.
Yeah.
Yes.
Okay. So can you see my screen now? And
yes.
Me
Yeah,
too?
yeah. Now it's fine.
Okay.
Yeah. Okay, so our next speaker is Dr. Abhishek Sarkar from IIT Jodhpur. He will be talking about freedom alternative type results for quasi-linear operators. Please continue.
Yeah. Okay. So I would like to begin with by thanking the organizers for their effort. So let me start with the talk itself. So I have chosen the talk like the topic which is quite familiar topic with many analysts for PDE or the analyst also, the freedom alternative type results. So we all know the freedom alternative results for the linear operators. So let me begin with the classical freedom alternative type results. So which says that we are given a non-trivial operator, which is linear, symmetric, and compact operator acting on a Hilbert space H. Then we can conclude two things. One is that if lambda is not an eigenvalue of the operator T, then the equation lambda u minus tu equals to f has a unique solution for any f belongs to the Hilbert space. And the second one is if lambda is not an eigenvalue of the linear operator T, then the equation lambda u minus tu, sorry, this is a small u, equals to f has a solution if and only if the inner product fu is 0. That is
Can I interrupt for a second? Did you start your video, by the way?
Yeah, I did once. Just a moment. Okay.
Your camera.
So now,
I mean.
yeah. So now can we?
Now we can see.
Yeah. Okay.
Okay. Perfect.
Okay.
Thank you.
So welcome. So the second one is that if lambda is not an eigenvalue of the operator t, then the equation lambda u minus t with small u equals to f has a solution. The necessary and sufficient condition being the f shall be orthogonal to the all the eigenvectors u of t corresponding to the eigenvalue lambda. So for our actually this condition is a little bit stronger condition, but the weak condition is that you can take it the operator on the Banach space and you can drop the symmetric as well. But the compact and linear is essential. But we have taken because of for our setup, because we want to discuss the this applicability for the elliptic operators and Laplace operators precisely. So let us begin with the linear case and also for the ODE case. So first, the simple example is that for the classical Freedom alternative is consider this equation minus u double prime equals to lambda u plus fx, and x belongs to the open interval 0 to 1. And we take the underlying space H equals to L2I with the Dirichlet boundary condition, that is U0 and U1 equals to 0. And then what conclusions we can give by the Freedom alternative theorem is that, so as we mentioned in the Freedom alternative theorem, if we change the lambda to be lambda 1, in that case, we can have the solution if and only if the orthogonal condition is satisfied with the corresponding eigenfunction. That is, in this case, if we take, so in this case, if we take this, so in this case, if we take, so this lambda 1 is the first eigenvalue. So in that case, corresponding to this eigenfunction, that is phi1, we have the L2 orthogonality condition, that is integral over I f phi1 dx equals to 0. So if this condition is satisfied, then we know that this equation will have a solution corresponding to this this first eigenvalue. So this is the first case of this Freedom alternative type Freedom alternative results for the ODE case. So what can we expect from the quasi-linear operators, so that up to some extent these conditions will be satisfied, or they will be behaving completely different from the linear case. So let us see what happens in the case of the quasi-linear operator. So to begin with, we will first of all now we are not in a linear ODE setup as well. So now the system got changed into this. So we take H belongs to the L infinity 0 to pi p, and pi p we have defined here. So for this kind of H bounded in 0 to pi p, we are considering this ODE, that is mod u to the power mod u prime to the power p minus 2 u prime the whole prime plus p minus 1, this whole equation with the Dirichlet boundary condition. So what is the speciality of this equation? Actually, this is a general case, like extension of the linear case, because if we take p equals to 2, that obviously replicates this case. So for p equals to 2, it becomes this case. And what is this actually? So this p minus 1 is actually the so this p minus 1 is nothing but u prime prime plus lambda u p minus 2u equals to 0. So for this kind of eigenvalue problem with the Dirichlet boundary condition, so the first eigenvalue is actually p minus 1 for this kind of ODE. And I would like to also mention that this kind of PDE is this kind of ODE are also called the half linear, because you can, from these solutions, you cannot expect the solutions will be linear, because suppose for this equation, if you get two solutions u and v, you cannot expect any longer that u plus v will also be a solution. But one thing is for sure, that the homogeneity condition will be intact. So if u is a solution, tu will also be the solution. So that is why these kind of equations are called half linear, not the linear anymore. So for those kind of ODE, and this lambda 1 is the first eigenvalue that we already mentioned, with the right hand side equals to 0. So in this case, as we have already seen, that the solvability of, in the case of p equals to 2, that is the linear case, a standard, like the if and only if condition for the solvability is that right hand side will be perpendicular to the given function h. That is ht sin t integration from 0 to pi will be equals to 0. Because if you take pi equals to 2, it will give you the only pi. So p equals to 2 is nothing but this. So for p equals to 2, it is already okay. So now let us see what happens for the general p. That is, we are mainly interested for 1 less than p less than like 1 less p for any p greater than 1 actually. So for those kind of for this kind of this kind of ODE, if you take h equivalently 0, then for this eigenvalue problem, you are only dealing with that eigenfunction will be like ut equals to sine pt, the non-trivial positive solution of the 1D for lambda equals to lambda 1 p minus 1. And we will also like to normalize in a way such that u prime 0 will be equals to 1. Then the function sine pt is the first eigenfunction with respect to the eigenvalue, the p minus 1 that you already mentioned. And actually what happens that for p, so this kind of function ut, this will also satisfy the what we expect for the, in a such a way we are normalizing u prime 0 equals to 1 such that you can also expect this kind of behavior, because that is obvious for the case p equals to 2. It is sine function and the cosine function square. So that gives you 1. So there will also be the same situation for the general p also. So that is quite an interesting generalized sine and cosine functions. So, and also this lambda 1 is actually a simple eigenvalue. By the simple eigenvalue, we mean that if you can have any other eigenvalues, eigenfunctions, that is, say you are already got lambda 1 phi 1. If you got any phi 2 other than phi 1, it will be like c into phi 1. So that is the constant multiple of phi 1. And that is what we meant by the simplicity. So these results are, so in this generalized sine p cos p functions are captured in this result, and also for the freedom alternative type results in this paper they have mentioned. So the question is there any role of this orthogonal condition in the case of general p greater than 1? So that the question is, what is the role, if any, of the corresponding analog of the Freedom alternative type result for the linear case, if it holds also for the nonlinear case, that is 0 to pi p ht sine pt dt is equals to 0. That remember, that is the So now we will state some results for the Freedom alternative type results for the p Laplace operator. And the p Laplace operator, by the definition, it is a, like if you categorize, it is a quasi-linear operator. So we will just like to mention the few articles, the one article first, which is written by Binding et al. In the Proceedings of AMS, that they construct an example which shows that the Freedom alternative type is not necessary for existence of solutions. But although they did not take this kind of U02 and pi p, this kind of condition, so they took in their paper, they started with something U1 or 01 like that. But that doesn't matter. You can normalize it always. For the nice boundary conditions, you can only take this. Otherwise, any real numbers is okay. So the first case is the first article, which we see that it states that is not a necessary condition. But what about the sufficient condition? So in their paper, Del Pino et al. In the JDE 99, they shown that the condition that Freedom alternative type linear in nature, that is 0 to pi p ht sine pt equals to 0. So this condition for any p greater than 1 is actually a sufficient condition for the existence of solution. So we have already seen that, like the results, that it may not be the necessary and sufficient, but it is not necessary but sufficient condition for the existence of solution. And you can also expect some multiplicity of solutions as well. So in their paper, explicitly they proved that the set of H for which that the one-dimensional case has non-empty solutions, such that at the lambda equals to lambda 1 has at least two solutions, ht sine pt dt is not equals to 0. So what the important part is, this you can get multiple solutions even without the orthogonal condition. That is, it is non-zero, but you are getting the existence of two solutions. So the idea of the proof is like the normal ODE techniques, and so the one of the important tool is that classical suiting arguments. So let us get into the Freedom alternative for higher dimensions. Okay, so I have 5 more minutes. Okay, so let us discuss about the Freedom alternative for the higher dimensions, that is p Laplace operator. Actually, the p Laplace operator, if you convert it for the radial solutions, it will convert it into the ODEs of the form of the 1D, which we wrote earlier. So in this case, omega is a bounded domain in Rn, and Laplacian U is defined by divergence of this quantity for p greater than 1. So first of all, for any kind of Freedom alternative type results, first you must have the sufficient information about the eigenvalue problem. So the lambda 1 is the first eigenvalue. So lambda 1 is related to, if you take h equals to 0. So lambda 1 can be characterized as the LP based constant C in the LP Poincare inequality. So depending on, so either you can write C here, in that case lambda 1 will be 1 by C, and since I am writing in this side, so C equals to lambda as the base constant. So depending on which side you are putting the constant, so the lambda 1 can be characterized as the base constant in the Poincare, LP Poincare inequality. And also for the eigenfunction, we will have that this inequality will be equals to 0 if you take u to be the eigenfunction corresponding to the lambda 1. So these results are well mentioned in the paper of Lindqvist in the proceedings of AMS, that the first eigenfunction is simple, it is positive and also isolated, and the phi1 is positive in omega, and also the normal derivative on omega del on the boundary is also positive. And also the Holder regularity up to C1 alpha is also mentioned in that article. So for p equals to 2, if lambda is not an eigenvalue problem, that we already know, for any arbitrary h in the right hand side, we can have a solution. So for the general case p greater than 1, and so for p greater than 1, for lambda not equals less than equals to 0, the monotonicity argument for any h, we can prove the unique solution for the lambda greater than equals to 0. So lambda for this case, say this is the lambda. So for all these cases, the solutions are there. So the only remaining part is, so if this is lambda 1, so for 0 to lambda 1, for p greater than 2 and lambda belongs to 0 to del 1 and 0 to the first eigenvalue, del Pino proved the existence of the multiple solutions, and also like the sufficient condition and necessary condition, how it fails. For 1 less than p less than 2 case and between lambda to 0 to lambda 1, Fleckinger et al. Proved this result condition. So the approach combines the variational methods, topological arguments, and also the lower and upper solutions. And to mention that these lower and upper solutions may not be the ordered one, but still they proved some results without the non-ordered lower and upper solutions. And the most importantly, they shown that the freedom alternative type condition is not necessary for the existence of multiple solutions is also shown. So can I have 2-3 more minutes, or shall I stop here? So I can stop. Hello.
Yes.
Okay.
I was sick. Yeah, you can stop. Actually, your time is out. Yeah.
Okay, so
maybe
okay, I'll stop here.
Yeah. So, is there any questions or comments?
So there is a question in the chat, probably you can take that.
Okay.
Yeah, you can. Yeah.
So for the trace class, actually for the trace, it will be delicate issues depending on the linear or the non-linear. So for the trace class, I don't know, because for the trace class, then it will also come to this fractional Laplace situation also. So for those cases, I don't know anything about it. Maybe fractional people also can highlight here, maybe if they're around. So it depends on the trace class with the fractional situations. So I have not come across to these classes. So
yeah. Okay. Yeah. So we can stop here maybe. Thanks, Abhishek, for this nice talk. Yeah, we can start. Yeah, we can continue with our next speaker. Yeah, thank you so much.
Yeah, welcome.
Yeah, Dr. Sudhakar, are you here?
Yes, I'm here.
Yeah. So let me make you co-host. Yeah, you can share your screen now.
Okay. So is it visible now?
Yeah.
Yeah, it's okay. Yeah. Okay, so we have here Dr. Sudhakar Chaudhary from. Hello. Yeah.
Yes. Yeah.
Yes. So we have Dr. Sudhakar Chaudhary from the Department of Mathematics, Institute of Infrastructure, Technology Research and Management, Ahmedabad, Gujarat. And he will be talking about this finite element method for parabolic non-local problems. Yeah, please continue.
Thank you for your kind introduction. Basically, in this talk, I will discuss about the numerical solution of parabolic non-local problems. What I mean by non-local problems, I think in our previous lectures already we have, heard about this term, non-local problem. So I will again, discuss about some special type of non-local problems and how to find their numerical solution. This is our main talk, basically task here. So this is the outline of my presentation. First is introduction, and here we describe about our non-local problem and what are the applications and what are the difficulties when we go to solve these type of problem numerically. Then we consider the weak formulation of our given problem. Then we go for semi-discrete and fully discrete formulation of the given problem. And here we also derive the a priori bound and a priori error estimate for the semi-discrete and fully discrete solutions. Finally, we will confirm our theoretical estimates via one numerical experiment. So, well, first of all, I would like to discuss what is the difference between if we take simple partial differential equation and if we take a non-local partial differential equation. We know that if we consider a partial differential equation, here basically we have a relationship between the dependent variable and its derivative. So in order to if we say that this partial differential equation holds a point, it means that we require value of the dependent variable in the neighborhood of that point. However, if we consider this non-local partial differential equation, it is completely opposite. If we say that a non-local partial differential equation holds at a point, this means that we also require value of the function, that is information in whole domain omega, whatever domain, in which domain we are considering our differential equation. The non-local partial differential equation which I am considering here, which that is given in equation number 1. And here the diffusion coefficient, we can see this diffusion coefficient m of L of u. This has basically two possibilities. L of u, either it can have like integral u dx, or it can be like integral mod grad u square dx. So because of presence of this term in this differential equation, this is no more a pointwise identity. That is why we call this equation as a non-local partial differential equation. So we know that getting analytical solution of these type of problems is difficult task. Therefore, we need to consider some numerical technique for solving these type of partial differential equation. So the numerical technique which I will be considering here is finite element method. Here I would like to mention what are the why in particular I have considered this well-known method for solving this parabolic non-local problem. Basically, once we use this finite element method for solving this non-local problem together with the Newton iteration, the Jacobian matrix which we will get, that will not be a sparse matrix. That will be a dense matrix, and that will be computationally expensive. So also here we will tell what are the, how to overcome this difficulty. Is there any way to get a sparse matrix after applying the Newton's method into this parabolic non-local problem? So that these actually issues I will discuss in my coming slides. So such type of equation basically appears in many real world phenomena. For example, this U could represent the density of the population of bacteria subjected to the spreading. Like that, there can be several applications. So now we will come to the weak formulation of given problem. Why we consider here the weak formulation of original PD? Because the steps in finite element method are as follows. First step is basically the weak formulation. So if I want to get the weak formulation of problem 1, we need to take a test function V in the Sobolev space at 0, 1 omega. This Sobolev space V consists of all square integrable function whose distributional derivative also belongs to L2 omega and V equal to 0 in the sense of trace on the boundary. So if we take that test function V and multiply our original equation 1 and then integrate by part, then we can land up into equation number 2. So this is our weak formulation. Before going into the finite dimensional setting, first of all, I would like to ensure about the well-posedness of this problem 2. For the well-posedness of this problem 2, we require certain assumptions on given data. So the first assumption is here given in H1, that is our initial data U0 is in H01 and F is in L2. That means if we fix a time t, then this ft will go to L2 omega. Second assumption is m is bounded and it is positive also, strictly positive. We can see here positive, and also m is ellipsis continuous. So with these assumptions, basically we can show that there will exist a unique solution for this problem 2. Of course, from this we also can show that that there will exist a strong solution, and that will be also unique. And the method which we will use for solving the existence, for showing the existence and uniqueness, that is nothing but Galerkin method and compactness arguments. So now I will come to the finite dimensional setting, and here we discretize our space variable. So suppose we have a domain, in space we have a domain that is kind of a square domain. So what we will do here in semi-discrete formulation, we will actually divide our square domain into small triangles. So in each triangles, we have local degrees of freedom, and overall, if we consider this complete square, we will have global degrees of freedom. So corresponding to each global degree of freedom, we will construct linear hat basis functions. So how this VH finite dimensional space is constructed here? VH consists of all piecewise linear polynomials on each triangle, which will vanish on the boundary of the whole domain omega. That is how this space VH is constructed. So, so the semi-discrete formulation we will define with help of this space VH. Semi-discrete formulation is to find discrete solution UH in VH such that equation 4 hold. Now next we want to show that this semi-discrete solution is bounded. Also, because we have discretized our space, so that means we have incorporated certain error in our problem. So how much error is being introduced, that is also I want to discuss here. So in this a priori estimate, what I have shown that if F is in L2 omega and UH naught is in L2 omega, then we have shown that this semi-discrete solution UH is bounded in L2 norm. Also, it is bounded in H01 norm. That is what we have shown in equation number 5. Now, in order to derive the a priori error estimate for this semi-discrete solution, we will be required this projection operator. This projection operator is defined here in equation number 6. This is known as the Riesz projection operator. And with the help of this Riesz projection operator, basically we have splitted our error U minus UH into two parts. That is rho and theta. So this rho is nothing but projection error, and theta is nothing but it is the discretization error. For the projection error, already we have estimates available in the literature, and they are given. Basically, these estimates are given in equation number 8. and references we have I have given here. So if we want to derive the a priori error estimate, I mean estimate E, then that means we just have to derive estimate for theta, because for estimates for rho are already available in the literature. So in the next slide, I will derive the estimate for theta. I will not give the complete derivation, just I will sketch the proof, that's all. So here, this is the statement of my theorem for the semi-discrete, for the error estimate for the semi-discrete solution. What here we have shown that if U is the solution corresponding to the weak formulation and UH is the solution corresponding to the semi-discrete formulation, then this error estimate which are given in 9 hold basically. So what it says that error in L2 norm, it is nothing but of order 2, and error in H1 norm, it is nothing but of order 1. So as I said, if we want to derive the error estimate, just we need to derive the estimate for theta. So we can show that the theta will satisfy this this equation, whatever I have written, this one. How to show that theta will satisfy this equation? This we can show just by taking the semi-discrete formulation and original weak formulation. From those two equations, we can derive basically this equation for theta. Now in this equation, we will apply Cauchy-Schwarz inequality, Poincare inequality, and also we use the property of our non-local term. Then we can land up into equation number basically 11. We can land up to equation number 11. And further, if we simplify this one, we can land up to equation number 13. So in this equation 13, we can see that the right hand side contains norm rho square plus norm rho s square. Already I told that this projection error is known to us. So we can use that projection error that is given in equation number 14. And finally, we can obtain the estimate for this theta in L2 norm. So L2 norm we have derived, it is of order 2. So ultimately, we wanted to derive estimate for this norm of U minus UH in L2 norm. So this we can write it as, this will be less or equal to norm rho plus norm theta. And norm rho already we can see here, it is given in equation number 8. So norm rho we can use from there, and norm theta we have derived here in equation number 15. And we can add them up to get this estimate, which is given in equation number 9, that is estimate in L2 norm. Similarly, we can derive error estimate in H1 norm also, that will be of order 1. So till now we have discretized only the space variable, that is why we called it as a semi-discrete formulation. Now we discretize the space and time variable both, and we say it is a fully discrete formulation. So for discretizing the time variable, we use basically here backward Euler scheme. So this time interval 0t is divided into equal number of subintervals. That is, and each interval is having this length delta t, that is nothing but capital T by j. So with help of these notation, if U capital UN here, if this capital UN represents the approximation of this semi-discrete solution UH at time t equal to Tn, then if we apply the backward Euler scheme into our semi-discrete formulation, then we get this fully discrete formulation that is given in equation number 16. So fully discrete formulation is nothing to find here is nothing but it is to find capital UN in VH such that equation 16 holds. So now, as I said in the beginning, that if we, because it is a non-linear equation, so in order to solve this non-linear equation, first of all, we have to linearize it. So for linearization, we can use either Picard method or Newton method. Newton method has advantage over Picard method in the sense of rate of convergence. But if we use Newton method for solving this equation 16 together with finite element method, then what will happen? The Jacobian matrix which we will get, that will not be a sparse matrix. To see this, what we do, we again reformulate, we again reconsider this equation number 16 that is given in equation number 17. And now I will apply this Newton's method. So how we will apply here Newton's method? This solution UN, I will write it as, it is nothing but sum of it is nothing but sum of U naught tilde plus WHN. U naught tilde is nothing but initial guess for the Newton iteration, and WHN is nothing but the correction term at nth iteration. So because UN I have considered here, so this UN I will substitute in this equation number 17, and then what we will get, that we will see in the next slide. Then finally we will land up with this equation number 18. So in this equation 18, we can see that this right hand side, this is nothing but the term corresponding to the this is the equation corresponding to the correction term, that is WHN. And corresponding to this correction term WHN, the Galerkin matrix which we will get after using finite element method, that is nothing but it is given in equation number 19. And the right hand side term which we will get, that is nothing that will be corresponding to this one. So now here I want to show that this Gij is not a sparse matrix. What I mean to say, what I mean by here is sparse matrix, a matrix which is having maximum basically 0 elements. If a matrix, if it is having maximum 0 elements, if elements are most of the elements are 0, then we will say this matrix as a sparse matrix. So this corresponding to this term phi phi j. What are these phi and phi j? Phi and phi j are the basis function, linear head basis functions. They have compact support. And here I and j is varying from 1 to n. So this phi phi j will give us a n cross n matrix. This will give us a n cross n matrix, but that matrix will be sparse. However, if we go into the second term corresponding to this one, integral over omega phi separately, and this inner product gradient u naught tilde into gradient of phi j, if we calculate this term, this second term, this will not give us a sparse matrix. Because of this term, basically sparsity of this G matrix is lost. So what will happen if I want to calculate this alpha from this equation G alpha is equal to R, then what we have to do, we have to get the inverse of this G matrix. And if G is a full matrix, then calculation of inverse of G will be computationally expensive. And this we want to avoid here. So how to avoid this difficulty? In order to avoid this difficulty, basically we will reformulate our original fully discrete formulation and then apply the Newton's method. So how we are reformulating? We are introducing here a new variable that is nothing here, that is D. And D I have written here, D is equal to integral u and dx. With help of this new variable, basically our fully discrete formulation can be written by equation number 21 and 22. Now in this equation 21 and 22, if we apply this Newton's method, then what? Then the Jacobian matrix which we will get will be of this form, that is given in equation number basically 24. This is here in J2. This is the Jacobian matrix which we will get when we apply Newton's method into our reformulated problem. So now I want to show that this matrix J2 is basically a sparse matrix. How it is a sparse matrix? So what are the entries of this J2 matrix? A, B, C, and delta 1, 1, where A is given here, and B is given here, C is given here, and delta is given here. So from the entries of matrix A, that is AJL, they are of this form, phi L, phi j, and grade phi L into grade phi j. Because phi L and phi j, they have compact support. So the matrix which we will get from this, these type of terms, that will be a sparse matrix. And obviously these Bj1, C1, C1L, and delta 1, 1, they are just a scalar, or they are the row or column vectors. So that is how we have shown that theoretically that this matrix J2 is a sparse matrix. So mainly what here I have shown that this A matrix is a sparse matrix, and hence J2 will be the sparse matrix. This also we will see in our numerical experiment. So as we have derived the a priori estimate and a priori error estimate for the semi-discrete formulation, same we will do also in case of fully discrete formulation. So the a priori estimate in fully discrete formulation, they are given in equation number 27. So in L2, in this equation 27, what we have shown that our fully discrete solution is bounded in L2 norm, and also it is bounded in basically H01 norm or in H1 norm, we can say, from this equation number 27. And about the a priori error estimate for the fully discrete solution, we have here this equation number 28. What it says that the fully discrete solution satisfies the estimate of this type. What is the meaning? That error in L2 norm in space variable is of order 2, and in time variable it is of order 1. And also error in H1 norm in space variable, it is of order 1. That is the second term. So this we will confirm numerically also. Means what I will show here, I will show that error in L2 norm is of order 2 and error in H1 norm is of order 1. This is what basically we will show here numerically. So so for our numerical experiment, we have basically considered example where we know the exact solution, that is sufficiently smooth solution U. It is nothing but given here. With help of this exact solution U, we have calculated the right hand side F, and based on that right hand side F, we have used the finite element method for calculating the numerical solution. The domain, spatial domain, is taken to be square 0, 1, and the final time t at which we have calculated our numerical solution is t equal to 1. Also, the step size in time variable is taken to be 0.001, and tolerance for stopping the Newton's iteration is taken to be 10 to the power minus 15. The initial guess for Newton iteration is taken like 1 at the interior node and 0 at the boundary node. With these information, we have used finite element method and have obtained the following errors in L2 and H1 norms. So we can see that error in L2 norm is of order 2 and error in H1 norm is that is converging, that is convergence is of order basically 1 in case of H1 norm. Also, now I want to show the sparsity figure here. So if we use our Newton's method directly into our fully discrete formulation with finite element method, then the sparsity, we can show that sparsity will be like this. And that is, we can say this NZ represent here the number of non-zero elements in our Jacobian matrix. And if we basically reformulate our system and then apply the Newton's method, then sparsity can be shown by this figure. So we can say see that this one is sparse, however this one is dense, and hence it will be computationally expensive. So here I want to mention some possible extension also to this problem. Like here I have taken simple non-local parabolic partial differential equation. So here we can consider here in place of Laplacian term, we can have here P Laplacian term also, and even variable exponent problem also, Px Laplacian problem. So I mean those will be highly non-linear, and I mean that will require that may not be easy, but yes, I mean those also can be solved by using same technique. Yeah, thank you. So
yeah, thank you so much. Thanks, Sudhakar. Is there any questions?
Yes.
Yes.
You mentioned sparse matrices. Now, are you aware of Nikhil Srivastava's work on sparse matrices? He did his PhD under Spielman, and Marcus, Spielman, and Srivastava solved Cardassian-Singer problem and got a lot of recognition and many prizes. Sparse matrices by Nikhil Srivastava.
Sorry, madam, but I mean, I did not.
Yeah, I'm just telling you. I'm telling you. It is
Okay,
not related to your work, but it is work on sparse matrices, and you are using them a lot, as I saw.
Yes.
Okay, so you might find some good results there to use. Okay?
Sure, madam. Sure.
Okay.
Yeah.
All the best.
Thank you.
Yeah, thanks, ma'am, for this nice comment. Yeah, so is there any more question? Yeah, if not, then let's thanks the speaker, and we
Yeah.
will continue at 4 o'clock. Yeah.
Yeah. Thank you.
Yeah.
Dr. Sudhakar, can you please unshare your screen?
Uh,
Yeah, thank you.
Okay, so welcome to everyone to this last session of this analysis PD's symposium, and we have our speaker, Dr. Pradeep Kumar Sharma from the Department of Mathematics, Aligarh Muslim University, and he will be talking about set order relations and set valued optimization. Yeah, please continue.
Okay, thank you very much. First of all, thank you very much for the organizers for organizing such a nice conference and giving me opportunity to present my work. Basically, my talk is based on the optimization problems with set valued maps and the techniques to solve optimization problems based on the comparisons of the values of the objective function, which uses the set order relations. So before starting my talk, first I will recall some basic notions which will used throughout the presentation. By Py, we denote the collection of all non-empty subset of Y, and for any two non-empty subset A and B of the topological vector space Y, the sum of A and B is defined as the collection of sum of elements of set A and elements of set B. In the given figure, we can see that the green picture represents the set A and the red picture represents the set B. And we can see that the teal colored figure represents the set A plus B. Further, A subset C of a vector space Y is said to be a cone if for all elements of C and non-negative lambda, we have lambda Y is in C. Basically, the lambda Y is the ray originating from the origin. And every ray originating from the origin will be in the C. So we will say that C will be a cone. In the figure, we can see that the cyan colored figure represents the cone C, and the cone C is said to be a convex cone if for all elements x and y of C and all non-negative scalars lambda and mu, lambda x plus mu y is in C. That is, the C should be convex and a cone. Then we will say that C is a convex cone. And the cone is said to be pointed if for any non-zero vector x is in C, then we have the negative of that vector should not be in C. That is, intersection of the cone C with its negative should have only 0 element. The cyan colored figure also represents that this cone is pointed, because if we took the negative of this cone, then the intersection of this cone C and its negative will have only 0 elements in common. And every convex cone always induces a pre-order on Y in such a way that X is related to Y by the ordering induced by a convex cone if and only if the difference of Y and X should be in C for every element of X and Y in Y. And the cone C is said to be, if the cone C is pointed, then this ordering will be a partial ordering on Y, and this play a crucial role to studying the vector optimization and also in set optimization. Now we are ready to formulate the set valued optimization problem. For a set valued map defined on a non-empty subset of a real vector space to a real topological vector space with non-empty values, the optimization problem with set valued maps is to minimize the objective function f over the feasible set S. Now the important question is that what is the meaning of the minimum in the formulation of set valued optimization problem. Note that objective function is a set valued. So how will we define the minimum in sense of sets? That is, how will we compare two sets? So before defining the meaning of this minimum, we consider an application of scalar optimization problem, vector valued optimization problem, and set optimization problem, because set valued map contains the single valued maps and scalar valued map, vector valued map. So basically set valued optimization is a generalization of scalar valued optimization problem and vector valued optimization problem. The detailed studies on vector optimization and set valued optimization can be found in the books uh, uh, given on the screen. So now let us distinguish the case of scalar optimization problem, vector optimization problem, and set optimization problem. Suppose that we are interested in finding out the fastest bowler from a set of cricket players. Then this is the case of scalar optimization problem, where the objective function gives the speed of a player. Basically, if we want to find the fastest bowler, then we have to we have to find the maximum. We will choose a person who has the maximum speed. So this case is of the maximization problem. Further, suppose we want to find a bowler from a set of cricket player in such a way that the bowler has several qualities, namely speed, stamina, in-swing, out-swing, and so on. Then we can see that a player is a vector whose coordinate are speed, in-swing, out-swing, stamina, and so on. So the value of the objective function is a vector. So this will be the case of vector optimization problem. Now, if we consider the objective function in such a way that the values of the objective functions are teams, and assume that teams is a set of players and each player is a vector whose coordinate consists of one's ability, stamina, speed, in-swing, out-swing, popularity, and many other properties. Then the problem of finding a good team from a set of teams or from a cricket league is a problem of can be modeled in a set valued optimization problems. Further, there are two types of optimal solutions of set valued optimization problem. First is the vector approach. In vector approach, one directly generalizes the concepts known from vector optimization to set optimization. Basically, in vector approach, solution concept depends on the only one element of the image set f of s. And there is another approach which is introduced by Kuroiwa in 1997 and play very crucial role to study set optimization problem. And this approach is based on the comparison among the values of the objective function, which is set valued map. Now, to define the meaning of the minimum, as said in the formulation of the set valued optimization problem, we need some kind of set order relation or some technique to compare two sets. So in 1997, Kuroiwa give many kinds of set order relations, but we mention here two types of set order relation because of the time. So we will say that A is related to B by lower setless order relation if and only if B is a subset of A plus C, where A plus C is a cone generated by the set A. The meaning of the right hand side inequality is containment is that for every B in B, there exists a in A such that A is related to B by the vector ordering induced by a cone C. And A is said to be related to B by upper set less order relation if and only if A is a subset of B minus C. The meaning of the right, there exists a B in B such that A is related to B by the ordering induced by a convex cone C. In the left hand side figure, we can see that the orange colored figure represents the set A and the red colored figure represents set B. And we can see that if we C is the positive orthant in R square, then we can see that B is a subset of A plus C. And similarly, in the right hand side figure, we can see that A is a subset of B minus C. So in the left hand side figure, A and B are related by the lower set less order relation, and in the figure right hand side figure, A and B are related by the upper set less order relation. It is important to note that lower set less order relation and upper set less order relation are pre-order, that is reflexive and transitive order relation, but they are not partial order relation. Now we can define the solution concept of set optimization problem. That is, we can define the meaning of the minimum in the formulation of the optimization problem with set valued objective function. So first definition is based on the vector approach. So any element of the set S is said to be a minimal solution of the set valued optimization problem if P can find any element y bar in the image set of x bar such that y bar is a minimal element of the image set f of S. That is intersection of the image set f of S with the negative of the cone originating from the y bar is contained only single elements, and the set of minimal elements of the problem is denoted by minimal of f of S. It is important to note that we can see that in this definition, the minimal solution depends only on one element y bar of the image set of x bar. Now consider the second definition corresponding to the set order relation. An element x bar in S is said to be alpha minimal solution of the set optimization problem with respect to the set order relation if and only if fx is related to fx bar by some kind of set order relation for some element x in S, then this gives f of x bar is also related to f of x by some kind of set order relations. So now here we can see that we are comparing images, not based on any particular element of the image set of x and x bar. Consider a simple example to see the difference in both of the definition. If we consider a set S which contains the three elements 0, 1 and 2, and consider the image of the f set valued f, f of 0, f of 1 and f of 2, and consider the cone is the positive orthant in R, then we can see that x bar equals to 2 is a minimal solution of the set valued optimization problem by vector approach, that is by the definition 1. But we can see that image of f0 is better than f of image of f at 1 and image of f at 2. That is f0 is related to lower set less order relations by f1 and f2. So we can see that in vector approach the 2 is a minimal solution, but according to the set approach 0 is the minimal solution. So the optimal solution considered by the set approach is better than the solution concept considered by the vector approach. Now consider two examples which shows that the solution sets obtained by vector approach and the set approach are both different. If we consider
Hello, Pradeep.
Yes.
Yeah, we don't have enough time actually. You are out of time,
Okay.
so maybe you can speak in a minute.
Okay,
Yeah.
okay. So in both of the example, we can see that the solution of set valued optimization problem by vector approach is empty, but by upper set less order relation is -1. And in the example second, we can see that solution set with vector approach is semi-closed interval 0, 1, and the solution set with upper set lesser order relation is singleton. And then we can say that both solution concept by both approach are different. Now we give the solution.
Yeah, I think we should. Hi. Pradeep,
Yeah.
I'm sorry. Yeah,
Yeah.
I think we are out of time. Basically, I should continue with next speaker because it's already 10 minutes. You spoke already 10 minutes. So and it's already
Okay.
15 minutes. So
Okay, I
yeah,
am sorry
I should.
for
Yeah,
that.
no problem. And we don't have time to take the questions. So maybe we can continue with our next speaker.
Okay, okay.
Yeah. Thank you
As
so
you
much.
wish.
Thank you so much. Yes.
Okay, thank you, thank you.
Yeah. Yeah. So please, Abrojyoti, yeah, could you please share your
Okay.
screen? Yeah.
Hello.
Yes, I can
Yes,
see.
everyone can see that.
Yes, I think so.
Okay.
Okay, so
let's start. No.
Yeah. Our next speaker is Abrojyoti, sent from I hope
Niger,
Niger.
Bhubaneswar. Yeah.
Bhubaneswar.
Yes.
Yeah. So he will be talking about this solutions with concentration.
Okay, I'm saying.
Concentration.
Okay, my
For conservation laws with the discontinuous flux and its application to numerical schemes for hyperbolic
systems. Yes.
Yeah,
So
please
it's
continue.
so it's a joint work with AMR Sahu, A. Agarwal, and Ganesh Vaidya. So my outline of the talk is, so we first review some conservation law. What is the conservation law is discontinuous flux, and what are the existing notion of solutions in this regard, and what are the questions and difficulties, and how we overcome it. And the next two sections we will see what is how we are solving the problem. Okay, so first first thing is that what is the conservation law with discontinuous flux. So when ut plus f capital F x u x equal to 0 is called a conservation law, and f ux, as you can see that f of x u depending on x, and it is not continuous in the space variable. So where f ux can be written as f ux is written as hx into fu plus 1 minus hx into gu, where h is a Heaviside function and fg are C1 strictly convex function. So fg can be any Lipschitz functions also, but here we are taking it as much more regular. It is C1 and strictly convex, and u0 is any bounded measurable function. So as you can see from this definition of capital F, that it is in the right half plane. So in the right half plane we have ut plus small fux equal to 0, and in the left half plane we have ut plus gux equal to 0. So it is so this conservation law is not continuous along the interface x equal to 0. So we'll call x equal to 0 as in interface. So the existing notion of solution is by Adimurthy. So by Adimurthy et al. In I think it's in 2000. yeah, in 2000, he gave a Adimurti et al. Gave a lax Olenek type representation when f and g are in C1 and strictly convex with superlinear growth. By superlinear growth, we mean that limit mod u goes to infinity plus infinity. It is plus infinity, and fu by mod u is going to plus infinity. So obviously you can see that linear functions are not here. Linear functions is not strictly convex and not superlinear growth. And also a concept of AB entropy solution is given when flux function are convex. See here the difference is that in the first point I told that it is for strictly convex. Now the flux function are only convex, so linear functions are allowed here. We can consider it here. Okay. And the the other, so if either you have to both f and g are convex or both are concave, or one of if one of them is convex and another of is concave. And the most important point is to note here that f and g should have a minimum or maximum, and it is unique minimum and maximum. So the now the following questions one can ask: what happens when f is not strictly convex? As I said, that what happens when linear fluxes with this condition? With this condition is very important for us, because if you assume this condition on the flux function, I mean when f is f is decreasing and g is increasing on the whole real line, then it automatically avoids the superlinearity condition. Okay. So see, observe, and what happens when what is the existence and uniqueness of solution when for the fluxes that we call overcompressive flux pair. So what is overcompressive flux pair? We call that f and g are non-linear flux pair, which is C1 and strictly convex, and f dash is negative and g dash is positive. So that means that we have different monotonicity on f and g. So f dash in the right half plane, it is negative, and it so a slope of the so f dash is negative, and in the left half plane g dash is g dash is greater than 0. Okay, so as I already told, that if we have this condition, we lose the superlinearity condition, but still we can have a lax Olenek type representation that I will show in the next slides. Okay, so the difficulties is that when f dash is negative, f dash is negative in the right half plane. So the characteristic coming from the right half plane and the characteristic coming from the left half plane may intersect in the they may meet in the x equal to 0 line at the interface. So there may not exist a bounded solution for that. So that is one problem. So so obviously a measured valued solution, notion of measured valued solution has to be introduced there. And also when f dash g is less than f dash g is less than 0 and g dash g is greater than 0, we lose the AB connections also. So Adimurti et al. In 2 gave a notion of bounded solution by relaxing the RH condition, but that doesn't conserve mass. So always in conservation law, we want that solution conserves mass. Conserves mass means conserving mass means that integration of minus infinity to infinity u of x t dx, if that we call a mass mt. So m dash t should be 0. Okay, so that are the difficulties we have. So how we overcome it? We propose a solution containing delta shock at the interface. So we put a delta measure at x equal to 0. Okay, so it can be seen that if you have delta measure, then I mean obviously when for the Riemann type of data, it can be seen that earlier we had some missing mass, but if you put a delta wave there, it is the mass is now conserved. Okay, now we use the vanishing viscosity method for linear fluxes, because linear flux need to be treated separately. It is not superlinear and so on. And a Laxolanic type formula is given for non-linear over-compressive flux pair. Finally, a convergent numerical schemes are proposed to which captures delta shock well. Okay. So so that is the notion of that is the weak formulation of measured value solution. When so this part is bounded, u bar is bounded, and this wt is the weight of the delta measure, delta shock. So we say that this uxt is a solution of the conservation law of the discontinuous flux if this integral formulation holds for all phi with compact support, or smooth phi with compact support, and this u bar and wt is locally bounded. Okay. So then the vanishing viscosity approximation. So here we are considering the linear fluxes. So our FU is BU and GU equal to AU, as you can see here. FU is BU and GU is AU, and A is positive, B is negative. The idea is, so what is the idea? I will tell you this idea, what we are doing, what we are going to do. We restrict the equation in the two quarter planes, putting a boundary condition along along u of 0 t equal to beta t, and show a existence of not c1. I mean, I wrote c1, but sorry, it is not c1. Okay, so we at least differentiable in the x variable. So we want a differentiable differentiable in the x variable u epsilon, u epsilon in the right half plane, in the half plane for the viscous equation. For viscous equation, I mean that with this epsilon uxx 2. Okay, so then we are, in this case, in the linear case, we can explicitly compute beta t, and that is the main part of this proof, because to pass to the limit, for passing to the limit, we need a uniform bound on beta t. Beta t, if we get a uniform bound, by uniform bound I mean that it is, the bound is independent of epsilon. So if we can get a uniform bound in beta t, then we can pass to the limit. Okay. So the weak formulation for the viscous equation is this. Here ux is already involved. So we say that u is c1. C1 means it is at least differentiable. Sorry, it is c naught. Okay. Is a weak formulation of the above problem if satisfies the following integral identity for all p with compact support. Okay. So here you observe we want some differentiable u. Okay. So this is our first theorem here, that we have the explicit formula u1. U1 is the formula of the right half plane. Here you can see as x is positive, and u2 is the formula for the left half plane, it is negative. And here we calculated explicitly what is beta t. So in beta t we have some term like e half half. So we have some term like e half half. So e half half, e alpha alpha is a metagalactic function with alpha, and alpha tilde is positive. That I will define in the proof what is metagalactic function. So in the most important point, the one I just quote the important point of the proof is that the finding the beta t explicitly. So as we want a differentiable solution, then we in the space variable, so u1x 0 plus equal to u2x 0 plus, this condition one can impose, and imposing this condition we got this formula, and then using integration by parts we have this non-homogeneous fractional differential equation. Here is a non-homogeneous fractional differential equation, and by applying some you have a explicit formula for this non-homogeneous fractional differential equation, and it is yeah, it is by this yt equal to this one, and e alpha alpha is the metagalactic function, z power k, gamma is the usual gamma function, gamma of alpha k plus alpha tilde, where z is in complex number. Okay, so we now from using this we can get the explicit formula of beta t. Okay, it's a calculation. Okay, so our next time is to pass to the limit. How we pass to the limit? Because boundary. So now, as I said in the plan, that beta t, we have to show that beta t is independent of epsilon. So if we so using the recursive relation of this beta Laffer function and some change of variable, we pass to the limit as epsilon tends to 0. And this is our final theorem for the linear case. Here you can see when x positive, we have u naught x plus c, and in the interface we have a delta wave. Interface means that x equal to 0, we have a delta wave. And otherwise, if this is not equal, so u naught we define 0 to x u naught of z. If it is not equal, then there is no delta wave. Yeah. So sketch of the proof is that write u1 u1 is in some differentiation as a differentiation of some function, partial differentiation of some function p, and u2 as a differentiation also some function p q. Now you define the capital uxt epsilon is pxt and uqxt. Now pass to the limit and define capital ux is a small u, and you obtain the. So here you can see that epsilon tends to 0, cap uxt is this and this. When x greater than 0, it is this, and when x less than 0, we have u naught minus x, u naught of x minus t minus 2 u naught of minus t. So then we can have a delta wave because it's a jump. Okay. So now the Lax-Solonic formula. Now we move on to the case non-linear case. As we know that this V is a Lipschitz continuous function, and which is a viscosity solution of this. Then the distributional derivative of it is a weak satisfies the weak formulation. Weak formulation, by weak formulation I mean this weak formulation. That first weak formulation I showed here. Okay, this weak formulation. Okay. Okay. So now one problem comes that if it is only strictly convex, if f and g are only strictly convex, and we assume that f dash is negative and g dash is positive, then we already loses the superlinearity condition. Okay. So but that can be avoided, that we can manage by the help of maximum principle, because if u naught is already bounded measurable function. So if u naught is in m small m to capital M, we can extend f and g outside of small m to capital M by superlinear function, and f equal to f bar and g equal to g bar on small m to capital M. So in that way, by modifying modifying the flux function outside small m to capital M, we can still have a Lax-Solonic type formula. So final result is the Lax-Solonic type formula is the, so suppose v naught is 0 to x u naught and define the cost functional. The v1 xt is defined in the minimum when y1 is less than equal to 0, and minimum of this functional. So minimum is attending on that set minus infinity to 0, and okay, sorry. And g star tilde g tilde star is the convex dual of g tilde. See, we have g tilde is a superlinear growth and strictly convex, so we can have the convex dual for that. And similarly for, and it is for the when x is less than equal to 0 and v2 also we define the similar manner, where f star is the convex dual, f tilde star is the convex dual of f tilde. Okay, so we have the following formula. This uxt equal to u bar of xt with the weight, and this is u bar is defined as this g tilde inverse, and wt is this. Okay. Okay, so yeah, so numerical schemes. Yeah, so I
think we are out of time.
Okay, fine. I just want to say, okay, so it's I just want to show a picture that where we can actually have a delta shock. Delta shock. Here we can see that this curve is blowing up. So the weight is 3.0024, and this is the weight of the delta shock here. Yeah, thank you.
Okay, thanks, Abhijit, for this nice talk.
Yeah.
Is there any questions? Yeah, so, okay, so I just have, yeah, I just wanted to ask you something. Okay, so basically here it seems X belongs to R, real line, right? How about in the higher dimensional domain? Like what would be the higher dimensional analog of this problem, like UT minus something, where X is Rn or maybe subset of Rn?
That is difficult because I don't know, because if you take in the 2 dimension, their definition of discontinuous flux is horrible. I mean, in which I don't know this. Just considering two dimension. So the definition of what is the discontinuous flux in that in the higher dimension. I just only we considered here in it is discontinuous in one point. So even if in one dimension, yes, even if in one dimension the flux is discontinuous in many points, I don't know the answer. I mean, how to do it. So yeah, that is a question. Yeah, that's a thank you.
Okay.
I
Yeah,
don't know the
thanks.
answer. Yeah.
Yeah. This is just my curiosity. Anyway, thank you so much. And
Yeah. Thank you.
Thanks
So
everyone.
anyone?
For...
Yes, here is some reference also. If one can see this number 4, that the detailed calculation is there. Okay. So.
Okay.
So there you can see how get it.
Yeah.
Okay.
Yeah. Okay.
Thank
okay.
you.
Thank you so much. Yeah.
Thank you.
And
Manas,
yes.
Thank you so much for chairing this session. Thanks
Yes.
a lot.
Yes. Thank you so much for this invitation to me. Yeah. Thank you so much. Yeah.
Thank you, Manas.
Okay, so we close here. Yeah.
Okay. Fine.
Meet at 5 for the plenary talk.
Okay.
Where is the chat gone? Don't see it anymore. Oh, okay, it's in more. Oh, okay, more.
Can you see it now?
It's in more. Yeah, I have to click more items and then, but I don't really need the chat. Actually, it's probably good I can't see the chat.
Okay,
so
sure.
If you want me to see the chat, you should just interrupt and tell me to see the chat.
So
No,
questions would come in by chat, is it?
Yeah.
I'll maybe I'll read them out. as they come in. If at an appropriate time, I'll wait till there's a pause or something and read them out. So then you don't need to. I mean, it's very distracting to keep looking at the chat.
Yeah, and in between, nobody will ask questions. So after the talk only, we will address the questions.
Oh, okay. So if they're but if there are questions in the chat, should I read them out or?
After the talk, I guess.
Only after the talk. Okay, so
Yeah.
no interruptions during the talk. Fine. It's almost time.
Yeah, we may start now, I guess.
Yeah, so
good evening, everybody.
Yeah, I welcome Professor Amritangshu Prasad. He will be chairing the session. Yeah, please continue, sir.
Good evening, everybody. Welcome to this talk. It's a great pleasure to introduce Eknath Ghate, School of Mathematics, TIFR. Professor Ghate works in p-adic representations and L functions. He received the Bhatnagar Shanti Swarup Bhatnagar Prize in 2013. Today he's going to talk about mod p representations. Eki, please.
Thank you.
Begin.
Thank you very much. So thank you, Professor Prasad, for that nice introduction, and thank you to the three organizers who put in so much effort. Just told me that you're doing this 12 hours a day for 5 days, so that's rather incredible. And it's also a good opportunity for older people like me to learn some technology and get to use these virtual platforms to give talks and things. So I will speak about mod p representations. That's the title right there. And that is the Brucher-Titz tree, in case you're wondering, that picture. I'll come back to it in the talk. But that is the central picture for the talk, actually. You know, they say all of mathematics is linear algebra or graph theory, but so here's a bit of graph theory. Okay, so here's the overview of the talk. So let p be a prime number. And I'm going to work a lot with these p-adic integers. So Zp is going to be all, as algebraically, you can just think of it as numbers and with some base p expansions, but they have infinite tails. So R0 plus R1p plus R2p squared, where Ri is 0, 1, 2, 3, up to p minus 1. Okay. So, you know, we are familiar with decimal expansions, and we usually terminate these things. But if you keep going here, then and p is a prime, then you get the p-adic integers. So that's how you can think of these algebraically. You can add these things by doing some carries and multiplying also by doing something similar. So QP is the quotient field of ZP, and it's the field of p-adic numbers. So again, this is all quite algebraic, but you can also think of QP as the completion of Q with respect to the p-adic metric. So, you know, you have this, can have this dictator who decrees that two numbers are close if they're highly divisible by 5. So for example, 25 is quite close to 0, but 125 is even closer to 0, and so on and so forth. 625 is very close to 0. So this gives some sort of metric on Q, and if you complete Q with respect to this metric, you get also QP. Okay, so we have the p-adic integers and their quotient field, the p-adic numbers. And finally, you can also go mod P. So starting from ZP again, from ZP again, you can go mod P. And if you go mod P, you kill all the terms R1P, R2P squared, etc. And you're just left with R0. So that's P by this 0 to P minus 1, that's P elements. And in fact, you get the field FP, finite field with P elements, which everybody knows. So in this talk, we'll be interested in certain representations of two groups in particular. So I'll denote by G the 2 by 2 matrices with entries in QP, invertible matrices. And I'll denote by gamma the 2 by 2 matrices with entries in FP, the finite field with P elements. Okay, so these two groups will play a very important role in this talk. And I will be interested on the actions of these groups on vector spaces, often infinite dimensional, usually infinite dimensional vector spaces, over a field of characteristic P, but more precisely over FP bar, the algebraic closure of FP. And we will just call loosely any such representation as a mod P representation, either of G or of gamma. Okay, we should also be interested in connections of these mod P representations of G of gamma, G or gamma, with Galois representations, and in particular with mod P Galois representations. So I'll define those much later towards the end of the talk, and using what are called Langlands correspondences. Okay, that sounds a bit fancy now, but we will see that everything is very concrete. Okay, so that is the overview of the talk. Basically, we'll study mod P representations of G, and we will see how they're connected to mod P representations of the Galois group of QP, which will come up later. Okay, so let's start with some representations of gamma. So let VR be the space of all homogeneous polynomials P in two variables, x, y, of degree r greater than 0, with coefficients in FP bar. So these are just your usual polynomials in two variables, coefficients are in FP bar. And they're homogeneous. So the degree is 10, it'll be like x10 and x9y and x8y squared. That'll be a basis as a vector space. So the finite dimensional thing, dimension r plus 1 if you have degree r. So this has a natural action of GL2FP on the space of polynomials. You just substitute for the variables. If you have a matrix ABCD in GL2 of finite field, you just take x to ax plus cy and y to bx plus cy, and you get a natural action of the group on this vector space. So this is a model for the symmetric arc power representation of the standard representation for the experts. But you can just think of this very classically as just 2 by 2 matrices acting on polynomials, sort of a high school kind of object. Now, it turns out that unlike the complex numbers, where these representations are irreducible for all r, these particular VRs, if you have GL2 FP acting on this mod P vector space, it's not always irreducible. In fact, it's only irreducible for small values of r. And then when you cross r equals P and onwards, it becomes reducible. And in fact, if you want to write down all irreducible representations, you can just use these. VR basically are the models of all of them, as long as you're willing to also twist by powers of the determinant. So GL2FP, if you take the determinant to get something in FP star, and if you take an sth power, then these are just characters, and you can twist this representation by d to the s. So these are all irreducible mod P representation. That's a complete list. Okay, so the question immediately arises, what is VR for larger R? And it has many interesting subquotients, and it has many interesting subrepresentations and quotients. And of course, the Jordan-Holder factors of these representations will, or these subrepresentations or subquotients, will always be from this list, this finite list. Okay, P times P minus 1 representations. So we will study a few of them here. And I will tell you why the particular ones we'll look at are important soon. So one class of sub-representations you can look at are the monomial submodules of VR. So this is, again, a very elementary thing to do. You just take, for example, x to the power of r, when I is 0, that xr minus I is generated by xr minus I y to the I, that particular monomial. You just take that particular monomial and look at the gamma submodule generated by that monomial. Okay. So I should say that before I go further, just, for example, if you have R is P and you look at x to the P, then how does a matrix act on x to the P? I would have written something here on my slide, but I'm a bit nervous to use my pen. So x to the P just goes to ax plus cy to the P, and by the freshman's dream, that's just a to the P, x to the P plus c to the P, y to the P, right? That's the most stupid version of the binomial theorem in characteristic P. So x to the P is not generating something very large. It's just generating a two-dimensional space. A to the P, in fact, is just A. So it's just all you get is x to the P and y to the P. It's a very small submodule, two-dimensional. And this is happening because it's allowed to happen because these VRs are not irreducible. They're reducible. So you can get something small. Okay, so the question arises, what are these submodules? What are their structure? What is the lattice of all submodules inside VR? So I'm going to restrict to the first P submodules, XR, XR minus 1, XR minus 2. Somebody keeps writing on my slides. That's not me, by the way. It's one of the hosts. So please be careful. XR by this P by this 1. So it's not at all clear, but there are inclusions between these monomial submodules. For example, let's look at the first one, XR and XR minus 1. You want to show that XR is sitting in XR minus 1. Well, you need to write the monomial X upper R as a linear combination of vectors in X lower R minus 1. And that particular linear combination works because if you make 1, 1, 0, 1 act on XR minus 1y, then the X part isn't changed. This acts by columns. So X just goes to X, but the Y goes to X plus Y. And so you'll get X to the R plus X to the R minus 1y, and then you cancel off the X R minus 1y. So you can see that XR is a linear combination of vectors in the second space, and so the first inclusion holds. And you can do similar tricks to show that, in fact, all those inclusion holds. It's a bit deceptive because after this, things begin to break down, which is why I've restricted to this particular list. Okay, so let me make a definition. For any I between 0 and R, you can look at the sum R minus I plus I, which is of course equal to R, but try and do this in base P, in those base, using the p-adic digits. And as in base 10, as we all learn in school, when we're adding numbers, then, if you have 3 plus 7 in the units, you get a 10, so you get a 0, you have to carry a 1. And there's some carries. And because there are just two numbers here, you just get a sequence of zeros and ones when you try and do this addition in base P. And these numbers are called the carry patterns of the equation above. Okay? Amritanshu, can I just request you to tell the hosts? Somebody's writing on this something. Somebody's rubbing.
I don't know how to do this. So I'm making Amritsar host. Can you?
So we don't understand actually what's happening.
I think somebody's elbow or somebody's is
maybe
touching some pad somewhere.
1-year-old child.
So
it has to be one of the hosts.
Do you know how to stop this? Maybe I can make Amritsar a host.
Maybe the talk is being hacked by the Chinese or something. Okay, I'll move on. I'll move on. So while you guys figure that out. So there's a sequence of zeros and ones that we get, which is called the carry pattern of the equation above. Okay, so as soon as you have an I, you canonically get a sequence of zeros and ones, the carry pattern of that particular summation in base P. For example, if you want to do of course, if you write, if I is 0, then R is equal to R plus 0, and then the carry pattern is just 0, 0, 0, 0. There are no carries. But a bit more interesting, if you take R minus 1 plus 1, so if P does not divide R, then there'll be no carries when you add r minus 1 and 1, right? Because if p does not divide r, then the last term, the constant term in that base p expansion, is non-zero. So r minus 1 is, you don't have to do much. You just have to subtract 1 from the constant term. And then when you add it back, there's nothing going to happen. You won't get any carries. But if p divides r, it's a bit more subtle, because if p divides r, suddenly the base p expansion of r minus 1 changes, right? Because there's nothing to subtract from the constant term. You have an r1p and then an r0, but r0 is 0. So when you subtract 1, you're not allowed to put a minus 1 in the constant term, right? So you have to write a p minus 1 there by borrowing a 1p. And then when you add a 1 back to it, then you will get a carry. P minus 1 plus 1 becomes p, but you're not allowed to write p, so you'll get a carry of 1. Okay, so it's very elementary. Each time you get some sequence of zeros and ones, carry pattern. Okay, so here is a rather remarkable theorem, which unfortunately is not true in our setting, but is true if you replace GL2FP, which is a finite group of Lie type, by some sort of algebraic group, GL2FP bar. So it's GL2 with infinitely many entries in it. And the theorem says that there's an isomorphism of lattices between the monomial submodules of VR, so those are the things we're trying to study, with respect to inclusion, and carry patterns with respect to lexicographic ordering. So this is a theorem of Doty from 1989. Okay, so lexicographic ordering is just the dictionary ordering, right? 0, 0, 0 comes before 1, 1, 1, and so on and so forth. 0, 1 comes before 1, 1, etc. So this is really a remarkable theorem. It's telling you all possible inclusion relations completely in terms of the relations between the carry patterns. Okay, unfortunately, this is no longer true when we replace gamma bar, which is an infinite group, GL2FP bar, back with gamma, which is GL2FP. So here's a silly counterexample. We just did, when p does not divide r, we just looked at the carry patterns when I was 0 and I was 1. When I is 0, of course, the carry pattern is always a string of zeros. But when I is 1 and p does not divide r, then we still get this sequence of carry patterns, trivial sequence, 0, 0, 0, 0, 0. So that means that it looks like XR should be equal to XR minus 1 because they have the same carry pattern by Doty's theorem. But Doty's theorem doesn't work here. Turns out that XR is strictly contained in R XR minus 1 if R is greater than or equal to P. And that's not such a hard computation. I've given some references to things I say which are on the last slide. So that's one of the references, Bhattacharya Ghate, 2015. Okay, so can we rescue this in some way? And it looks pretty nasty, but here is a nice lemma. So we need a little bit of notation. So let sigma PR be the sum of the p-adic digits of R. So R0 plus R1 plus R2 plus Rm. In base P expansion, R is an integer, so it stops. So you can add these things up, a regular integer, not a p-adic integer. And the lemma is this, that if R is greater than or equal to P, and j is smaller than I, but always between 0 and p minus 1. Remember that we know that xr minus j is sitting in xr minus I because we had those strings of inclusions. But they're in fact equal exactly when I and j have the same carry patterns. But in addition, you have two more conditions. The sum of the p-adic digits of r minus j has to be small, and the sum of the p-adic digits of r minus r0, r0 was the constant term in the base p expansion, that also has to be small, less than or equal to j and less than or equal to p minus 1. Okay, so that, notice that the fact that I and j have the same carry patterns is a necessary condition, because if xr minus j is equal to xr minus I over fp, when you work with GL2FP, then it's necessarily true over GL2FP bar, right? They're the same generators. So it forces that I and j have the same carry patterns by Doty's theorem. But it's not sufficient. You need two extra conditions to guarantee equality there. Okay, so this is some kind of flavor of how things change when you move from GL2FP bar to GL2FP. Okay, now what about the actual structure of these modules? So let P be greater than or equal to 3, eventually P will be even 5 or more. The structure of XR, as I said, XR can be quite small. Remember when R was P, then XR was just a 2-dimensional representation. It's just something quite small. But in general, XR has at most 2 Jordan-Holder factors. And XR minus 1 this was due to Glover in 1978, the previous result. XR minus 1 was studied much later Surprisingly, these kind of high school things, there's not much literature on them, and we looked quite a lot, and then had to do everything by hand. So XR-1, remember this is the gamma submodule, GL2FP submodule generated by XR-1Y. And this has between 2 and 4 Jordan-Holder factors. And these can be determined quite explicitly. Remember, I gave you a complete list of the P times P-1 Jordan-Holder, all the irreducible representations. You can really write down which ones occur in which cases. Basically, it's a 3-part theorem. I won't get into it now. But everything can be done very explicitly. So here's some joint work with Raviteja Vangala, who was also speaking, I think, giving a short talk at the end of this conference in more details about some of the things here. But here is one of the theorems. It says that if R is sufficiently large, then the structure, and if the sum of the p-adic digits of R minus R naught is sufficiently large, bigger than P, then XR minus I is very simple. It's just the tensor product of 2 fairly known representations. So XR minus I is the tensor product of what I call XR minus I comma R minus I. So this is the gamma submodule generated by X upper R minus I, but in VR minus I, lower I. Okay, so that's why there are 2 commas, because it's a bit ambiguous, the notation. And then tensored with VI. VI is sitting in, is just VI. Okay, so it's a tensor product of 2 smaller things. And there are these representation theory, if you try and do any representations of SU2C and things, there's something called Clebsch-Gordon formulas. Very nice formulas that if you have 2 irreducibles, then you tensor them, how do they decompose? And so these kinds of formulas also hold here. So once you know that something's a tensor product, you can apply Clebsch-Gordon formulas to actually find the full structure of XR minus I. So this, unfortunately, has a condition that the sum of the p-adic digits of R minus R naught is a bit large. That's the generic case. It usually will be large. But if it's small, if the sum of the p-adic digits of R minus R naught is less than P, then the structure of XR minus I can also be determined in terms of explicit tensor products and certain irreducible principal series representations, which I will get to in a second. So I won't tell you exactly what it is, but I will tell you what principal series representations are. I should say that isomorphism looks a bit mysterious, but it is not at all mysterious, because on the right-hand side, you have the monomial X upper R minus I, which sits in VR minus I, and you have Y to the I in VI. And if you multiply those together, you get XR minus I YI. So there's a map from the right to the left, multiplication map, and it's that multiplication map which becomes an isomorphism. Okay, so what are these principal series representations? So some standard notation. We look at the upper triangular matrices in gamma. It's called the Borel subgroup, the standard Borel. A, B, 0, D, where the diagonal entries are non-zero elements in the finite field, and D is in FP. And we look at a character chi acting on such matrices. So we just look at the diagonal things, and we take A, B0D to A to the M, D to the N, where M and D are integers. Okay, so this defines the character chi of B. Should turn my phone off. Okay. So for such a character, we immediately get a p+1 dimensional representation. What you do is you look at all functions from gamma to FP. So these are all functions from GL to FP to FP. It's like a, almost like a computer science talk. So everything is finite here and finite dimensional so far, right? We're working over finite fields. So these are functions, arbitrary functions, not homomorphisms or anything, from GL to FP to FP. But it has one relation, and that is that f of h gamma is chi of h times f of gamma. So chi of h, remember, was something in FP star, so you're just multiplying by a scalar. And f of gamma was something in FP, so again, another scalar. You're just taking the product of 2 scalars there. This is for all h in the Borel and all gamma and gamma. So if you have this condition here on the left, then you can make an action on the right. Gamma can just act on the right. It won't change your condition, and it'll preserve this space. And so this is called the principal series representation of gamma. And because the index of B in G, the index of B in gamma in GL2FP is clearly p+1, right? GL2FP mod the upper triangular matrices, that cardinality of that thing is p+1. This representation has dimension p+1, and it cannot possibly be irreducible, because remember, irreducibles stop at p, dimension p, because p minus 1 was the last one. So that has dimension p. So this is almost irreducible. It's just beyond that range, and it has 2 Jordan-Holder factors. Okay, so these kinds of principal series representations can be used also to describe the structure of the monobial submodules, and they come up in many places. So I thought I'd recall the definition here. Okay, so that's one kind of submodules of VR, and there's another very interesting set of submodules of VR, which I will describe now. So these are the theta submodules. So what is theta? Theta is a very concrete polynomial, sometimes called the Dixon polynomial, x to the p y minus xy to the p. This has the remarkable property that GL2FP preserves this polynomial, in the sense that if you make a matrix act on that, then you'll just get the determinant pulling out, and you'll get the same polynomial back, right? So it acts on theta by the determinant. That's a small computation, and this uses very, very heavily that you're working in GL2FP and not in GL2FP bar. So this is something completely new to GL2FP, because you want to use things like a to the p is equal to a and things like that for scalars. Okay, so for each of these, for theta, we get these submodules, and they're very easy to define. VR upper m. They're just all the polynomials which are divisible by theta m times. Okay, so VR1 means all polynomials which are once divisible by theta. VR2 means all polynomials twice divisible by theta, so on and so forth. Okay, so clearly there's a filtration. As you have more and more divisibilities by theta, you have this. And ultimately, of course, you'll go off to 0 because R is finite and the degrees of these things are increasing. So notice that there are some elementary facts about these VRMs. So first of all, the first one is very easy. The first one just says that VRM is basically another VR, but for a smaller r. R minus m p plus 1. The degree of theta is p plus 1, right? That polynomial at the top of the page has degree p plus 1. So what you're left over with something of that degree, r minus m times p plus 1. And because you've pulled out the theta, the action is by determinant to the m. So that's more or less obvious, the first thing. So individually, they're not that interesting. They're just shifts of VR up to twists. And the quotients are also fairly interesting. The quotients are actually principal series representations. So VRM mod VRM plus 1 is induction b to gamma, a to the m, d to the r minus m. So as on the previous slide, in particular, they're p plus 1 dimensional, which they have to be, right? Because you're dividing by theta. So each one of those things which has degree p plus 1, dimension p plus 1. Sorry, degree p plus 1. So any one of these quotients will have dimension p plus 1. In particular, you notice that VR mod VR1 is periodic in R mod p minus 1, right? Because if you take m to be 0, then you just get induction b to gamma d to the r. And d to the r is periodic mod p minus 1 because, d is in a finite field. So if you replace r by some s, then d to the r is congruent to d to the s. They're equal. And that immediately says that VR mod VR1 is also periodic. And remarkably, this was in Glover's originally paper, this was proved in some ad hoc way. So he has a fairly long proof, a half a page proof. But if you notice that these things are principal series, the proof is very trivial. So one of the things that Ravi and I started wondering about is there some periodicity for the higher quotients? So VR mod VR1 is periodic. What about VR mod VRM? So we came up with the following periodicity result. I won't read all the quantifiers there, but basically R and S are large and M is small. So if R is going to S mod P times P minus 1 this time, okay, not mod P minus 1, then in fact the periodicity can be, you can have some talking about general periodicity result. VR mod VRM is isomorphic to VS mod VSM. Okay, so for an m is equal to 1, we already knew this by Glover. In fact, you don't need R to be corresponding to S mod P times P minus 1. You just need R to be corresponding to S mod P minus 1. But if you're willing to throw in the P times P minus 1, then you get this. And I leave you to you to guess what a generalization of this would be for if m becomes bigger and bigger, goes beyond p. There's some very obvious statement here. But this is the one that we needed, and we could prove this. And since every talk's supposed to have a proof, let me give you a quick proof. Quite pleased about this proof because it uses some objects from deformation theory, which is a subject that number theorists study quite a bit. And one of the things that appear in deformation theory is not the field Fp, but the ring Fp epsilon mod epsilon to the m. Okay, so when m is 2, those are just what are called the dual numbers. Okay, so I'm going to give a proof, a one-line proof using these dual numbers and their higher analogs. So let gamma r be GL2R. So GL2 is some sort of group, but you can plug in fields, as Anand Sawan did in the opening talk, finite fields or infinite fields. But you can also plug in rings, right? You still get a group. So gamma r is GL2R for that ring. And BR is similarly the Borel, the upper triangular matrices, but the entries now are in R. Okay, and then we define a map from VR to this sort of generalized principal series, but you know, it's induction from BR to gamma R this time. The same definition, D to the R. And we take the polynomial Pxy to some function. And what function is that going to be? It just takes gamma to P of CD. And then it's a nice, very pleasant check to see that this map is actually FP linear and gamma linear. And so you get a morphism from VR to the right side. And the kernel of this map is exactly VRM. And then as we observed in the case of Glauer, that character D to the R is periodic mod P times P minus 1. If your ring R is in that range, then your character there is periodic mod P times P minus 1. So if R is corresponding to S, mod P times P minus 1, then D to the R is equal to D to the S, and therefore the right-hand side doesn't change. And therefore you can see that VR mod VRM is the same as VR, is periodic. It's the same as VS mod VSM. There's something more one has to check because this map is not actually an isomorphism. It's only surjective if M equals 1. But the point is that the right-hand side, periodicity of the right-hand side forces periodicity of the left-hand side. Okay, so we want to move on now. So we defined, just to recap where we are, we first defined VR, the symmetric power representations of GL2FP. Then we defined some monomial submodules, the XR, XR minus 1, XR minus 2, etc. And we also defined some theta submodules, VR0, VR1, VR2, right? 2 different filtrations. Now we want to combine these and look at quotients which use both of these submodules. So here's the definition. We look at VR and we take the quotient of VR by XR minus I. That's what the I is there in QI. But we also quotient out by VR to the I plus 1. Okay, so it's not so clear why not we take I and J, but these are the ones that are very interesting for us for applications. Okay. So it follows from the previous lemma that because VR mod VRI plus 1 is periodic, that the QIs are in fact periodic in R modulo P times P minus 1. Okay, so this is one observation. So let's do some simple examples. When I is 0, that's the simplest case. Well, VR mod VR1, we just said that many times, it has 2 Jordan-Holder factors, and I is 0, so XR minus I is just XR. It kills one of the Jordan-Holder factors, and Q0 is just then one particular Jordan-Holder factor, and that's what it is. It's one of the irreducibles, and then that's the formula for what you get. Vp minus 1 minus A tensor dA. Notice that P minus 1 minus A is smaller than P minus 1. You can also compute Q1, and it has 1 to 3 explicit Jordan-Holder factors. Again, I won't write them down, but they're basically 3 cases. When you get 1, when you get 2, when you get 3. And so you can work out Q0 and Q1 explicitly. So one of the things that Ravi has done is he has come up with an algorithm to in fact compute Qi, all the Jordan-Holder factors for Qi, as I varies between 0 and P minus 1. And this is not easy because XR minus I is slightly erratically behaved. even though VR mod VRI plus 1 is well behaved, XR minus I is slightly erratically behaved. So there's some cases and some things that have to be done here. And he will hopefully tell you more details about this. Okay, so the theorem is that the quotient Qi has between 1 and 2i plus 1 explicit Jordan-Holder factors. The fact that it has that many Jordan factors is not at all hard, but you can explicitly write them down, as I did for Q0. Okay, so much, I think, for representations of GL2FP gamma. Now we want to move to representations of GL2QP, which are a lot trickier. So just so that I don't have to write GL2QP many, many times, please note that G is again GL2QP. There are many groups in this talk, but G will appear a lot. So it's GL2 of an infinite field, the field of p-adic numbers. Okay, and some more notation. We have, just like QP has its integers, ZP, similarly, G has the subgroup GL2ZP, which we'll denote by K, and this is a compact open subgroup of G. And then you have the diagonal matrices, isomorphic to a copy of QP star, this AA sitting on the diagonal, where A is in QP star, and we'll call that the center, Z. Okay, so I said that the tree will come back into this talk. So notice that GL2QP acts on lattices inside QP squared. So, okay, let's break this down a little bit. So QP plus QP has lattices. Lattice, what do I mean by lattice? Basically, I mean something which is isomorphic to two copies of ZP. So ZP plus ZP sits inside QP plus QP, but in many ways, there are many copies of ZP plus ZP inside QP plus QP. So GL2QP moves these lattices around, because if you have two basis vectors, E1 and E2, you can just make them act, and you'll get another lattice, right? So what we do is we look at the tree. This tree is a pictorial representation of all the lattices and all the inclusion relations between them. In the center dot there is the standard lattice, let's say generated by 1, 0, and 0, 1, ZP linear combinations of that. And then what we do is so the vertices are all the lattice. The edges are the inclusion relations. So if you've done a little bit of first year algebra, you know that inside Z plus Z, there are 3 lattices of index 2, not just 2Z plus Z and Z plus 2Z, but there's also a diagonal lattice, the sort of all entries inside Z plus Z, which are either both even or both odd, X congruent to Y mod 2. That's another lattice inside Z plus Z. So there are 3 lattices. So those are those 3 dots. I'm doing this for p equals 2. And I was giving an example for Z, but ZP is exactly the same argument. So the central dot is the standard lattice, and then those 3 dots reaching out from it are those 3 lattices I just talked about, and so on and so forth. Okay, so that is the Bruhatitz tree. And though I said that p is greater than or equal to 3 in this talk, it gets trickier and trickier to draw this, and especially find pictures on the internet. So here's the picture for p equals 2, which is complicated enough. So I'll just read what's written at the bottom. The vertices are homothetic classes of lattices, to be a bit more precise. I'll leave that for you to figure out. It's just something easy. And whose edges correspond to inclusion relations among lattices. And that also needs to be made a bit more precise, because we replaced lattices by homothetic classes of lattices. Just multiplying lattices by a scalar. Okay, so this tree in general has valency p plus 1. So this is a very central object, and many of the representations that appear are basically going to be some sort of functions on the tree. Can people hear me? Let me just pause for a second. There's been long silences. Can one of the organizers say everything is okay?
Yeah, everything is clear.
Okay, great. Am I going too slowly?
No, I don't think so.
Okay. Okay, so now we want to move from the tree to representations of G. How do we do this? So you start with a mod P representation of gamma. We've seen many of them, right? So if you have a mod P representation of GL2FP, then you immediately get a representation of GL2ZP by surjecting GL2ZP onto GL2FP. And then you can make the diagonal matrix P act trivially. So this becomes a representation of Kz. Okay. So starting from a representation of GL2FP, we got a representation of Kz, but how do we get a representation of G? Well, Kz acts by G on the left, it's a subgroup, and it acts on V, as we just described in the line above. So Kz acts on G cross V, and then you can take the projection to the first factor, Kz to G. And we just said that was the tree, right? Because G acts transitively on the lattices, and Kz was the stabilizer of the standard lattice. So that's just the tree. So we have this kind of collection of vector spaces sitting above the tree. And we will define sections of this cover. So a section has the obvious definition, but I wrote it out here. It's all functions from G to V, such that again, f of hg is h times f of g for all h in kz and g in g. Okay, so this is the condition that the function has to satisfy. So if you have a section, what is a section? It's something from a function from the right to the left. On the first coordinate, it's kind of forced what you have to do, right? Because if you have a little g on the first coordinate, it has to be little g. But on the second coordinate, you have some ambiguity. So you call that f of g. So it's something at v, and that's how you get your function. And then this condition is more or less forced on you. F of hg is h dot f of g to make things well defined. But there's a little more technical condition. We also require that f is compactly supported mod kz. Okay? So what does it mean that f is compactly supported mod kz? First, note that kz really acts on the support, right? Because of that condition, f of hg is h dot f of g. So it makes sense to speak of support z, kz backslash support of f. And because kz is open, I said k was open. So kz is open in G. The support mod kz has the discrete topology. And because it's compactly supported, this thing is in fact finite, the support. So one could drop that fancy language, f is compactly supported mod kz, to just say f is finitely supported mod kz. Basically, it's on finitely many cosets, it takes some values, and then within the cosets, you can get the values by these translations. All right, and this is a G module via right translation in the usual way, just as we did for the when we were defining the principal series, which was induction from the Borel. This is induction from KZ, by the way. So a very simple instance of this is if V is the trivial representation, then this in space of sections, well, what is this relation f of hg, h dot f of g? The action of h on f of g is trivial. So it's just f of hg is f of g. So it's just functions on the tree. And these are just finitely supported functions on the tree. So the simplest case of this somewhat general construction is basically the Brumer-Stark tree along with some numbers on the vertices of this tree between 0 and p minus 1, which are the values of the function at that point. And it's compactly supported. Within a ball, you have some non-zero things, and outside this ball, you don't have anything. So it's a very, very simple kind of object. So all we're looking at are these graphs with numbers on them. Though on this page, you will not be able to tell that to a graph theorist if you just showed them this page, right? It's just basically some tree with some numbers on it, and the numbers are compactly supported. And more generally, if you have a coefficient system V, then you get something a bit more complicated. But it's not much more difficult from this. Okay, so now here comes an extremely important definition. So remember, int kz, g, v are basically functions on the tree. I mean, when v was trivial, they're just those compactly supported functions on the tree. So one very natural operator is the sum of neighbors operator. If you have a function and you want to define a new function, well, how can you do this? Well, at any point on the tree, you can add up the values of all the neighbors of that particular vertex and decree that to be the new value at that point. Okay, the sum of neighbors operator. So this is a very canonical thing to do in graph theory. And if you have a more general coefficient system V, then you get in general a more complicated definition for the Heck operator. And it turns out that this map is certainly G equivariant, right? Because if you add up the values on the tree, you get one thing, but if you shift and add, it's the same thing as adding and then shifting, right? So it doesn't change anything. I mean, adding and shifting and adding are the same thing. So this is a G-equivariant map. In fact, this is the only G-equivariant map there is. The endomorphism algebra is completely generated by this one canonical operator, the Heck operator. Okay, as I said, in the very silly case of the trivial representation, where you just have these graphs with a bunch of dots on it, a bunch of numbers on it, then the value at any point is just the value of the sum of the neighbors of that point. Okay, now if you think about it a little bit, let's just take lambda to be 0 for a second. The operator T is injective, because if you have just like the graph with just one non-zero point, that's going to propagate once you apply T to it, right? You take the sum of neighbors, it's going to give you a whole bunch of non-zero things. Just take the graph where everything is 0 except at the origin you have a 1. If you look at T of that function, well, around that thing, you're going to take sum of neighbors and the 1 will propagate. So non-zero functions sort of blow up, they become non-zero, more than non-zero. So T is injective. And T minus lambda just means you're multiplying a function by lambda. So that's a sum of two operators. That's lambda times identity operator. So that continues to be injective, but it is not surjective. And I'll leave you to think about that for a bit. Okay. So once you have a G-equivariant operator, which is injective but not surjective, the kernel is not very interesting because it's injective, but the co-kernels of these operators can be very interesting. And they give new representations. So that is the basis behind this definition. The induction KZGVR is the space of all functions. And then we're modding out by the image of T minus lambda. So that's the co-kernel. Okay, it wasn't surjective, so that's a non-zero space. And then we twist that by some characters, eta composed with det. So if you just look a couple of lines above, R is small, lambda is a non-zero scalar, and eta is a character. And so this is the basic representation, pi r lambda eta, which I will use again and again. Okay, so these mod PG representations are essentially irreducible, which is very surprising. Notice that we just modded out by the image of T minus lambda, but there's no one to say that the co-kernel should be irreducible. But they're essentially irreducible, so that's one fact. And they turn out to be the basic building blocks of the mod P representations of GL2QP. Okay, they'll come up again and again. So I'll make this a bit more precise, I think, in the next slide. Why are they the basic building blocks? You can write all the representations in 4 families, and they're all more or less built out of this pi r lambda eta. So I think here they are. Before I do that, I'm going really slowly. So let me tell you about one of the 3 classes of representations. So for example, if you take the trivial representation, then there's something very combinatorial you can do. Remember, the trivial representation is just compactly supported functions on the tree, right? Just basically those graphs, which are a bunch of non-zero values. And you can look at the total sum of any particular function because it's compactly supported. You just add up all the values and you get a number, right? Okay, so that's a very canonical thing to do. And clearly, the total sum of TF was the sum of neighbors of everything, right? Is P plus 1 times the total sum of F because you've overcounted P plus 1 times, right? Each vertex has P plus 1 neighbors. So if you first do that and then you take total sum, you'll get P plus 1 times the total sum. But P is 0. So when you push everything into FP bar, then TF and F have the same total sum. That P plus 1 times the total sum just becomes 1 times the total sum. So TF minus F goes to 0. And another way to say that is that that map factors through T minus 1. And now that's beginning to look very much like one of the representations on the previous slide. It's beginning to look like pi 0, 1. The last one there is the identity character. I didn't twist by anything. So R was 0, so that's the pi 0, and then we're modding out by T minus 1. So we get a factorization through 1, and so pi 0, 1, 1 is no longer, unfortunately, irreducible because it had a FP bar as a quotient. But the kernel now turns out to be irreducible, and it's called the Steinberg representation. Okay, so this is how you can build some of the representations out of these pi r lambda etas. Okay, so I will now tell you the classification. Before I do that, let me just say that there are some topologies involved, and we always want to work in the category of smooth representation. So a mod P representation of GL2QP is said to be smooth if the stabilizers of vectors are open. Okay, this is what will guarantee that the natural action of G on the vector space of pi to pi, this action is continuous. Okay, so this word is always there in the background. Okay, so here is the classification. Eta will denote a character. It's a theorem of the following people: Barthel-Livna in 2 papers, in Duke and JNT, 1904 and 95, and then Breuil and Compositio and Jussieu actually has 2 papers as well, but they were both in the same year. They say, these authors say, that there are 4 classes of smooth irreducible mod P representations of G. Okay, so they're the one-dimensional ones. You know, there's a silly representation of GL2QP. You just take the determinant, then you get something in QP star, and then you take a character and eta, you just apply eta to it, you get something in FP bar star. So those one-dimensional representations, eta composed with eta, are always there. But more interestingly, you have the Steinbergs and twists of them. We just did that one. You have what are called the principal series representations for GL2QP, but here it's pi r lambda eta, but the r's are small, but the lambdas have some condition on them. They're not allowed to be plus minus 1 if r is 0 or p minus 1. We just saw when r was 0 and lambda was 1, then that pi 1 0, pi 0 1 1 was not irreducible. So you need to drop some values, some finitely many values of everything's finite anyway, but some values of r and lambda to make that irreducible. And it's not clear why these are called principal series, because it's compact induction, right? But I'll explain that in a second. And finally, by the way, in case 3, I should have said the lambdas are non-zero. And finally, you have the representations with lambda equal to 0. And these turn out to what are called supercuspidals. Okay, so this is a complete list of all the representations of GL2QP acting on smooth representations, acting on mod P vector spaces, this FP bar stuff. And I wanted to say why in case 3 it's called a principal series. It turns out that the compact induction in case 3 is also a Borel induction. And there's a formula there, and the notation for that formula is going to come up in later slides, but I thought I'd just write it. So there's an isomorphism of some kind. Okay. So this is the classification of Barthel-Livna and Breuil. Barthel-Livna actually did the first 3 cases, and Breuil showed that in fact the remaining representations were in case 4, and that they were irreducible in fact. And there was a complete list of things which are not in case 1, 2, and 3 were the ones in case 4. Very simple representations. Okay, so one more word I want to use, and that is the word admissible. So a smooth representation, mod P representation always, is admissible if the invariant vectors under every compact open subgroup of G are finite dimensional. So pi to the k, that's the usual notation of invariant vectors, for k is a compact open, that space is finite dimensional. Okay, so this is a condition that is very classical. It appears in all the automorphic forms language. It goes back maybe to Harish Chandra, who studied this for GK modules, etc. But it's everywhere in the literature. And one can ask whether this property also holds in the mod P setting. Okay, so it turns out that in fact, each of the 4 families of representations in the Barthel-Livna-Breuil classification is in fact admissible. The k invariant vectors are always finite dimensional, and k is a compact open. Okay, and this is a check. You physically just mentally, I mean not mentally, physically check this. You don't have to do a computation. Okay, there's no theoretical reason why this should be true. It just happens to be true. Let me make a remark. As soon as you have an admissible representation, then it automatically has a central character. The center Z has to act by a scalar. Okay, and so this is a nice a remark, a proof of which was explained to me by Sandeep Verma a few days ago. It's very trivial, it's in all books, but I'd forgotten. And what is the proof? The proof is that if you have a compact open and you look at pi to the k, then it's finite dimensional, and any scalar will preserve this space. Okay, so you have now a scalar acting on a finite dimensional space, and everything's algebraically closed, so you'll have an eigenvalue, and you'll have a non-zero eigenvector. And now if you look at the eigenspace, well, that's G stable because Z was central. And if it's G stable by irreducibility, it forces it to blow up and be the whole thing. So basically, Z doesn't just act on those vectors by lambda, but it acts on the whole thing by lambda. So that's why every admissible representation has a central character. Okay, so this is a standard fact in the subject. The classification was originally done for smooth. There's some nice comments I want to make. The classification of Broglie, etc., was done for smooth, initially done for smooth irreducible representation with central character, though I didn't write it there. And the reason is that later Berger showed that in fact every smooth irreducible mod P rep has a central character. So if you put all the facts together on this slide, you obtain the following theorem, which is a mix of some serendipity and various other things. Every smooth irreducible mod P representation of G is admissible. Okay, it's because A, you can classify the ones with central character and they all turn out to be admissible by a physical check. And then some other ad hoc argument shows that in fact, every smooth irreducible does have a central character. And so you get this result. And this is a reflection of a theorem which is sort of well known when you work over the complex numbers, GL2QP, and you're working over the complex numbers. It's a fact going back to Jacquet-Ohl theorem, I think 70s, 80s, I can't remember. So every smooth irreducible representation of GL2QP of the complex numbers is admissible. And we are seeing a mirror of this fact in the mod P worth. So you may ask whether such a theorem is true in general. For example, if you replace, I'm going to do a little bit of an aside because it's quite interesting. So just for 2 slides, I'm going to ask whether this theorem is true for GL2 of a finite extension of QP, even though I haven't defined what they are in this talk. But just bear with me. So the question is every smooth irreducible mod P rep always admissible? So remarkably, it was shown by Daniel Lee that this is false when QP is replaced by a more general p-adic field. In particular, he looked at the following p-adic fields. He looked at the degree F extension of QP. Okay, so QPF is what is called the unique unramified extension of QP. Okay, so this is a generalization of the p-adic numbers, and I won't define it here, but trust me that there's one for every F. In fact, what he did was he showed that there's a non-admissible smooth irreducible mod P rep for GL2 QPF for each F greater than 1. But in fact, he did this for F greater than 3. Okay, of course, for F equals 1, we just said it's not, everything is admissible. But for F greater than or equal to 3, he used these diagrams of Bro and Pascunas. I'm just going to throw a few words around here. As I said, these slides are just a bit of extra information. He used what are called these diagrams of Bro and Pascunas to construct these non-admissible irreducibles. It's a very clever argument, a very short paper in Math Research Letters, and appeared last year. So Bro and Pascunas looked at what are called finite dimensional diagrams, and this is an infinite sum of these diagrams. And then he put some slightly strange action of GL2QP on this diagram and managed to construct these representations, which are non-admissible. His argument doesn't work for F equals 2. So about a year ago, I asked Mihir Sheth about this, and he came up with a very clever way to get around this. So these diagrams that Lee looked at were attached to irreducible 2-dimensional mod P Gal representations, and Sheth decided to look at a reducible split mod P Gal representation. And using this particular diagram, you can in fact give a simpler construction of a non-admissible irreducible mod P rep. So it's very, very heavily false that for more general p-adic fields, GL2QP has GL2F, capital F has the property that all smooth irreducibles are admissible. Okay, so there were a bit of stuff on Gal representation, so that is a good segue into talking about Gal representations. Because these diagrams, it's kind of ironic. You want to study these mod P representations purely on the so-called automorphic side. You want to study these mod P representations of G, GL2QP or GL2QPF, but you have to use Gal representations as a crutch in between to study them. And so that leads nicely into Galois representations. Let me talk about Galois representations now. So I'm going to concentrate on mod P Galois representations, but there will be some characteristic zero Galois representations also floating around towards the end. So for notation, remember QPF was the finite extension, finite degree extension of QP of degree F, and we let its Galois group be GQPF. So these are all automorphisms of QP bar fixing QPF. I need some characters of these Galois groups. So these are what are called the fundamental characters of level F. They're very canonically defined. Notice that there's a lot of notation in subscripts and superscripts and things, but it's quite simple. On the left-hand side, you have a Galois group, and on the right-hand side, you have a finite field, but not with P elements anymore. It has Q elements, where Q is P to the F, and non-zero elements. It's a homomorphism. So today morning, Mahesh said he will not define what omega is. So let me do that for you. Omega is the first fundamental character of level 1. And in general, the fundamental characters of any level F are defined by what is called Brumer theory. You just take a root of minus p, in particular p to the fth minus 1th root of minus p, and if you make sigma act on it, you get the original object up to p to the f minus 1th root of unity, right? Omega f of sigma is a p to the f minus 1th root of unity. So that is it. That defines what omega f of sigma is for every sigma in the Galois group. It's a root of unity, but the roots of unity are exactly in that are canonically isomorphic to FPF star. Okay, so you get a character into FPF star. So in this talk, I'm only going to use omega 1 and omega 2 because everything is two-dimensional. But if you were working with GL3 or GL4, you'd need fundamental characters of higher levels. There's one more character that came up a few slides ago, and I said it'll come up later. So eta lambda is another character of GQP. It takes geometric Frobenius. So that's the more or less the canonical generator. Frobenius P is the generator of the Galois group of QP modulo the inertia group. We take the inverse of that and we send it to lambda. Okay, so unramified means that on inertia it's trivial. So these are the two basic kind of characters that will show up. The omega f's are ramified characters. They're tamely ramified characters, and their eta lambdas are unramified characters. So ramified and unramified. And every two-dimensional semi-simple mod P representation of Galois group of QP can be built out of these things. And here is the, let me write both of them at the same time. Okay, let me do one at a time. So the reducible ones are just direct sums. So you have two powers of fundamental characters of level 1. And in front, you have some unramified characters, eta lambda and eta mu. And then you have also yet another induction, but this is Galois induction from the index 2 subgroup of the Galois group of QP, the Galois group of QP squared, of omega 2 to the c. C is just an integer. Omega 2 was the fundamental character of level 2. You take a power, it's a character of GQP squared, you induce it. So you get a two-dimensional representation, and you can twist it with eta lambda or eta gamma, where gamma is a non-zero element in FP bar star. You can twist these things, and so this is a whole family of two-dimensional representations. So both are two-dimensional, 1 + 1 or 2. Okay, it's said my internet connection is unstable. Can you hear me, Omri?
Yeah, you're clear.
Okay, great. It's briefly flashed on my screen. Okay, so this is a complete list of all two-dimensional representations of the Galois group of QP. And I would like to connect these now to the representations we were talking about earlier. So here is a remarkable map. You know, these Langlands correspondences sound very abstract, but you know, here we're doing everything about P. It's basically some sort of computer science, not really mathematics. Everything is more or less finite and countable, and things like count things and make lists and things. So here's this map from the mod P representations of the Galois group of QP to mod P representations of GL2QP, which I was calling G. So this is called the local Langlands correspondence, mod P local Langlands correspondence. And remember, on the left-hand side, there were two families of Galois representations, the reducible ones and the irreducible ones. So on the reducible ones, there's a direct sum in there, if you can see it. There's a direct sum there. It goes to a sum of those two of the pi r lambda etas, if lambda is not equal to 0. So eta lambda was that unramified character. It was only defined if lambda was not equal to 0. So this is what, you don't have to understand everything here. I'm just trying to give a rough flavor of it, that if you have a direct sum of two characters on the left, you get a direct sum of two basically principal series representations on the right. Unfortunately, they're not always irreducible because lambda could be 1 or something, and then you have to do something else. You have to take the semi-simplification. R prime, it will be defined at the bottom. It's basically P minus 3 minus R. So it's just some flip of R. Okay? So lambda, and then there's lambda inverse and eta, and there's that. And then there's this two-dimensional induced representation, and that goes to a supercuspidal, pi r0 eta, if lambda is equal to 0. Okay, so this is the mod P Langlands correspondence. And as I said, I'll define R prime. R prime is the unique number congruent to P minus 3 minus R in that set, 0 to P minus 2, mod P minus 1. So it's just kind of a shift. Later, right on the last slide, I will use the fact that when R is P minus 2, R prime is just R. Right? If you put in P minus 3 minus P minus 2, you'll get minus 1. So you have to add P minus 1 to that, and you get P minus 2. So R prime is minus 1 is not in the set, so you have to replace it by P minus 2. Okay, so I'll use that on the last slide. So just remember that reducibles go to sums of principal series, and these induced representations, these dihedral representations, two-dimensional dihedrals on the left go to supercuspidal. Everything on the right is infinite dimensional, everything on the left is two-dimensional. Okay, so that's the mod P local Langlands correspondence. Okay, so now let me tell you why I introduced that. So there's a very classical problem in number theory, and that is to study characteristic zero Galois representations and their reductions. So there are certain irreducible two-dimensional representations, VKAP, of the Galois group of QP, which are defined not over QP, but finite extensions of QP. It's not important what those finite extensions are. They're parametrized by integers k greater than or equal to 2. Those are called the Hochstate weights and things, but it's not important here. And certain elements AP, which I said they were defined over finite extensions of QP. QP bar is the algebraic closure. And V is called the slope of these things. And I'm requiring that p-adic valuation of AP, which is V, I'm requiring that to be positive. Okay, so these parameterize basically all irreducible two-dimensional representations of the Galois group of QP. Okay, so you have a representation from GL2 QP, G Galois group of QP to GL2 of a p-adic field. And one thing you can do is you can take a lattice in here and go mod P, and you get its reduction. So you get a mod P representation of the Galois group of QP, and you can ask what it is. Is it of type 1 or of type 2? Is it reducible or is it irreducible? And that question is an extremely hard classical question. And the techniques that one has introduced so far can be used to actually answer that question in some cases. Let me just say that if this looks very abstract for people working in modular forms, the VKAPs are basically the local Galois representations attached to modular forms. Okay, that's what that says there. So they're not something too mysterious, where P is prime to the level, and K is the weight of the form, etc. Obvious notation, AP is the pth for coefficient of the form. Okay, but I haven't defined the representation precisely, just by some notation. So as I was saying, if you have a representation to GL2 of a finite extension of QP, you can conjugate it to lie in GL2 of a finite extension of ZP. And then you can go modular maximal ideal, and you get something in GL2 of FP bar, finite extension of FP, so in GL2 FP bar. So this is called the reduction, and it's only well defined up to semi-simplification because it depends on a choice of lattice, but up to how you conjugate, etc. But we will always look at the semi-simplification of this. The reducibility or the irreducibility of that doesn't change, right, up to semi-simplification. So here's that classical question. This goes back to Fontaine, etc. What is the reduction of these crystalline representations as a semi-simple two-dimensional mod P representation of the Galois group of QP? So Fontaine himself answered this for small weights when k is less than p minus 1. And Broglie invented the p-adic, the mod P local Langlands correspondence to extend his results up to weight 2p minus 1 or something like that. So for small weights, this is known by their work, and it's also known for large slopes, where the p-adic valuation of AP is very large. But it's open in general, and in particular, it's not known for small slopes. So as an application of everything in this talk so far, and in particular of the mod P local Langlands correspondence, there is the following theorem, let p be bigger than or equal to 5, then one can write down the reduction explicitly for all small slopes. Remember, v was positive. This industry was started off by Buzzard G in 2 papers up to slope 1, though they couldn't do slope half initially, and then they cleaned it up later. And then we started looking at things between slope 1 and 2, and Shanli Bhattacharya could do all slopes between 1 and 2 except 3 halves. Meanwhile, the missing case of slope 1 was done also with Rosenstein, Sandra Rosenstein and Ian S. Leon. And finally, this missing case of slope 1.5 was done recently by Vivek Rai, who was a postdoc now at ICER. This is still a preprint. Okay, so how is the BOTP LLC used exactly to answer this question? Let us take a look at that. So before I do that, I'll just make some remarks about, I didn't really tell you what the answers are for the reduction, whether you get something reducible or what. So I'll just make some qualitative remarks that you mostly get something reducible when your slope is integral, like slope 1, but it's mostly irreducible if your slope is between 0 and 1 or between 1 and 2 strictly. If it's fractional slopes, you tend to get irreducible things. And I won't tell you all the characters that you actually get. The behavior at these special slopes, half, 1, 3 halves, these half integral slopes is very tricky. And in particular, when the weights satisfy some congruence condition, these are called the exceptional weights, when k is congruent to 2v plus 2, mod p minus 1, all kinds of hell breaks loose. But now at least there's a conjecture which says what should happen. And it says that there's an alternating sequence of irreducible and reducible possibilities that should occur. And I'll just leave it as a qualitative statement like that for now. But I'll come back to this at the end of the talk. Okay, so and this is a conjecture in general. It's been solved now for 1.5 by Vivek Rai. And finally, I should also say that when one writes things down, one notices some patterns between slope v plus 1 and slope v. And there is a general principle that explains this, which uses Hida families and the theta operator. But this is a talk in its own right. And there, I won't say more about this. This is a preprint with Arvind Kumar. Okay, so let me come quickly in 2 slides. Let me tell you how the proof goes. So there's also a p-adic local Langlands correspondence. Okay, so this is also due to Bro and Berger, etc. But there's a functorial version due to Colmaze in 2010, which associates to VKAP the G representation pi KAP, which is given by a very similar formula, compact induction, and then modulo T minus AP. But this time it's characteristic 0. There's a QP bar squared there. Okay, so you can guess what the definition is because everything has more or less been defined many times now, but it's a little bit slightly different context. It's a characteristic 0 thing. And the point is that the p-adic local Langlands correspondence is a characteristic 0 matching up of representations. It commutes with the BOTP local Langlands correspondence with respect to the process of reduction. So let me explain that. So we have these crystalline representations, characteristic 0-1s, VKAPs on Galois representations. And the p-adic local Langlands correspondence associates these automorphic representations, automorphic size, everything is local here, so but representations of GL2QP, these pi KAPs, right? That's the p-adic local Langlands correspondence. And we're interested in studying the reduction on the left. But you could also look at the reduction on the right, which is now a mod P representation of either the Galois group of QP or of G, GL2QP. And as I was saying, the mod P local Langlands correspondence, which is an arrow on the bottom, it makes this square commute. This is really remarkable. So that very ad hoc definition of the mod P local Langlands correspondence that we saw earlier, given by Broy, is canonical in the sense that it makes this diagram commute. It doesn't matter whether you go over on the top, look at the pi KP and take its reduction, or you go downwards, take the reduction and apply local Langlands, mod P local Langlands, you'll get the same representation. Okay, so this is the basic idea. So if you want to compute the reduction on the left, you may as well compute the reduction on the right. And to do that, everything that I've said in this talk is used, and I will explain that in one slide. So it suffices to compute the reduction on the right, pi bar SSKAP of pi KAP. I should say that this map here, The mod p local Langlands correspondence is injective. So once you know what's happening in the bottom right corner here, you can invert the mod p local Langlands correspondence and come up with what's happening in the bottom left. Okay, so we just have to work on the right-hand side of this square. Just suffices to compute the reduction. And for that, we need to have a lattice inside this huge infinite space. And we take the standard lattice, which is the image of these kinds of functions, sim k minus 2 zp bar squared. These are functions from G to sim to polynomial representations, but the coefficients now are over zp bar, which is the integers in qp bar. Okay, so we look at the image of this thing in pi k ap. And of course, if you reduce this, then you just get the reduction by definition. So notice that there's a natural surjection between int k z g vr and theta bar k ap. So there's a natural surjection like this. And the reason is that if you look at the third line on this slide, theta k ap, then you have this image of this sim k minus 2 zp bar square stuff sitting in there. But if you go mod p, then it'll factor through sim k minus 2 fp bar squared. And remember, that was just VR. The second last line of this slide says that VR is just sim r fp bar squared, where r is k minus 2. So it factors through this thing. So all of a sudden, if you're trying to understand the reductions of crystalline representations, you need to understand the Jordan-Holder factors and the various submodules of VR, which is how I started off this lecture. Okay, so this slide finishes the proof. It turns out that if the slope is fractional, then the above map, this map here, the third last line, it further factors through this quotient Qi. Qi, remember, was VR mod VR to the I plus 1. And then you also mod out by XR minus I. But as we mentioned at the beginning, a complete list of Jordan-Holder factors of Qi is now known for all small values of I. So you have a lot of information now on the left, and this allows you to more or less compute what you have on the right. If you can eliminate some of the Jordan-Holder factors on the left, and this is a very delicate computation with the Heck operator T, if you can cut it down to 1 or 2 Jordan-Holder factors, you pretty much get an isomorphism between the left and the right, and therefore you completely know what theta bar is, and therefore you completely know what pi bar is, and therefore you completely know what V bar is, VK AP bar. Okay, so that's how this works. And as I said, this allows you to compute what VK AP bar is. Similar argument applies if V is integral. This time you don't factor through Qi, you factor through another quotient, which I haven't introduced in this talk, but it's a variant of Qi. Okay, so all well and good, but here's a very important point. Eliminating Jordan-Holder factors on the left is extremely tricky. And that is where the small slope condition is used. It can only be done for small I, or equivalently for small slopes V, because V lies in I to I plus 1. So when I is small, you can eliminate Jordan-Holder factors, and therefore V is forced to be small. That's why we had those small slopes at the beginning, up to slope 2, basically. To show you how tricky this can be, and I'll end in 2 minutes. I'm at the 75-minute mark, which is what I was told to do. There's no way to say which Jordan-Holder factors Ji survive. In fact, I'll just end with this picture. For half integral slopes, V equals I plus a half, each of the 2I plus 1 Jordan-Holder factors Ji seem to occur, 1 or 2 at a time, in the following zigzag pattern. So remember, Qi was basically VR mod VR I plus 1, right? I plus 1 means I plus 1 copies of the theta polynomial in there. And so we break it up into pieces. And each of those pieces has 2 Jordan-Holder factors, J0, J1, and then J1, J2, J2, J3, which are quotients of VR1 and VR2, etc. So what is happening is that when you try and eliminate Jordan-Holder factors, it seems that you first get J0 never appears, but you first get J1, and then after a while you get J1 and J2 both together. Okay, so remember when you have two Jordan-Holder factors together, it's a direct sum of principal series. So you probably get a reducible Galois representation. Then for a while you only get J2, and then for a while you only get J3. So you get these supercuspidals, and therefore you get irreducible Galois representations. But then suddenly you start getting J3 and J4 together. And again, you get something reducible. And then so on and so forth. You get irreducibles because first only J4 appears and J5 appears, but then they appear in pairs. So it's an alternate sequence of single Jordan-Holder factors or pairs of Jordan-Holder factors that appear. And they appear in this zigzag pattern. And then right at the end, this J2I plus 1, which is the last Jordan-Holder factor, it turns out that the R here is P minus 2. So the R prime is also P minus 2 by the remark I made some slides ago. And you have some sort of self, the D is for duality. You basically have pi P minus 2 and pi P minus 2 here. And you get another reducible of a very special kind. Okay, so this is how it looks like God wants us to choose the Jordan-Holder factors. And this is how it has played out in real life up till slope 1.5. And the way the Jordan-Holder factors here are selected depend on the size of an explicit parameter tau. So as that parameter gets larger and larger, you start getting this zigzag pattern. As you vary through the whole range of the parameter, you get all the Jordan-Holder factors here in this order. So it's extremely tricky. It's not like there's one canonical Jordan-Holder factor that survives and you can immediately compute theta bar. All of them play a role in some special cases. Okay, so I will end with that. And here are some references in case you're interested. And so thank you very much.
Thank you, Professor Ghate. That was. I wonder if there are any questions from the audience at this point. So I guess you can type your questions into the chat.
Yeah, there is one question in the chat.
Okay. So I don't have it because I got disconnected in the middle and then the chat got cleared. So maybe can you send it again or maybe just read it out? Okay. So a question on YouTube. What about mod P representations of K where K is a finite, totally ramified extension of QP?
Yeah, so I didn't talk about those in this talk. You can actually, so Breuer and Pascunas have written a book where they actually construct representations of GL2 QPF, where QPF is a finite unramified extension of QP. But they also have some theorems which they have many theorems about that, but they also have some, at the beginning of the book, they also construct representations for GL2K, where K is an arbitrary extension of QP. So they have these combinatorial objects called diagrams. Diagram is basically a K representation and then the normalizer of an Bahori representation, and they're glued together in some way. So they have these diagrams, and they say that basically once you have a diagram, you get a representation which comes from this diagram. I'll be a little vague here. So those kinds of theorems actually work when you have an arbitrary finite extension of QP. But they say a lot more, and for that they need, for example, for the irreducibility of those representations they construct, they need that K over QP is unramified. And I think, so Michael Schein in Israel have some criteria on how to show these things are irreducible when K is totally ramified over QP, but it's not always, I think, easy to carry that out.
Okay, it seems like there are no more questions in the chat, but I had a question, especially in the finite field case. Do you think it's too early to ask about GL3? Have people
Yeah,
tried to look at the...
GL3. I think people have started constructing. Some kinds of the p-adic local lang length correspondences. These kinds of things have started to be done, and people have also people have started work on GL3. It's not like people have not done anything. There are things on GL3,
I was thinking maybe
but there are
just
no,
finite fields,
yeah,
even
there's no mod p local Langlands correspondence, unfortunately, for GL3. Three-dimensional representations corresponding to these things. That is not known yet, I don't think. And so that is one issue if one wants to carry this out. But in individual corners of the squares, people have been working, individual corners of that square. Just relating things together has not been done.
I was thinking specifically about at the beginning of your talk, you talked about mod P representations of GL2FP. And so I was wondering about just that part of it. That may be some
Mod P representations of GL3FP. Yeah, the things must be known. Of course, things must be known. You're an expert on this more than me. Green's theorems and like GL and FP and things over the complex numbers. Yeah.
Yeah, so here, of course, everything's been known for more than 100 years now.
Yeah. I'll have to think a little bit about what the general statements are for GL and FP mod P, whether everything is completely known. I'd be surprised if it is, but I may be wrong.
Okay, let's see. So audience can unmute and ask questions at this point if they like.
I think GL2 finite extension of FP is classified, right? Instead of GL3 FP, if we extend the finite field, and then the similar result works, just like symmetric powers, but with proper tensor.
Yeah, if you have GL2 of FQ, then you can embed, so you can take various symmetric powers, but you can change the action of GL2 FQ each time by applying Frobenius, powers of Frobenius. So you get many, many different copies of symmetric powers, and the tensor product of all those, and then twisting with characters gives you a complete list of the irreducibles. These kinds of theorems go back to Brouwer and Nesbitt from the 50s, 60s, etc., or maybe even earlier, I'm not sure. But this is a complete list of irreducible representations. So there's Q times Q minus 1 irreducibles for GL2 FQ, if you're working mod P.
Okay, are there any more questions? Well, it seems that there are no more questions. So in that case, let us thank Professor Ghate for this wonderful talk. You can unmute your mics and clap, or you can use the virtual clapping feature of Zoom to do that.
Thank you. Thank you very much.
Thank you.
Yeah, thank you, Professor Amri. Thank you for chairing this session.
My pleasure.
Okay, so we can close this session now.
Okay, thank you. Bye.
Tag it aside. Can you hear me?
Can you hear me?
Yes.
Yes, yes.
Yes.
So Somnath, can next time that box appears, can you just click on it and drag it aside? And try to drag it away from the thing.
Okay, just a second. I don't know what happened here.
Then leave it. It's not a big problem.
No, it's not a big problem from my side. I don't know. Maybe it clicked somewhere, something else.
Then just leave it. It's better to leave it.
Yeah,
Anyway,
yeah.
it's not creating too much trouble.
I mean,
Then
yeah. So it's not in the direct way of the visual sort of access. So
yes, yeah.
So let us just wait for 2 minutes, so then we can start after that.
Okay.
Okay.
Yeah, sure. Yeah, let me invite Professor Abhijit Pal from IIT Kanpur. He will be the chair for this session on topology, geometry, and dynamics symposium. Yeah, Abhijit, you can start.
Okay, yeah. So thanks very much, Soumya. So first of all, I thanks all the organizers to invite me for chairing this session. And so today in this evening symposium, so Professor Somnath Basu from ISR Kolkata, so he'll be speaking on and around loop spaces. So Somnath, it's now up to you.
Okay. Thank you. Thank you, Abhijit. And to reiterate what Abhijit said, I would like to thank Soumya and the other organizers, presumably a lot of other people who were in the background while making this successful event, an event of this scale, in the context of this pandemic. So, so thank you for the opportunity. So I would like to talk about my thoughts on loop spaces. And this is going to be the title, as you can see, on and around loop spaces. And I'm going to basically go in a circle talking about a few topics which present themselves in the context of studying and understanding loop spaces. And I'm going to start with, so I mean, these are symbols as of now. Hopefully they'll make more sense as we go along, but I'm going to start with this first topic, which is this quantity, which is nabla gamma dot gamma dot. So that's our starting point. Okay, just a second. So these are called closed geodesics. If you set it equal to 0, then for those of you who have taken Riemannian geometry, a geodesic is defined by the equation nabla gamma dot is 0. But let's take let's take a step back and ask, what is a geodesic in general? Well, in the context of metric spaces or metric geometry, these are what are called locally length minimizing curves. Okay, since we are going to be interested only in the Riemannian context, what does it mean in Riemannian geometry? Well, informally, these are locally everywhere length minimizing smooth curves. So typically these are C2 curves, but we're going to assume these are smooth curves. So this is a good definition in the sense of giving you an idea of what it is, but it's not a good definition in terms of computing things. So how do you actually define a geodesic? Well, there has to be some differential equation that it satisfies. And usually the formalism that you see is that you start with what's called the energy of a path. So here we have a smooth path defined on an interval A to B. I'll call that path gamma. And the energy of the path is defined to be simply you take the velocity gamma dot, take its absolute value or the speed, take its square.
So that's what this inner product gamma dot means. It's the speed square, and we integrate it from A to B. And there's a normalizing factor of half. So this is what the energy of a path or a loop or a curve is. And one can ask, what are the critical points of this energy functional? Okay, and the answer is the critical points of this energy functional are precisely the geodesics. Okay, they actually are locally length minimizing among all curves joining gamma A to gamma B. So if we use the calculus of variations, then there's a formalism called the Euler-Lagrange equations, and the Euler-Lagrange equations will tell you what these critical points ought to satisfy, and it satisfies a system of differential equations of this form. So again, I'm writing my curve gamma t in local coordinates. In a manifold, in a local chart, you can have coordinates x1, x2, xn. So here my gamma t is of the form x1 of t, x2 of t up to xn of t. And these coordinates in terms of t should satisfy these system of equations. So this is like the acceleration of xk. So delta, d by dt2 of xk plus these products of these dxi dt, dxj dt. But there are these constants which should remind you of something that you already know. These are called the Christoffel symbols associated to the Riemannian metric. And given the Riemannian metric, one can write down these Christoffel symbols, which are in terms of derivatives of g. And then one can solve this locally using Picard-Lindelof, and you know that your geodesics exist locally, and they're unique given initial conditions. Okay, so these are what geodesics are. So this is the formal setup, but for those who have not seen Riemannian geometry, well, let's try to see what it is for simple examples. So for Euclidean spaces, the usual Euclidean space Rn with the standard metric, it turns out that metric is flat. So the geodesics, as we know from childhood, these are straight lines, right? Okay. What about spheres? Well, these are spheres, unit spheres or spheres of some radii inside Rn plus 1. Rn plus 1 has the metric as discussed above here. But when you restrict that metric to any submanifold, namely the sphere, what you get is a round metric. It's called a round metric because the curvature is everywhere the same and it's positive. It's actually 1 over r square. And the geodesics on the spheres are nothing but great circles or parts of great circles. And we already know that from our experience in traveling around the globe that the plane tends to take the arc along a great circle, typically when you try to fly from point A to point B. Okay. So what about the hyperbolic plane? Well, this is it's upper half space, but the metric is not the usual metric from R2. The metric is somewhat different. If you have seen the metric, you already know what it is. If you haven't, then you might be interested in looking up what is called the Poincare metric. And this is a metric which is special because it gives the hyperbolic plane a constant negative curvature -1. Okay, so it becomes negatively curved, and the geodesics on the hyperbolic plane are basically going to be all either straight lines perpendicular to the x-axis. So this is the x-axis which is missing, or semicircles which are perpendicular to the x-axis. So these are all the geodesics on the upper half plane. Okay. So one thing you should note is that among these three examples, the only case where we actually get closed geodesics or periodic geodesics or loops which are geodesics is the case of the sphere. In the case of the plane or the hyperbolic space, these geodesics are not closed geodesics. Okay? So one might wonder whether compactness has something to do with even obtaining a closed geodesics or a periodic geodesics. They're used interchangeably here. So that's a natural question that you have. Does compactness ensure the existence of one non-trivial periodic geodesic? And by periodic, I mean it should be a smooth curve, which is a geodesic such that gamma has a period. It's defined over the whole real line. Non-trivial means that we are not interested in the constant curves. The constant curves are obviously geodesics. They satisfy the differential equation that I set up earlier, but we're interested in non-constant geodesics. So that's what I mean by non-trivial. So, okay, so that's the question. So if I ensure compactness, does it mean that I always have a non-trivial closed geodesic? So let's see. So to talk about geodesics further, I have to introduce one of the objects already appeared in the first slide. This this object called LM. So L stands for loop. So LM, this we're going to call this the free loop space. And what is this? Well, this is nothing but the space of all continuous maps from the circle to the manifold M. So for those of you who have seen a bit of topology, you know that this space has a natural topology which on it called the compact open topology. And so it is a topological space. Okay. And we are interested in this space simply because we are looking for closed geodesics. And closed geodesics are simply going to be some special curves in this space, right? So we are not interested in random geodesics which are defined over an arbitrary interval. We're interested in closed geodesics. There's a cousin, which is the smooth version of this, which is denoted by script LM, which is all piecewise smooth curves from S1 to M. Okay. So this is slightly better behaved in terms of doing some sort of infinite dimensional analysis and so on. It turns out that these two spaces, the continuous free loop space and this smooth cousin, they are homotopy equivalent. Okay. However, as I said, each one has its own advantages in terms of what you want to do at that point. If you want to do more geometry, maybe script LM is better. If you want to do more topology, algebraic topology, maybe LM is better suited. Nonetheless, the closed geodesics live inside both of them. Okay, there are special curves in here. And in fact, if you go back to the first slide, we talked about the energy functional, and the energy functional is still defined on either of these two spaces, right? The point is that the energy, I mean, it's definitely defined on the latter one, because this is piecewise smooth, hence piecewise differentiable. And we want the critical points of the energy function to be the geodesics. So we are really in secret trying to study the energy function on this infinite dimensional space, which we cannot as of now. So let's see what happens when, so having said that, let's see what happens when M is compact. Well, when M is compact, it turns out that there is a chance that you can get a non-trivial closed geodesics. So there's a topological argument that if pi1 is non-zero, then there's something called curve shortening, that if you choose a non-zero element in your fundamental group, choose a curve representing that element, and try to basically represent that curve by other curves which are homotopy equivalent but having smaller and smaller length, and you shorten the length, and if you can obtain a curve which realizes the shortest possible length, then it turns out that curve is indeed actually a smooth curve and actually a geodesic. So this is Birkhoff's famous curve shortening process, and this tells you that you will always find non-trivial geodesics if you choose a non-trivial element in pi1 which relies on the fundamental group being non-zero. But this process wouldn't work if the manifold is simply connected, because you simply do not have any non-trivial loop, any non-trivial element in pi1 to begin with. The only element that you can choose is the trivial loop, and the trivial loop is represented by the constant geodesic, which we don't want. So then Morse theory comes to the picture, and Morse theory helps you prove that indeed if M is compact and pi1 is even if pi1 is 0, there is going to be a non-trivial closed geodesic in every component of LM, actually. So LM will have lots of components. In each component, you're going to find a non-trivial closed geodesic. And this is basically a line of reasoning following Morse, where he introduced Morse theory, the theory that bears his name these days. And one of the applications of that theory was this. Okay, we'll talk about some other applications later on. Okay. However, if you think that, okay, all of this is nice, just take this simple example. This is like a bumpy sphere. Okay, just imagine that you took some actual old cricket ball and then you know, like dipped it inside some like warm chocolate or warm mud, and then you pulled it out and it had all these peaks and bumps and so on. And I couldn't draw as many peaks as I wished, but imagine that there are way more peaks of different heights and different sort of radii. And so now imagine yourself being a traveler on this bumpy earth, so to speak, and then you're just trying to start at a point, and then you're traveling along a geodesic and hoping to come back and close it up. And if you imagine for 1 second that you can close it up, you'll see that at every point you hit one of these peaks, you cannot really go up the peak, because that wouldn't be locally length minimizing. You have to go around the peak either right or left. But if the peaks are sufficiently, you know, like densely placed, you have to always make a choice of right and left, and then by the time you come back to somewhere close to where you started, you might have already taken a different direction and gone another way, and it's conceivable that you may not actually even close up. Okay, so the question being, can you spot a closed geodesic here in this S2, meaning this is topologically an S2, that's pretty clear, but the metric is the metric induced from R3. So it's not the standard S2, obviously. Okay, so these kind of examples are right in front of you. So let's keep it at that. Let me ask a different question. Does there exist infinitely many periodic geodesics for any metric? Okay. So I should be clear here. When I say periodic geodesics, I obviously mean distinct periodic geodesics. Okay, so if I take a geodesic gamma and gamma square, they of course give me the same. They of course give me the same. You know, I would call them the same geodesic because the image of gamma and the image of gamma square are the same. So I mean distinct periodic geodesics, and I'm asking whether there are infinitely many of them. Forget one of them. Okay, so it's an even stronger question. Fortunately, the answer in some of the cases is in the affirmative. Okay, so allow me to move on to the next slide. So this is the first affirmative answer in this direction by Gromol and Mayer, where they use equivariant Morse theory to say that yes, this is true for any metric if the manifold is simply connected and the manifold is closed. So closed, let me remind you, means it's compact and without boundary. Simply connected already means it's oriented. And there's this condition that the Betti numbers of LM, namely you look at the singular homology of LM or the singular cohomology of LM, take its dimension. So these are the Betti numbers of the free loop space. This is LM. This sequence has to be unbounded. So it basically boils down to knowing how to calculate these things and checking whether these are unbounded at all. If that happens, then yes. Okay. So in general, how do you even check something like this is true? Well, the follow-up result of Vic Poirier and Dennis Sullivan from '76, this used rational homotopy theory, tells us that if your cohomology ring of the manifold, so this is H dot, so H upper dot means this is the direct sum of H0, H1, H2, this is the whole graded cohomology ring. So the cohomology groups of a manifold or a space form a ring using the cup product or the wedge product of forms. And if this ring requires at least two generators as a ring, then the answer is yes. Okay, so this is something that is easy to check, right? So for example, if you take spheres, the cohomology ring of a sphere is generated by one element. The cohomology ring of CPN is generated by one element. So these do not fit into this category. Okay? And in fact, for a sphere, one can show that the Betti numbers of LM are actually not unbounded. So for spheres, neither one of these two theorems apply. Okay. So, and then Lambrecht later on actually modified this for specific connect sum operations. So you can do a little bit more, but you know, the question remains, what about S2, right? I gave you an example of this bumpy S2. So is it true that there are non-trivial closed geodesics there? So it has a long history. I think in 1927, a group of people claimed, I think Fate and Lustenik and maybe others claimed that there is at least 3 non-trivial closed geodesics on S2, but it was incomplete and things took a long time to settle. And then in '93, using works of Franks, Bangert, and then independently Hingston showed that yes, there are infinitely many distinct periodic geodesics for any metric on S2. But their proofs was not just using differential geometry, it was using dynamical systems and ideas from those fields as well. So it's true. Okay. Okay. So this brings me to one point of confusion, which is often there in the interface of differential geometry and algebraic topology, especially in this context, that whenever people talk about this dimension of HK of LM, sometimes there's a chance of confusing this LM with this particular space, omega M. Okay. And what is omega M? Well, omega M is called the based loop space. That's another object in our study. It's based because these are not all maps of circles to M. These are all maps of circles to M which start and end at x0. So it's just a smaller subset, okay, much smaller subset. So the space of loops is much bigger. Here we're asking the loops to start and end at x0. So there's a confusion because this space and the free loop space are completely different. And usually you can have a hold on what the Betti numbers of these are if you know it for M, but you cannot really control anything about LM in general. So these two are quite different objects, okay? But for some reason there was some confusion in the literature and otherwise, and so if you replace this answer or theorem of Bromall-Meyer with Betti numbers of omega M, then this theorem is of course not true. So this is an entirely different thing altogether. But how does this base loop space enter the picture? Well, let's do a simple map. Let's take this map evaluation from the free loop space to M. What does it do? It takes a loop and it sends it to its image at 1. So it just looks at the base point of the loop, right, where it starts and ends. So this is it's a smooth map, and it turns out this is locally a fiber bundle, or is locally a bundle. If you have seen bundles, then this simply means that locally LM looks like M cross this thing, okay? And what is evaluation inverse of X0? Evaluation inverse of X0 is going to be precisely omega M, all loops which start and end at X0. Okay? So by saying it's a fibration, I mean that LM locally looks like M cross omega M. So of course, omega M is secretly X0 here, but for any X0, I get different omega M's. They're all homotopy equivalent. They're all loops based at different points, but you can go from one to another. Okay. All right. So let me continue talking about base loop spaces. So base loop spaces basically is due to seminal results from the late 1950s. Bott had done some work, and among those it includes Bott periodicity, and he proved pi2 of a Lie group is 0, and he also introduced more spot theory. On the other hand, in homotopy theory, the base loop space is a central object of study. Okay, it's just an important object there, and there are various properties that one uses. Okay, that there's an adjunction, which if you haven't seen, it's fine. This is something very useful. Switches the homotopy groups of X to homotopy groups of the base loop space, and it's an H space. Okay, so H space means it has some extra structure, meaning it has a multiplication map. What is the multiplication map? Given two loops, you concatenate, right? Okay. What is the dual map or the co-algebra map? Well, the co-algebra map is simply the diagonal map. Given a loop, you just take alpha comma alpha. This diagonal map exists for any space. A goes to A comma A. So these two maps combine in a nice way and form what is called an H space. And in fact, if you have seen this example, if you take homology of this space, which you can always, it turns out to be much more than just a co-algebra. It's actually a half algebra, because all these maps combine in a nice way to give you a lot of structure. It's an algebra, it's a co-algebra. The co-algebra map is compatible with the algebra map in a certain nice way. Okay, so there's this slide that I would want to just maybe briefly go through. So since we talked about homology, I want to talk about the chain complex which gives rise to homology, right? So homology comes from chain complexes, for those who have seen algebraic topology. So this is just a singular chain complex. Delta is the usual boundary map. If you take its homology, what you get is the homology of omega x, right? So one can check that this boundary is actually compatible with the multiplication map. And I mean, I hope you'll trust me when I say this. So that's what this means, that you can multiply two chains and then take boundary, or you can take boundary in this fashion and then multiply, it will be the same. All that means is that the homology of omega x becomes what is the half algebra. So it incorporates all these extra structure of M and delta. Okay, we'll use this later on in a moment. So this is what I was talking about. So this is the Pontryagin product, right? Which is the usual product of loops. Alpha times beta is alpha travel twice as fast, beta travel twice as fast. So you have all seen in a course in algebraic topology that if I take three loops, I can combine them in either of the two fashion, and these are homotopic. But these are not homotopic. So yeah, just forget the last line, it's a glitch. Just focus here. So this is alpha dot beta gamma, and this is alpha dot beta dot gamma. And a homotopy would be a way of going from this loop to this loop, parameterized over interval 0, 1. So there are several choices. This is one choice. Why is this a choice? Because at every S, I basically give you a subdivision of the interval 0, 1 into 3 intervals, and I use this much length for alpha, this much for beta, and this much for gamma. And this is a homotopy between these two loops, right? But there are lots of choices. This is another natural homotopy. So you have to make a choice. When you say these two are homotopic, to make a choice, assuming you have made a choice, what you get is a map from the interval cross 3 copies of omega x to omega x. Why is that? Because every point in the interval, which is S, gives me a way of subdividing 0, 1 into 3 intervals, and that gives me a way to combine 3 loops into 1 loop, as the picture suggests. So what about 4 loops? How do I combine these 4 and these 4, and how many ways are there? It turns out there are 2 different ways to do this using this fixed choice, and they're both homotopic. So let me show you this picture. Okay, so there's the picture, and you can have a look at it while I speak. So you can go from the left bracketed system to the right bracketed system, either by using the M3 that we have defined in 3 moves, or by using M3 using 2 moves. And these are 2 different ways of going from the left bracket to the right bracket. But these 2 ways are again homotopic amongst each other. So which means is that this entire pentagon can be filled in. What does that mean? Well, that simply means that there's a map defined over this pentagon cross 4 copies of omega x to omega x. So K4 is just a notation for this pentagon. Okay. So K4 is just the convex polyhedron which governs how many ways you can combine 4 base loops. It turns out in general there are these objects called Kn which govern how many ways you can combine n base loops, and I'll call them Kns. Okay. So this brings us to the next topic, which is what are these Kns and what kind of a space is omega x? It has way more structure as it seems than just being able to combine things one way, because the next time you'll try to do this, you'll see there are 5, you will take 5 base loops and you'll see how many ways to combine them and what are the objects that we get. So this is what leads us to associative up to homotopy. So this is a definition defined by Jim Stasheff in the early 60s, motivated by this study on H spaces and base loop spaces. So he calls this an AN space. What we are interested in are going to be A infinity space, which is an infinity here, as you saw in the first slide. So an AN space is nothing but a space X and a family of maps Mi from Ki cross I copies of X to X. What are Ki's? Well, Ki's, you have already seen the first 2. K2 is a point, K3 is an interval, K4 was a pentagon, and then K5, we don't know what it is, and then there are K6, K7, and so on. Okay. So the important thing is M2, the first map, is really a map from X cross X to X, because K2 is a point. So M2 has to be a multiplication with a unit, but everything is up to homotopy. Okay, so the unit is up to homotopy. The multiplication is just a multiplication. And then there's a third condition which looks a bit obscure, but this is how it's presented in Stasheff. And because algebra is always typically bereft of pictures, but what this says is something very simple. It says these Ki's are actually somewhat, like prescribed. So if you take any Ki, then each Ki in its face will have things of the form Kr cross Ks. And this is just saying that if you restrict the Mi onto the boundary of Ki and combine them, it's amounting to asking, like computing the Mi's on using the previous data. So let me give you a picture instead. So K2 is just a point, and you get a map from X cross X to X. What is K3? Well, K3 is just the associator between A dot BC and AB dot C. What is K4? We already saw that picture. This is what K5 looks like. Okay, so if you take K5, then you look at 5 plus 1, that is 6. And then the faces of K5 are going to be either K2 cross K4 or K3 cross K3. So what is a K2 cross K4? A K2 cross K4 is nothing but a pentagon. A K4 cross K2 is also nothing but a pentagon. And a K3 cross K3 is exactly a diamond, because K3 is an interval. So you see 3 diamonds as the faces and 6 pentagons as the faces. So this is exactly, if you go back and think about it, this is exactly a compatibility condition, saying that the MIs are not independent. The MIs restricted to the boundary should be defined in terms of the previous MIs in the appropriate sense. Okay. Okay, so it has some nice pictures, and these polytopes, by the way, are called Stasheff, like polytopes or Stashev associahedra. It was rediscovered by him in the 60s while he was working on these things. It was earlier discovered by Tamari when he was working on Tamari lattices. Okay. But to come back to our A infinity setup, what is an A infinity space? Well, it's a space where these mj's exist for all j. So m2, m3, m4 all the way. And examples, of course, groups are examples because it's associative strictly, so you don't need any higher correction homotopies. Monoids and base loop spaces, obviously. Okay. And I'll sort of leave you with this quickly because I want to get to the other main point. So an important result of Stashev is that if you want a characterization of A infinity spaces, namely if I give you a space and ask you to check if it's an A infinity space, how do you check it? So he proves that a space is an A infinity space if and only if it is homotopy equivalent to a base loop space. In fact, this X can be defined in terms of Y itself. So effectively, up to homotopy equivalence, an A infinity space is as good as a base loop space. That's what he's saying. So omega X is the prototypical example. It's also in some sense the only example. Okay. But the key thing that was observed by his work is that associativity is not a homotopy invariant. So if you like homotopy invariant things to work with, associativity is not a homotopy invariant. For simple reason, if you take a homotopy equivalence between two sets, one is a group, the other one is just a set, use the homotopy equivalence to transfer the structure. The structure that you get on the set is not going to be a group anymore, in the sense the multiplication is going to be associative up to homotopy and higher homotopies and so on. So that's what we mean by this, okay? But you do want to transfer structures. So what you want to work with is the notion of A infinity or associative up to homotopy, but not strict associativity. That's the key upshot of all of this. And then this went into several directions. There was work by Boardman and Vogt and May, initiating works by others in the topological setting, how to recognize iterated loop spaces. And then there was the direction of proper adds and other homotopy algebras. So A is not the only alphabet that you can use. You can use C infinity, C for commutative, L infinity, L for Lie, and so on. Okay, so it has a huge history and it has a strong imprint on mathematical physics as well. So that's a direction which this has taken a strong stride towards. So, but just to give you one point of view for those who are algebraists in the audience, we often take homology and cohomology of spaces. So what about homology and cohomology of algebras? Well, it turns out there are certain theories of cohomology and homology for algebras. And so, associative algebras are usual algebras without a differential, but sometimes we talk about DG algebras. So G stands for graded. Like you can take the example of differential forms. There's a grading, there's a de Rham differential, and there's a wedge product. So it's a differential graded algebra, right? So DG algebras means that. And then you can take chains on the base loop space. That's also a differential graded algebra, not an associative algebra. Okay? The point is that for associative algebras or even A infinity algebras, there's a notion of homology called Hochschul homology and a notion of cohomology called Hochschul cohomology. And this has its own origins. Let me not get into that, but there's a result due to Burgelia and Fedorovich and Goodwillie. So just take it as a black box, whatever these things are, okay? Like cohomology theories, the Hochschul cohomology has nice algebraic properties like cup products. The Hochschul homology does not have these cup products. Just comparing with the standard homology. But in 86 and 85, in a way simultaneously, Burgelia, Fedorovich, and Goodwillie, Tom Goodwillie, they proved that there are isomorphisms of graded modules, namely whatever this black box is, the Hochschul homology, the kth degree of this algebra, the chains of the base loop space is nothing but the kth homology of the free loop space. Remember, this Betti number was something we did care about at some point in the beginning. So although this might be hard to compute, this is saying that the kth Betti number of LM can be recovered if you knew how to compute the Hochschul homology of the chains of the base loop space. So this gives you some connection why we might care about the Hochschul homology or cohomology of C star of omega x, okay? But again, this is just for every k and there's no extra algebraic structure on either side as of now. But keep this in mind, we'll come back to this, okay? So this brings me, so this connection brings me back to the fourth object of my talk, namely the free loop space, which we already talked about. So the free loop spaces, remember, is all maps from circle to M with a compact open topology. Well, you should also recall the fibration that we talked about. We talked about the evaluation map, takes a loop, sends it to its base point, gamma goes to gamma 1. And this is written in this way. This simply means that the inverse image of a point is simply the loops based at that point. And LM should be thought of as a union of these omega m's, all loops based at different points as the point varies over M. That's a picture. Okay, excuse me. So we would like to define some sort of algebraic structures on the free loop space. So you can be naive and say, what can we do? Well, we could do what we did for omega m, take two loops and just concatenate them. But if you think for a minute, you cannot do that in the free loop space, because if I take two arbitrary loops, they may not start at the same point. So concatenation doesn't even make sense if two loops start at different points, right? So what can I do? Well, I can try to do this in families, because on M, I can intersect families transversely. This is what transversal intersection does. On omega M, I can combine families if they start and end at the same point. So I want to combine these two operations. So I start with families. So alpha and beta are families of loops. Alpha is an I-dimensional family. Beta is a J-dimensional family. I look at evaluation alpha, evaluation beta. So what are they? They're simply the images or the shadows of alpha in M and shadow of beta in M. So these will give me I and J-dimensional families in M itself. Inside M, I can put them in general position, intersect them transversely, and get a I plus J minus D-dimensional family, because D is my dimension of M, right? So if I take a generic I family and J family of, the I-dimensional and J-dimensional like subset inside M, intersected transversely, its dimension is I plus J minus D. And for each of those intersection points, I could combine the alpha loop with the beta loop, because now I can use the fact that they both start and end at the same point. What I get is a I plus J minus D dimensional family in LM, right? So I hope this. So I mean, here's a picture. If what I said is not convincing, just imagine a blue family of loops, which is a two-dimensional family, and the green planar region is the base point evaluation alpha, and here's this orange family, a one-dimensional family of loops, and this brown line is evaluation beta. And clearly the brown line intersects the sheet exactly at one point, namely this point. And I can combine the blue loop followed by the orange loop. What I get is one single loop. It's a zero-dimensional family. So it's just a point in LM, but a point in LM is a loop. So that's a picture. Okay? So of course, one has to be a little careful, make all of these things precise, because you have to make things transverse, combine them. This can be done. So this is the theorem of Moira, Chas, and Dennis Sullivan in '99, where they prove that the loop product defines a graded commutative associative algebra structure on H dot of LM. Okay, so this is the paper which was seminal in the sense that it kickstarted this field of string topology, which is basically the study of algebraic and differential topology of free loop spaces. So it has a product structure called the loop product, but you have to do it with families. You cannot do it, point by point. Okay, so we'll see what this is in a moment. So this is nice. Okay. So it combines, as I said, the Pontryagin product of the base loop space along with the intersection product in the base manifold, because you're really combining both these things. And you can check that this algebra has an identity, the class of constant loops. But there are further structures. Okay. So what are these further structures? Well, remember there's a circle action on the loops. You can take a loop, you can rotate a loop and then map it in. So gamma is a map from S1 to M. You could pre-compose with a rotation and then map by gamma. So that gives you an action of the circle. I mean, physically, it just means you rotate the loop before you map it in. As simple as that. So that actually induces an operator delta from HK to HK plus 1. This is called the BV operator, as you'll see. But this has two properties. One is del square is 0. This is a nice bit of exercise in algebraic topology if you want to think about it. And there's this mysterious 7-term relation. This one term equals these 6 terms on the right. So for those of you who like algebra, you might have encountered this. For those who haven't, this might be very, very mysterious. This doesn't even look anything remotely like things you might have seen. This has a geometric sort of meaning and a geometric origin. Maybe I can talk about it later if there's time. But such an algebraic structure has a name. It's called a BV algebra. Butlin-Vilkovisky, named after two theoretical physicists who were studying these structures even before they were defined here, based on their interpretation of some physical phenomenon. So anyway, so what we get is this structure. So we have all these structures. So the question is, can we compute some of these things? What can you say about these structures? Are they homotopy invariants? What other invariants can we get? Okay. But before that, let me just throw in a question. The question is the following: that remember I said that the Hochschild cohomology of A, where A is an associative algebra or a DG algebra, has a lot of algebraic structures. One of the algebraic structures that appears in the Hochschild cohomology of an algebra is that it has a canonical BV structure. I didn't say what it was then, but I can say it now. So whatever this structure is, and remember there is some identification between the Hochschild homology of the chains of the base loop space along with the homology of the loop space. But now we are saying that the homology of the loop space also has a BV structure. So it's quite natural to ask, can one somehow reconcile these two structures where A is the chains on the base loop space? Because this is somewhat algebraic, and this is something coming from the construction of how you rotate the loops. So this is a question which maybe we'll address later, okay? But it's there since we discussed BV. Okay, so of course, in terms of computations, not much is known about computing this, even if you ignore the BV operator. There are a few computations on spheres and CPNs, and perhaps a little bit more, mainly due to Cohen-Jones and Yan, but nothing more. Okay, so one would still like to compute more examples. On the other hand, if you are looking for interesting sophisticated invariants, then the theorem of Cohen, Klein, and Sullivan says that this loop product dot is a homotopy invariant. So you cannot expect non-homotopy invariants through loop products. Okay. So in fact, one of the original motivations of defining this loop product and string topology was to come up with non-homotopy invariants. But this theorem says that the loop product is not the place to look for that. Okay. So how do we search for non-homotopy invariants? That's a question. And I'm going to give you a template, but this is still a bit imprecise, like most templates are. You have to work through the details and see what you get. One way to do this would be to incorporate geometric constraints into the space you're studying. So you don't want to study the full loop space. You want to study certain subsets defined by geometric constraints with the hope that you extract non-homotopy invariants or geometric invariants, not topological invariants. Okay? So here's something that I could do. You could take a loop. A loop is nothing but the upper hemisphere of the circle and the lower hemisphere of the circle, both in tandem mapping to M. But I could imagine this map as a map into M cross M, where I map both these two strands simultaneously, right? So I just take gamma of t and gamma of 1 minus t and map it simultaneously. What I get is a curve in M cross M, starting and ending on the diagonal. So this is the picture. So once I have this picture, I could basically now say, okay, I don't care about the loops here. I only care about arcs in M cross M, starting and ending on the diagonal. And I can impose certain constraints, like I want the arcs to be perpendicular to the diagonal when it hits it, or I want the arcs to be in a specific direction to the normal when it hits it, and so on. So I could impose all sorts of extra constraints on the arcs when it hits the submanifold, and the submanifold could be something else. It need not be the diagonal submanifold. I could enlarge this game quite a bit, but then the problem is you have to define a theory which involves how to split the strings, how to glue the strings, what is the analog of the loop product, how does the circle act, and so on. So one has to work through all of those details. And there are some instances where this has turned out to be interesting and important. So this has some chance of being true, but one has to work in the specific context. So you have to essentially modify LM to be something inspired from geometry. Okay, so yeah, I mean, if there are questions later on, I'd be happy to talk more about this. But there's one other thing. So the circle action, remember, acts on the loop space. So for those who have seen equivalent homology, whenever a group acts on a space, you can talk about the G equivalent homology of that space. So whatever that is, we are going to focus on a very simple aspect of this. So you take again two families of equivalent loops. So equivalent loops means these are directed loops, but equivalent means that there is no base point. So the base point is gone. So any point is as good as a base point. Okay. So what can I do? I can put markings everywhere. So any I-dimensional family creates a I plus one-dimensional family because I've put a marking everywhere. So each equivalent loops gives me a one-dimensional family, a circle worth of equivalent loops. I can intersect these using the loop product. I get a I plus j plus 2 minus d dimensional family of actual loops, and then I ignore the marking. Okay, I ignore the marking. What I get is an equivalent family of loops. I denote this by bracket alpha beta. So again, as before, this has to be done carefully and precisely to show that this is well defined, but it can be done. And the theorem of Chas and Sullivan says that the equivalent loop homology, whatever this gadget is. So in case some of you may be confused, this is not the homology of LM quotient out by the S1 action, okay? Because that is true if the action is free, but the S1 action on the free loop space is not free. So this is something else altogether, but this turns out to be a Lie by algebra. So it's a Lie algebra, and there's a co-product which satisfies the co-Jacobi and so on. I'll give an example of that in a minute. But it's something more than a Lie algebra, but in particular, it's a Lie algebra of degree 2 minus d. Okay, so it's a nice bit of structure that you see coming up if you go to the equivalent settings. Okay, so the question is, okay, what is this structure? We have defined some abstract things without much pictures or without much insight into how these are well defined. So let's take the simplest possible route. Let's do it for surfaces. Okay, so what should this be for surfaces? Well, M is a surface. D is equal to 2, D is the dimension of M. So this is 2 minus 2, so this is degree 0. So what you get is a Lie by algebra of degree 0, meaning you have a bracket, a co-bracket, they're compatible, and it determines something on whatever these objects are. Okay, so let's see what that is. So that brings me to my last object in the study, which is sigma, the case for surfaces. So sigma, as usual, is going to be closed, connected, an oriented surface of genus 2 or more. I'm not going to stick to spheres or the torus. Torus can be handled easily, and the spheres, because of being simply connected, can be handled by other means, and it doesn't fall into this sort of family of results. Okay, so one thing most of you would know, at least those attending the topology session, is that any such surface is an example of a k pi 1, meaning that there are no higher homotopy groups, right? All these Riemann surfaces. And one can show that the components of the loop space, so the loop space will have lots of components. The components are indexed by free homotopy classes or conjugacy classes, if you like conjugacy classes more, they're equivalent. In fact, one can show that the components of this are homotopic to circles. So they are fat, but they are basically look like circles up to homotopy. Okay. And one can in fact calculate the equivalent homology of this, whatever this is, just from definitions with a little bit of work. Show that with rational coefficients, the equivalent homology is concentrated in degree 0 only. So all the extra degrees are no longer relevant for us. Okay. So what are we asking? We're asking what is this Lie by algebra structure on whatever this quantity is. But just take a minute and think about what this quantity is. What is this? Well, this is the 0th equivalent homology of L sigma. But forget equivalent. What is the 0th homology of L sigma? These are just points in L sigma, path components. And equivalent means you just take an element of L sigma, remove the marking. That's all. So these are simply directed, unmarked loops. But we are allowed to work in L sigma. In L sigma, any two loops are path connected if and only if they're freely homotopic to each other. So we're really looking at free homotopy classes of loops. So this space is nothing but the vector space generated by the free homotopy classes in pi 1 sigma or the conjugacy classes in pi 1 sigma. Okay? So it's just that thing. You take the pi 1 sigma, take its free homotopy classes or conjugacy classes, take the free vector space generated by those elements. So what we get, we should be getting a Lie bracket and a co-bracket. So instead of defining it formally again for you, let me show you in terms of a picture what we get. Okay. Hopefully that will convey more than, because I already said what it is in the abstract setting. So this is due to Goldman. So by the way, so the string topology gives you these things, but the study of string topology or loop spaces by Chas and Sullivan is motivated by the works of Goldman and Turaev. And this is what motivated them to generalize it further. So this is the beginning point, that Goldman in '86 showed, among other things, that if you take two curves which are placed in general position, the red curve and the blue curve, it has double intersection points and the surface is oriented in a clockwise manner, meaning that the normal points inward if you take the right hand rule. At every point, you go and see what is the orientation given by A followed by B. Well, it's clockwise here, so there's a plus sign. It's clockwise here, there's a plus sign. And now what you do is you start following the A curve until you come back to the A curve and then you follow the B curve. So you can only resolve it one way exactly to get an oriented curve. And these are the two pictures that you get. So the Lie bracket of these two curves will be this curve plus this curve. Okay, and these are oriented curves, but these are unbased. That's why there's an arrow and no starting point. Okay, and it turns out this will be a Lie algebra. Okay, so what about the co-algebra? Well, the co-algebra by Turaev is something similar. You take a loop and you split it into each of its double intersection points. So if I split it here, I'm going to get these two. If I split it here, I'm going to get these two curves. Okay, and of course you have to skew symmetrize these things appropriately, but you can do that. So that's what Turaev does. And if you combine these two things, modulo some details that I'm going to skip, you're going to get the Lie bialgebra that was described in the abstract string topology setting, but specialized to the case of surfaces. Okay. So, I mean, these are nice pictures that you can think about and recover the other things. Okay. Okay. So just one more slide and I'm done. So the Lie bialgebra is associated to surfaces. There has been work on this by a lot of other people in different directions in combinatorial topology and connecting probability with self-intersections. Very nice works. But connecting it all to the Hochschild cohomology, there was a result by Weintraub, which says that if M is a KG1, our surfaces are examples of that. The Hochschild cohomology of the group ring. So KG simply stands for the group ring where K is a field. The Hochschild cohomology of this algebra is isomorphic as BV algebras to the homology of LM as BV algebras. So this was the thing that I was hinting towards. So if you replace this with cohomology and not homology here, then this is an algebra, this is an algebra, it's an isomorphism as BV algebras, which is very nice, right? Provided K is, let's say, Q. But this is very specific to manifolds of the form KG1, not for other kinds of manifolds. Okay. But finally, let me take one full circle and finish up where we began. We started off with closed geodesics, and let me finish on a simpler note by asking, okay, what are the closed geodesics on the surfaces that we have been talking about? Well, our surfaces are genus 2 or higher, closed oriented, so you can put a negatively curved metric on sigma. In fact, you can put a metric of constant curvature -1. For each free homotopy class, you can find a closed curve in that class, which minimizes the length. And this, it turns out, is unique because of the negatively curved property. And this is also a geodesic. That's what Borkhoff is telling us. So in fact, for every free homotopy class, there's a unique geodesic in that class. Okay. So we know what closed geodesics look like on surfaces, provided you choose nice enough metrics. Okay. So this brings me back to where we started. So thank you for your attention. So we can't hear you, I guess.
Yeah. So thank you, Somnath, for this wonderful talk. And so now any questions? So please ask Somnath.
I have a question. Yeah, can you hear me?
Yeah.
Yeah. So the Weintraub result, when you said M is KG1 and the Hochschild homology is isomorphic to the loop space homology, is there one equivariant version of this? Because if I remember, Hochschild homology sort of admits also
I see. So there might be. So I guess, yeah, they have. So the Hochschild thing has this cyclic action, and so usually you want to replace the cyclic action. I mean, corresponds to the circle action on the loop space side. So I am not aware of any result on that note for the KG1 spaces. I mean, but it's I mean, now that you point out, it's definitely probably something that one should think about, and I am not aware of any such results. But if there is such, I mean, that would be very interesting to note, actually. But on the other hand, if you see, I mean, I guess the main point would be to look for what it does for KG1 spaces, because for surfaces, the Goldman bracket over Q, for example, is
Sheila, so I think this is Sheila. So can you mute yourself?
Kevin, sorry.
So I
Okay.
mean, on the Goldman bracket side, I guess the Lie algebra, there's still a lot of things that one would like to sort of say anyway regarding characterizing what are the structures and so on. But yeah, so I mean, your question is very interesting and very important. But I mean, I'll think about it. But I don't know of any reference that comes to mind. Yeah.
Okay. Okay. And another one, you said that earlier you stated a result that if you can compute the Betty numbers, then probably you know that there is a closed loop, right? Closed geodesic, if I remember correctly.
Yeah.
So does this extra structure helps you to compute the Betty numbers in some way?
No, does this like, can you say that again? Does this?
So earlier you said some result, if I remember correctly, that if the Betty numbers are unbounded.
Yeah, right.
Yeah.
So yeah, so that is Gromol-Mayer's result. So the point is that usually to say that the Betty numbers are unbounded, you need to have some techniques. So one technique one could try is like take a rational, model of the free loop space from rational homotopy theory, try to write down the generators relations and then compute it. But that typically gets out of hand very soon. On the other hand, if you go by this dictionary of Hochschild homology or cohomology, then one could try to compute the Hochschild cohomology of an algebra. But even those computations are usually very hard. But there are some computations regarding bounding or unbounding the Betty numbers of LM, but it usually requires a combination of techniques either from homotopy theory or from rational homotopy theory or homological algebra. But some amount of these things are known. Say in 4 manifolds or highly connected manifolds, one knows that these Betty numbers are unbounded, and hence they have infinitely many distinct periodic geodesics. So, but not in the general case. There are some conjectures of Gromov regarding that, but I think for the most part that is open.
Oh, okay. Thank you. Thank you.
So are there any other questions? Yeah. So I think this is Ankur. Yeah. So.
So I want to ask that evolution map which you have defined, is it will be a fiber bundle if M is non-compact?
Yeah, it is. I mean, it has nothing to do with, so that's a good question. It's nothing to do with compactness. So what you have to show is that locally, you see, all the fibers are homotopy equivalent because omega M at x0 and omega M at x1 are homotopy equivalent. But one has to show that locally this looks like U cross omega M, where U is an open subset of M. So I mean, it doesn't really depend on M being compact, but you need M being compact in the whole analysis later on because you want to talk about the fundamental class of M. And the fundamental class of M is very important because it generates the identity of the loop product. If M is non-compact, then there would not be any identity in the algebra. So that's partly why you need M to be oriented and compact as well. Okay.
One more question is that so the base loop space has H space structure, right?
Yes.
And LM, that free loop space you have given a structure. So if the structure, if I restrict the structure of LM on the base loop space, can we get the H space structure?
Yeah, so see the structure on LM is really not on LM, but it's on the homology of LM. That's what I said, right? You cannot combine two loops in LM directly because they may not start and end at the same point. But see, there's this phenomena that there's the inclusion of the base loop space inside the free loop space, right? And the base loop space has an H, so it induces a map in homology, and one can show that this map in homology is actually a map of algebras, that the H space structure is compatible with the loop space structure there, up to a shift of degrees and so on. So yeah.
Okay, so are there any other questions?
There are some questions which were asked. I have written them in chat box. Can you see them?
Oh, achha. Can you run a spectral sequence?
3 questions are there.
Oh, 3, huh? So is there an intuitive way to expect only gives to so the first question, I guess, is how hard is it to check the Betty number on H star LM? Yeah, so I partly answered that. So I guess the point is that H star omega m, as rightly pointed out, is the universal enveloping algebra, but then H star LM is quite different from that. And as one knows from examples in 4 manifolds and so on, if you take any 4 manifolds of second Betti number at least 3 or higher, then the Betti numbers on LM actually grows quite fast. So, but omega m is quite controlled because it's somehow controlled by m and the homotopy groups of m, because the homotopy groups of m and omega m are the same. So in general, the Betti numbers of LM is a slightly different sort of object, algebraically or otherwise, compared to omega m. So in general, in Gromov mesh, there's no condition, but there's a conjecture of Gromov which says that you expect the Betti numbers of LM to grow in a certain rate, provided your manifold is generic. So generic means that it's rationally hyperbolic. You can look it up. And the metric is bumpy. So you do not expect these kind of arbitrary growth, unbounded growths on the Betti numbers for any manifold and any metric. There are, there are genericity constraints there. So that's what is known on that context. And yeah, so how hard is it to check? Yeah, so H star LM, I don't think there's any general techniques to compute H star LM. I mean, there are obvious theoretical methods, but you cannot really compute with any one of them, practically speaking. You need different techniques. So you have to model M and then use a bit of homological algebra and so on. The last question is, can you run a spectral sequence on M to compute the algebra completely? No. So the point is that, see, I mean, there is a spectral sequence which Cohen-Jones and Yan uses to get the loops, the loop product on LM, but there are some extension issues like it is in any spectral sequence, and they only managed to do it for CPN and SN, and that's where they managed to compute the full loop product algebra on H star of LSN or H star of LCPN. But in general, I mean, even there you have to know H star of omega m really well, H star of m, and if H star of m has a lot of generators, then you'd be at a loss to even control the maps. These works very well for SN and CPN because these are monogenic manifolds. The cohomology ring is generated by one element. That's why things simplify. So there is a spectral sequence, but I don't know how useful it is for practical computations. Okay, so I think these are the 3 questions they had. So, yeah.
Okay, thanks, Somnath. So yeah, so thanks, Somnath, for this nice talk. So now we'll move to the next talk. So yeah, after this, so there will be, I guess, 4 more talks. So there will be short talks by Sheila Barma, Anurag Singh, Munmi Saikia, and Abhishek Mukherjee. Yeah. Sheila, can you hear me?
Yes, yeah.
Yeah, so can you share your screen?
Yeah.
Yeah. So maybe we can, so you share your screen, maybe we can take just 2-3 minutes break, and after that we can start. Okay. Sheila, so can you switch on your video? No, it's okay. Yeah, fine. So just wait for, give us break for just 2-3 minutes. So then after that we'll start, okay? Okay. Sheila, can you hear me?
Yes, I can hear you. I think I got
Okay.
some.
Okay. Very good.
My video is on or not? I can't see from here. Actually.
You can't see what?
I can't see from here whether my video is on or not.
No. Yeah, it is on. Yeah. Sharp bound for this eigenvalues on starship domain. That is your title, right?
Yeah.
Okay. Good. So how long you are been in the TIFR?
So it has been 1 year from July. Actually.
Okay, 1 year. Okay, good. Okay, so yeah. So welcome to the second talk. So Sheila Burma, she is a postdoc in TIFR Bangalore. So she'll be speaking on sharp bound for Stickelberger eigenvalues on starship domain. So Sheila, you should finish your talk within 15 minutes. Okay. I think the organizer have said to you. Okay, so you can start your talk.
Okay. So I'll basically talk about some lower bounds of Stickelberger eigenvalues. So before coming to the results, I'll just give some brief intro of such problems. So these problems started from day life applications. So like if you take any musical instrument, like if you take guitar or if you take drum. So in guitar, we have different strings of different widths, and they also sound differently. Similarly, if we take the example of drums, so if we take drums of different widths, they also sound differently. So this somehow suggests that we have some relation between the shape and the sound that shape produced. So if we'll go mathematically, so actually these the sound that comes to us as a frequency, they are nothing but the eigenvalues of the Laplacian if we consider the Laplace operator on that domain. And so this suggests that if we consider Laplace operator on a manifold, then if we find out the eigenvalues of that operator, then these eigenvalues have some information about the geometry of that manifold. So the question was that if we know all the eigenvalues of Laplace operator on some particular manifold, can we reconstruct the manifold by knowing those eigenvalues? So this question got famous after an article by Mark Keck, the title of that article was "Can One Hear the Shape of a Drum?" So the purpose of this article was basically to ask the question that how much information these eigenvalues have about the shape of the domain. So at the end of this article, he basically proved that if we know all the Laplace eigenvalues of a manifold, then we can recover the genus of that manifold. After that, there was a lot of research, not only on the eigenvalues of Laplace operator, but on different other eigenvalues problems like Dirichlet eigenvalue problem, Neumann and Stickelberger, Robin and Mix and so on. So today I'll talk about this Stickelberger eigenvalue problem. So we'll start with a compact connected orientable Riemannian manifold with matrix G. And if we take any bounded domain with a smooth boundary and we'll denote by nu that by nu the outward unit normal to boundary of omega, then if we take any smooth function phi on C2 of omega, then the Laplace operator on this omega is defined by minus divergence of gradient of var phi. Then the Stickelberger problem is to find all real numbers nu such that there exists a non-trivial function, phi, which is in C2 of omega intersection C1 of omega closure, such that this function var phi is harmonic in omega and the outer normal derivative of this var phi is equal to mu of phi on boundary of omega. So this problem was introduced by Stickelberger in 1902, and the motivation came from physics, where this function var phi represents the temperature, and the problem is stated as we want steady state temperature in omega such that on the boundary this del phi by del mu, this is the flux on the boundary, this is directly proportional to the temperature on the boundary of omega. This problem can also be think of as the vibrations of the free membrane where all its mass is concentrated along the boundary. Now this problem is also important because the eigenvalues of Stickelberger problem is same as the eigenvalues of Dirichlet to Neumann operator, where this operator is defined from C infinity boundary of omega to C infinity boundary of omega, where this we take a function var phi and take its harmonic extension. This take its harmonic extension on whole omega and take its outer normal derivative again on the boundary. So this function var phi is mapped to del var phi over del mu, and the corresponding eigenfunctions, they form an orthonormal basis of L2 boundary of omega. Then next, the eigenvalues of this problem. So the eigenvalue of Stickelberger problem, they form a discrete sequence, and this sequence is increasing, and the first Stickelberger eigenvalue is equal to 0, and all other eigenvalues are strictly positive since we are taking our manifold to be connected here, and the eigenfunction corresponding to this 0 eigenvalue is the constant function. Next is the variational characterization of these eigenvalues. This is important because mostly we use such type of variational characterization to find the bounds for these eigenvalues. So for any L from 0, 1, 2 and so on, this mu L of omega is equal to supremum over set E, where E is a set of L functions from H1 of omega, and then we take the infimum over this expression, this Rayleigh quotient expression of var phi, where phi comes from E perp, where E perp is set of all functions var phi which are perpendicular to these phi i's over boundary of omega. So we will use this variational characterization to prove the bound for the eigenvalues. Next, here are some examples. So if we take any unit disk in R2, then the Stickelberger eigenvalues are 0, 1, 2 and so on. And the multiplicity of 0 eigenvalue is 1, and all other eigenvalues have multiplicity 2. And if we'll take unit ball in Rn, then eigenvalues are 0, 1, 2 and so on. And the multiplicity of eigenvalues k greater than or equal to 1 is given by this expression. Next, so this is the first result about the Stickelberger eigenvalues, which was given by Brumer-Stark. So this bound is of isoperimetric type. By saying isoperimetric type, I mean that we will fix some geometric constants like where perimeter or volume or say area or diameter, and we will consider all the domains under that geometric constants. So when Stark took that constants as perimeter, so he considered all the domains in R2 which were simply connected and they were of fixed perimeter, and he proved that among such domains, disk maximizes the first non-zero Stickelberger eigenvalue. Later, Hirsch and Payne, they observed that if we use the idea of Weierstrass and take the same assumptions, even we have more stronger result, which is the harmonic mean of first two non-zero Stickelberger eigenvalues, and they are bounded below by perimeter of omega divided by pi. If we'll take our omega to be the ball, actually this bound is sharp and equality holds. So then next result is about the star-shaped domain in R2. So this result was given by Cutler and Sigilletto, and he took a star-shaped bounded domain in R2 with a smooth boundary and which was centered at the origin. Then for k between 1 to infinity, he proved this sharp lower bound. I think there's some problem with my video. I can't add into this. I will just take 1 more minute and I will just reshare this. So here this r theta. So since we have star-shaped domains in every direction theta, we will have a point on the boundary, and that distance is actually given by this r theta. And if we take omega to be the ball, then this bound is again sharp. So the next question is, what about if we consider this problem on higher dimension? So this means if we consider this problem in Rn, then these are some notations. So this theta q, this is the angle between the radial direction and normal direction at any point on the boundary, and this ru is the distance in the direction u, the distance from the center to the boundary point, and this alpha will take the maximum of this theta q, and a is the tan square of alpha. Then with these notations, Garcia and Montano, they proved this that the similar result for the star-shaped boundary domain with a smooth boundary in Rn. Now basically they actually compared this mu1 of omega with mu1 of a ball of radius 1. So yeah. So then next is if whether we can generalize this result to more general manifold. So for starting, just like say for space forms, like for constant curvature space. So yes, so we considered this problem for the sphere, and under the same conditions, here again Ru is nothing but that is in any direction u, the distance between the center and the boundary point, and alpha is a maximum of theta q, and a is the tan square of alpha. Then, but here the problem is we don't know the eigenvalues on the unit ball like Rn. So here we compared the first non-zero Stick law eigenvalue on omega with the first non-zero Stick law eigenvalue of Brm. What is this Rm? Rm is the radius of the ball centered with the same center as omega and lies inside the omega. And we were able to prove the similar result as we had for this Rn. And just the thing which has changed is the Jacobi field, because the Jacobi field in Rn is given by R, and for a sphere we have the Jacobi field given by sine of R. Next question is, what about the negative curvature? This is for hyperbolic space. So sadly we don't have such result for hyperbolic space, because unlike in this sphere we have this Jacobi field is sine R, and we satisfy this condition sine ax is greater than or equal to a sine x for a between 0 and 1, and sine ax is less than or equal to a sine x if a is greater than or equal to 1. But for sine hyperbolic we have reverse inequality, so this result is not true. Next is what about the hypersurface of revolution? So for paraboloid we have the similar result. So we thought of writing it for general hypersurface of revolution. So we will take a hypersurface of revolution with matrix dr square plus h square rgsn minus 1, where we have some assumption on h 0 is 0 and h prime 0 equal to 1. These conditions we are taking for the smoothness of the domain. And we have to take some more additional condition on h, which is h is an increasing function of r and hr by r is an decreasing function of r. Then we will again define the this a as we defined previously, and with these assumptions we have similar result even for the hypersurface of revolution. Now I'll just give the brief proof of this result. So here again we are comparing this mu L of omega. Yeah, here one more thing, we were actually able to prove this result for all Stick law eigenvalues. So to do this, we firstly took a function f which is continuously differentiable and defined on omega closure, and we actually find out the relation between this Rayleigh quotient over omega and the Rayleigh quotient over Brm, which is integral over omega grad f of e square divided by integral over boundary of omega f square, and this relates the similar expression over b of Rn. Then we choose the function phi I such that this phi I s to the power n minus 2 ru, and this is square root of h square of ru plus del bar of ru square. This is the ith Stick law eigenfunction on Brm. And why we are taking this function is because we want to construct the test function on boundary of omega. So if we'll take any var phi such that integral over boundary of Brm var phi with this function is equal to 0, then actually this var phi will be perpendicular to phi I over the boundary of omega. Now we will go to the variational characterization and we will use this to prove the result. So we will take our E to be phi naught phi 1 phi L minus 1. This is a set of L functions, Now, if you'll recall, this mu L of omega was supremum over E. So since we have removed that supremum over E, this mu L of omega is greater than or equal to infimum of this quantity. Now, since we have the relation of this Rayleigh quotient over omega and the relation over ball of BRM, we'll just write down that expression. And now we'll just concentrate on this expression in this bracket, which is infimum over non-zero phi, where infimum over this non-zero var phi, where this var phi is perpendicular to all previous L minus 1 eigenfunctions over BRM. So this expression in this bracket is nothing but this Lth non-zero Stickelberger eigenvalue of B of Rn, and we get the desired result. So yeah, this is for all. This. Thank you.
So thank you, Sila, for the nice talk. So any questions? So if not, so let us thank Sheila again. Okay. So Anurag, you are here? Yeah. So this is
yes.
Yeah. So you are now in CMI?
CMI, yeah.
Okay, okay. So can you share your screen?
Yeah, just I'm sharing in a minute. So my voice is like clear, right?
No, it's clear. It's okay.
Yeah.
Yeah, it's working.
Shall I start?
Yeah. So this is Anurag Singh. So he's from CMI. So he's a postdoc in CMI, and he will be speaking on bounded degree complexes of graphs. Yeah, Anurag, you can start.
Yeah, thank you, sir. Thank you for the introduction. I would also like to thank all the organizers for giving this opportunity to talk over here. So the aim of this talk is to just give a brief survey about these particular bounded degree complexes associated with graphs. So let me first start with a very classical notion from graph theory, which is a matching. Matching is nothing but a collection of edges from the graph with the property that any two edges do not intersect, or maybe they don't have a common vertex. For example, if you take a complete graph, the edge 1, 3 and 2, 4 form a matching. Similarly, edge 1, 4 and 2, 3 form a matching. So given a graph, you can have many matchings. And this has a very beautiful property that if you have a matching and you take any sub-collection of that matching, that is again a matching. So any sub-collection of a matching is again a matching. Now with this property in our hand, we can define a simplicial complex associated with this. Given any graph, we can define a simplicial complex. And the simplices of the simplicial complex are nothing but all the matchings of the graph. For example, you take this graph on the left-hand side and you realize that what edges B and C do have a common vertex, so they will not form a simplex in the matching complex. Similarly, the edges B and A have a common vertex. On the other hand, B and D do not have a common vertex, so there is a edge between B and D in the matching complex. Yeah, so a little bit of history about these complexes, why these complexes are famous and why these and how they started. So it was in 1979 when Gauss was working on the Tix-Coset complexes. So a particular example of Tix-Coset complex is Coset complex. So they are related with some group and given a list of subgroups of this complex. So he realized that when you take the symmetric group and the subgroups are all those elements which fixes the value I, then you actually recover a complex associated with this particular graph. And he called this complex chessboard complex. Till 1992, there was no further progress on these complexes, though they appeared in many different places. Like in the work of Jivalevic and Resika in 1992 itself, they were dealing with the Perberg type problems. In the same year, Bauk was also working on the Brown's complexes, and they are the complexes obtained from posets of P subgroups of a given group G. So he realized to understand this complex, even for the value P equal to 2, it is important to understand the topology of this particular complex, which is coming from a graph. Then he started the study of these complexes and computed the combinatorial formula for the Betti number of these matching complexes.
So this represents the Betti number. And I must mention here that he just not gave the commutative formula for the Betti number. He also gave a representation of the symmetric group on the homology of this complex. So the representation, there's a natural action of the symmetric group on this complete graph by permuting the vertices of the graph that gives back action on this matching complex. And he realized that determining the topology or the homotopy type of these complexes are not very easy because there is a torsion available in the homology groups. And in fact, this is the smallest non-trivial place where the homology survives, and we have a torsion which is G3 available over there. After his work, there were many other results which came regarding connectivity of these complexes and the integral homology and so on, and similar results were obtained for the matching complexes of complete bipartite graph as well. Now this motivated Reiner and Roberts to generalize the notion of the matching complexes, now so-called boundary degree complexes. What is that? In a matching, what do you have? You have the property that matching is a subgraph in which the degree of any vertex is at most 1. So what if you relax this condition 1 and say you assign this value lambda to the vertices of the graph, and you collect all the subgraphs satisfying the property that the degree of the vertex in this graph is less than equal to the assigned value, then this also satisfies the hereditary property and you get a simplicial complex. For example, when you have this graph in the left, you get this particular simplicial complex. Here the main point is when you take lambda is equal to 2, 2, 2 and 2, even E2, E3 is not a subset of any simplex over here because they have a vertex of degree 3. So maximal simplices of this complex are just these 3 maximal simplices. Yeah, so when you have the image is equal to 1, you recover your matching complex. And this is why when image is equal to R, people call it R matching complexes, which is denoted by BD R of G. Yeah, so using the same funda that Bauk used in his result, he computed the rational homology of these complexes when the graph G was complete graph or complete bipartite graph. Yeah, so this left the following 2 questions unanswered. The first one was, we cannot answer the homotopy, we cannot compute the homotopy type of matching complex of Kn exactly in all the cases, but what if we don't take lambda is equal to 1? What if we take lambda bigger? Can we compute the homotopy type? If we cannot compute the homotopy type, at least can we say about the connectivity degree of these complexes? But the connectivity degree is nothing but the smallest place where the higher homotopy group is non-trivial. Yeah, I'm assuming that pi 0 represents the connectivity of this complex, so that's what it is here. And having these questions in mind, Johnson in 2008 in his PhD started studying the homotopy type of BD R of Kn. And when he realized that when you fix n and vary R, you get the following filtration. His main idea was that on the top you have the simplex of this dimension, and on the bottom you have the empty set. In between, what are the complexes are coming? Can you actually say what the homotopy type is or the connectivity? But he soon realized that it is not actually easy to compute the homotopy type because of the availability of the torsion in the homology, even in the case when lambda is not equal to 1. So he shifted his attention from computing the homotopy type to compute the connectivity degree of these complexes. He proved that the connectivity degree of 2 matching complex of Kn is bounded below by this, and 3 matching complex is bounded below by this. For bigger R, he also computed the Euler characteristic of the Alexander dual of BD R of Kn. Now, having the Euler characteristic of Alexander dual, it is easy to compute the Euler characteristic of the given complex. So he actually computed the Euler characteristic of R matching complex of Kn when R belongs to n-3 and n-2. He also gave a general lower bound for the connectivity of these boundary degree complexes of complete graph. But he also said that this bound is general because they are far from being tight. Even for lambda is equal to 2, he realized that these bounds are pretty far from each other. So he posed a problem in his thesis that what can we say about the connectivity of R matching complexes of complete graphs? Now recently I have been able to show that the connectivity degree of n-2 matching complexes of complete graph is exactly like this. And not only that, I was able to compute the exact homotopy type of these complexes, which was the first time we have a complete class of homotopy type known for anything. And using the same methods that I did here, I was able to compute the R matching complexes of complete bipartite graph, and similarly the n-1 matching complex of K and N. Now, so far I have spoken about like complete graph and complete bipartite graph, but there is also a theory when the graphs are not complete, like when the graphs are not complete in the sense for the general graphs. So the first major result in this direction came in 2008 when Mariatti and Testa was able to prove that the matching complexes of trees is always homotopy equivalent to wedge of spheres. So this posed the following problem. What happens when you take lambda other than 1? What happens with the homotopy type of boundary degree complexes of trees? Now this question was, like last year, Vega was trying to answer this question, but she restricted herself with a particular class of trees now called caterpillar graph. And these graphs are nothing but a tree with a central path, and on each vertex on the central path, you have mi leaves. For example, G243 is nothing but a central path with 2 vertices, and on the first vertex, you have 4 leaves. On the second vertex, you have 3 leaves. When the number of leaves on each vertex is equal, you call it perfect caterpillar graph, and you denote by G and M. So she was able to prove that the 2 matching complex of perfect caterpillar graph is homotopy equivalent to wedge of sphere. And she had an intuition that this is actually true for any caterpillar graph. The boundary degree complex of any caterpillar graph are homotopy equivalent to wedge of spheres. And recently, I was able to show that her conjecture is like true, and this is in fact the case that boundary degree complex of any caterpillar graph is homotopy equivalent to wedge of spheres. So these are some technicalities I'm not getting into, but I was also able to generalize this result for any tree, that you take a tree, the boundary degree complexes of trees are always homotopy equivalent to spheres, which implies a very simple result for the cycle graph, that boundary degree complex of cycle graph is always homotopy equivalent to wedge of spheres. Yeah, so now in this direction, there are many questions that have opened, but I would like to pose some which are available in the literature. The first question is the conjecture of Johnson, which he gave in his thesis. The first, like he said that the connectivity that he found is tight for the 2 matching complexes of complete graphs. The second thing to ask is what happens when you take the K matching complex of complete graph? What is the smallest K? For example, that we have recently shown that this is always wedge of spheres, but in the matching complex, we know there is a torsion. So we can ask, what is the smallest value K where there is no torsion in all the homology group of the BDK of Kn? The next question, the similar question can be asked for the complete bipartite graph. For the matching complex of complete graph, we know there is torsion, but for the top subcomplex in the filtration, we know there is no torsion, they are homotopy equivalent to wedge of spheres. So can we compute the smallest K for which they don't have torsion and everything is homotopy equivalent to wedge of spheres? And yeah, so these 3 questions are available. And other than that, there are other families of graphs which have also been studied very well. One of them is grid graph. And in 2018, Matsushita was able to show that the matching complex of the grid graph is homotopy equivalent to wedge of spheres. And computation of the boundary degree complex of grid graph is still open. So it would be interesting to see if the boundary degree complex of grid graphs are also homotopy equivalent to wedge of spheres. Yeah. And that's it. That was it. Thank you.
Okay, so thank you, Anurag, for the nice talk. So any questions? So I think there are no questions. So if not, so let us thank Anurag again.
Yeah, thank you.
Okay. So next is, yeah, she is here. Munmi, can you hear me? Miss Munmi?
Yeah, she has just connected. She's now connecting.
Okay. She is just connecting.
audible to you?
Yeah, so your voice is not clear. I mean, you have to speak little loudly, I guess. Yeah.
Yes, sir.
So
Am I audible to you, sir?
yeah, so you're audible, but your voice is little bit on the low side. Yeah, speak again. I mean,
Okay, good evening, everyone. Myself, Dr. Munmi Sekia, Assistant
just
Faculty
wait,
of
just
Mathematics from Royal Global University.
yeah. So just wait for some time. I mean, first you have to share your screen.
Yeah, I am trying.
Okay, okay. And maybe so we can't see you properly. Maybe you can hear us.
Yeah, yes, sir.
Okay, okay. So maybe yeah. So
Yeah,
your
can you
face
please
is
turn on the video?
no. She's has turned on the video.
Turned on my video.
That part is fine, but
Okay.
you have to. I mean, you are facing opposite to the light. Yeah. So your face is not visible. So can you just rotate yourself so that we can see? Okay, it's okay, fine. So if it is a lot of trouble, so don't do it. Don't do it.
Okay, so I can see there are another user named Munmi Shaikia.
Yeah, I am in my mobile also.
Okay, so yeah,
Somehow
so this
if
name
my
is
laptop
user.
not work, then
So which one? I mean, we will use to share your screen.
Put
User.
both of them as co-host. Put both of them as
put both of them.
it will be fine then for me.
Okay.
Okay,
Yeah.
so now you can share your screen.
Okay.
Yes, now it's coming. So you can share your slide. Okay, very good.
Is it visible, sir?
Yeah, it's fine. Fine. Yeah.
Okay, can I start?
Just wait for a few minutes. I think the official time is at
fine, sir.
8:45, but we can start a little bit early
Yes,
also,
sir.
and just wait for a few minutes.
Okay, sir, fine.
Yeah. So, Ms. Munmi, so you are a faculty or postdoc in the Assam Royal Global University?
Sir, I am a faculty.
Okay, okay.
Yes,
okay,
sir. I'm a faculty there.
Okay, okay. So, from where you have done your PhD?
From Guwahati University, sir.
From Guwahati University, I see.
Assam. Yeah, yes, sir.
Yeah, okay, I see. Okay, so let us welcome Ms. Munmi Saikia.
I think just a second. I think it's
Yeah,
a good
yeah, sure.
idea to start at 8:45.
Okay, okay, okay.
Yeah,
Very good.
just
So we'll
wait.
start at 8:45 then.
Yeah.
Okay, fine, sir.
Okay.
Using the vertices.
Okay, Munmi, you are ready, Dr.
Yes,
Munmi?
sir. Yes.
Yeah.
Yes, sir.
Okay, so let us welcome Dr. Munmi Sakya from the Assam Royal Global University. So she is a faculty there, and she will be speaking on dynamics of a pre-predator ecosystem, a mathematical model. So you can start, and you have to finish your talk within 15 minutes.
Okay, I'll try,
Okay.
sir. Good
Okay,
evening,
all right.
everyone. My topic of presentation is dynamics of a prey-predator ecosystem, a mathematical model. So mathematical modeling plays a vital role in studying any time evolutionary process or system and helps to predict its behavior under different conditions. It follows a systematic methodology so that the initial understanding and contradictions may be utilized in making modifications in the system for it to mimic a real system. Through an example of prey-predator ecosystem on Kaziranga National Park, I will try to discuss ecological behavior as well as various dynamical behaviors such as local stability, global stability, existence, direction, and stability of hope bifurcation. Here's the outline of my presentation. First, I'll be talking about mathematical modeling and some basic steps in modeling and the utility of mathematical modeling. Then I'll give the example of a mathematical modeling on rhinoceros and tiger population and application to Kaziranga National Park, and the discussion and conclusion with regard to my example and the references that I have followed. Now, the mathematical modeling, it's a process of using mathematics to solve real-world problems. And mathematical modeling models are basically a simplified description of a system built to help us better understand the operation of a real system and the interactions of its main components. Mathematical models are collections of variables or maybe equations and starting values that form a cohesive representation of a process or behavior. And the most important part of modeling is to make sure that the concerned mathematical model can exhibit the well-known system behaviors for the system under consideration. These are the few basic steps in construction of a model. First, we have to identify the real problem. Then we have to list all the factors and assumptions relating to the problem. Then we have to try to formulate and solve the mathematical problem. Then interpretation of the mathematical solution. Then we can publish and make testable predictions about the system, and we can compare with the real world. If it doesn't mimic the real situation, then we have to modify the model, and this cycle goes. Utility of mathematical model. Interactions among the members of biological communities and components of the abiotic environment are extremely complex. Mathematical models are useful for thorough understanding how ecosystems function and for making predictions about managing ecosystems. Actually, management requires predictions and predictions require models. Mathematical models provide a way to design and evaluate protocols to manage and control animal populations, natural resources, wildlife resources, and infectious disease. Researchers on animal conservation can make use of the models to aid the accomplishment of field experiments through the indication of the parameters which should be observed. Actually, through a mathematical model, we can study many factors, just changing the parameters which we want to observe. This is the example taking effect of poaching on rhinoceros and tiger population, an application to Kaziranga National Park. So here, what I have done, I have considered the I have collected data from the PCCF Wildlife Assam. Then based on the data and census report, I have divided the rhino population into two categories, the mature rhino and immature rhino. And from the data, we have found that the tiger attacks the immature rhino for food, kills immature rhino for food. So based on that, we have constructed the model. These are something important about the Kaziranga National Park. All of we know about Kaziranga National Park. It's an important landmark in the world for holding around 85% of the world's one-horned rhinoceros. It's a home to high degrees of diversified species with great visibility, and it's a biodiversity hotspot. Compared with other protected areas in India, Kaziranga has achieved notable success in wildlife conservation. And these are the threats to Kaziranga National Park: poaching, annual flood, erosion, siltation and weeds, illegal fishing, heavy traffic, livestock grazing, break in embankment, wildfires, insect attack, and pathological problems. Out of all these threats, in my model, I have considered the poaching effect only, and I am working on annual flood. Here I'll discuss only about the poaching effect. These are the field data that I have collected. So here I am showing this figure 2. This represents the rhino population in KNP since 1905, so quite increasing. In the second figure, we can see the total rhino death in KNP due to poaching and natural causes. So here you can see. So fluctuations there. And this figure 4, here you can see tiger population here. This also increasing in KNP. And the figure 5 represent the immature rhino killed by tiger in KNP. So sometime in 1998, it's showing not so high, low. Here also a lot of fluctuations there. Now coming to the mathematical model formulation part. Based on the data from the KNP and the PCCF Wildlife, I have considered some assumptions and some factors, some importance for the A-structured prey-predator model. And here these are: the birth rate of the immature rhino population is proportional to the existing mature rhino population with a proportionality constant A1. For the immature population, the death rate and the transformation rate to mature are proportional to the existing immature population with proportionality constants D1 and R1 respectively. The natural death rate of mature prey is assumed to be D2. The human poaching rate on mature prey is P. According to the Forest Department of Assam, there is no record of death due to infight between mature and immature rhino. So intraspecific competition between the immature and mature rhino I have not considered. And the intraspecific interference of mature rhino is rho, and A is line 0 to 1 is the conversion efficiency, measuring the number of newly born predators for each captured prey. Tiger as predator population do not kill mature rhino for food easily. As for tiger, other herbivores are like swamp deer, buffalo are also available. Only 4 such cases found during 2013 to 18. So I have ignored that factor. And from the data obtained from PCCF Wildlife, A1 R1 is greater than D1 plus R1 into D2 plus P, which means that the immature rhino birth rate and the transformation rate to mature is greater than a threshold value, which depends on the death rate of the immature rhino and death rate of the mature rhino, as well as on the poaching rate. These are the model equations. So to represent the model, I have taken help of this differential equations, model system of differential equations. Here, this x1, x2, y, this represents immature rhino, mature rhino, as well as tiger population. And the first equation represents growth of the immature rhino with respect to time t. The second equation represents the growth of the mature rhino with respect to time t. And the last equation represents the growth rate of the tiger population with respect to time t. And here the most important factor is this Holling type 2 function response. That function response means the prey-predator interaction relationship that I am assuming here as Holling type 2 function response. And with initial conditions here, x1 0 greater than 0, x2 0 greater than 0, and y 0 greater than 0. Next, the positivity and boundedness of solutions. This part is very important because positivity guarantees that the system is well posed and densities cannot become negative, and the boundedness represents growth restriction as a consequence of limited resources. So that's why first, after constructing the model, we have to verify this positivity and boundedness of solutions. So for the positivity part, I have taken help of Nagumo. And for the boundedness, I have constructed a time-dependent function and taken help of differential inequality, and I have proved this theorem. This set omega 1 with this attracts all solutions in the interior of the positive orthant with the V factor minimum of the death rate of the immature rhino, D2 plus P, death rate of the mature rhino plus poaching rate, S by K. S means the death rate of the tiger, K is the conversion efficiency. And this boundedness is important, as already I told. It represents the growth restriction and as a consequence of limited resources. And it means that the system is ecologically well behaved. Now coming to the existence of equilibrium points, to study the local stability and global stability of the system, we have to first find the equilibrium points. So equating the equations, these equations to 0, we can evaluate the equilibrium points. Sometimes it takes too much time to evaluate the equilibrium points because the system is non-linear here. So I found for my model 3 equilibrium points. The trivial 0, 0, 0 always exist. In absence of the predator, E1 exists under the condition A1. 1 means that A1 R1 when greater than D2 plus P into D1 plus R1, then the E2, that is the most important equilibrium point, that is the interior equilibrium point. This is, we can find this provided the condition A1 X2 star greater than S into D1 plus R1 divided by A into K minus SH, which means that the birth rate of the immature rhino is greater than a threshold value. Next, I have performed the analysis. For this, I have evaluated the Jacobian of the system. Then at each of the equilibrium point, I have evaluated the Jacobian. So I have found this. The trivial equilibrium point always a saddle point, means unstable. In absence of the predator, the second equilibrium point E1 locally asymptotically stable under this condition, and otherwise it's unstable. And the interior equilibrium point E2 is locally asymptotically stable if and only if this condition holds. That is, the birth rate of the immature rhino and transformation rate to mature rhino is less than a threshold value. Next, I have performed the Hope bifurcation. Bifurcation means what? It's the switching from the unstable situation to the stable situation, or from the stable to unstable situation. Means the sudden change in the system. And Hope bifurcation means the occurrence of limit cycle from the equilibrium point, when the suddenly one parameter changes or takes some different value, critical value. So considering poaching effect P as a bifurcation parameter, the necessary and sufficient conditions for Hope bifurcation to occur are this conditions 1, 2, 3. A1 at the critical point P star greater than 0, A3 at the critical point P star greater than 0. The second condition A1, A2 minus A3 is equal to 0 at the critical point P star. And the real part of the derivative of the lambda J means eigenvalue. Eigenvalues of the Jacobian matrix evaluated at the interior equilibrium point with respect to the dp at the critical point P star non-zero for J 1 to 3. Here P star is the critical value of P, A1, A2, A3 are the coefficients of the characteristic equation of the Jacobian matrix evaluated at E2 given by this. Here A1, A2, A3 are given by these expressions. Next, the direction and stability. I will not show the whole calculation part, so it's too lengthy calculation. Here I have taken the help of the center manifold theory and normal form theory to study the direction and stability of Hope bifurcation. And actually this direction and stability we have to perform when the equilibrium point is non-hyperbolic. Non-hyperbolic equilibrium point means when the eigenvalue real part. In that case, we can't analyze the stability of the equilibrium point through the local stability or global stability. In that case, we have to take help of the central manifold theory and normal form theory to minimize the dimension of the system and to study the direction and stability of the Hope bifurcation. Next is global stability. I got this theorem. If these two conditions hold, then the interior equilibrium point will be globally asymptotically stable. Then I have performed the numerical simulation to validate my analytical results. And here I have considered P as the key parameter, that means the poaching rate, that directly influence the dynamics of the system and ecologically balanced behavior of the park. And I have divided the section into two parts based on the ecological behavior of the park and complex dynamical behavior of the system. And for this, I have chosen some biologically feasible parameters which satisfy my analytical conditions. First, the ecological behavior of the KNP. So to see the ecological behavior of KNP, to observe the effect of the key parameter P on ecological balance of KNP, I have considered these parameters: A1, immature rhino birth rate 45, immature rhino death rate 5, then attacking rate A 3, handling time by tiger 0.02, immature rhino to mature, the transformation rate 22, and the intraspecific interference between the mature rhinos 2, death rate of the mature rhino 0.3, poaching rate P1, death rate of the tiger 1, conversion efficiency 0.05, and with the initial conditions 1, 1, 1, I have seen that this satisfy the local stability condition. So the positive equilibrium point is locally asymptotically stable, as this satisfy the condition of local stability. So to concentrate our attention in the maintenance of ecologically balanced behavior of the park, from the first figure, you can see when the attacking rate by the tiger population A is 3 and the poaching rate low means 1, then the density of rhino, here red lines represent the immature rhino, this blue line represent the mature rhino, and the green line represent the tiger population. So then the density of this rhino population, as you can see from the figure, it's higher than the tiger population. But if the attacking rate in the A equal 5, if increase means from 3 to 5, then the density of tiger population increases compared to rhino population. The same figure that we can see here, this tiger population, the green line going up.
Yeah, so Dr. Munmi, so please finish your
Yes,
talk
sir.
within 5 minutes.
Okay, I'll try. If the attacking rate as well as the poaching effect increase, say A equal 20 and P equal 10, then in the figure, this third figure, we can see the trajectories first oscillate and then go to the respective equilibrium level. Here, density of tiger population is larger than the rhino population. That means what? We can say the park is showing the ecologically imbalanced situation. Ecologically imbalanced, I'm saying because I have assumed that ecologically balanced when tiger population will be lower than the rhino population, and the park will show ecologically imbalanced when tiger population is lower than rhino population. Balance means higher rhino population than the tiger. Imbalance means lower rhino population than the tiger. So means what? Modification is required in the model so that attacking rate can be minimized and ecological balance of the park can be maintained. Next, the second part, complex dynamical behavior of the system. For this, I have chosen a different set of parameter values. So for this set of parameter values, here in the figure A7A, we have observed the local stability of the equilibrium, interior equilibrium point. And in the second figure, I have observed the global stability of the interior equilibrium point. In the third figure, I have observed the Hope oscillation. And in the last figure, I have observed the limit cycle for the P value greater than the critical point 12.15. Next, in the last figure, for the same set of parameter values, when attacking rate A equal 25 greater than the critical value of the attacking rate on the immature rhino by the tiger population, the oscillation behavior and limit cycle is observed, which implies that the attacking rate should be controlled. Modification is required in the model. I have performed all those parts, but here due to time limitation, I cannot show. the discussion conclusion. So according to reported real data collected from PCC Wildlife Assam, I have tried to formulate and analyze to understand the dynamics of rhino and tiger interaction. As the tiger feeds on immature rhinos, stage structure is considered on rhino population by classifying into two subpopulation, immature and mature rhino. Immature means I have considered a horn not developed category, and mature rhino means the horn developed category, because only when horn developed, then only they are post. In view of ecology, the main objective of this study is to increase the size of the rhino population in this park, also to maintain the ecological balance of the park. And from the mathematical point of view, the stability and complex dynamical behavior of the system are analyzed for my model. And the first part in the numerical simulation section, I have tried to discuss the ecological balance behavior of the park, while in the second part, I have tried to discuss the complex dynamical behavior of the system from the mathematical point of view. And the park is considered to be in, as already I have mentioned, ecological balance and imbalance part. Again, I will not repeat. And I have observed that if the poaching effect and or attacking rate are higher, then the park is in ecologically imbalanced situation. And in the second part, if the poaching rate is increased beyond a threshold value, an adverse effect on the rhino population is observed, which should lead them towards extinction. Again, if the attacking rate on immature rhino by tiger population increases, the positive equilibrium point becomes unstable. To control the attacking rate and the oscillation behavior of the system, some modifications has to be introduced. So in my model, I have introduced additional food quality and quantity factor. Then also I have incorporated the habitat complexity factor to modify my model and to mimic the real situation. The system describes the interaction between stage structure and presence of continuous trade of poaching. It is assumed that the tiger population consumes immature rhino only as per Holding type 2 function response. This is my assumption. So someone, if interested, they can modify the function response and can try to see the behavior of the system. The intraspecific interaction between mature rhino is also considered by considering the poaching effect as a bifurcation parameter. The conditions of existence of bifurcation I have tried to establish as the tiger preys on other herbivores of KNP2. So the considered function response can be modified. So using that additional food that other herbivores as tiger preys on, so I have incorporated additional food. So I have modified the function response in the second part of this research. So these are some of the references that I have followed for this research. And I want to acknowledge Dr. Atasi Patron, my team, with whom I am doing this work, and also my guide, Dr. Anuradha Devi of Royal Global University. Thank you.
Okay, so thanks Dr. Munmi for your talk. So we do not have time for the question answers. So we'll move to the next talk by Dr. Abhishek Mukherjee. Yeah.
Okay, sir. Thank you, sir.
Thank you. Yeah. Abhishek, are you here?
Yes, I'm here. Can you hear me?
Yeah, I can hear you. So maybe you can switch on your video.
Okay, I need to switch on.
So yeah. Yeah.
Okay.
Yes. How are you?
Fine. তুমি
Okay,
কেমন
very
আছো?
good. ভালো।
অনেকদিন পর দেখা। আচ্ছা।
So share your screen.
Yes, sure.
Yeah, okay. So maybe we can start at 9:10.
Okay, sure. No
Yes,
problem.
okay, all right.
Sure.
Abhishek, so maybe you can go to the full screen mode. Yeah.
Okay.
Okay. So shall we start? Okay.
Yes, yes, yes.
Yeah. So this is the last lecture today for the today evening. So this is Dr. Abhijit Mukherjee. He's a faculty in the Department of Mathematics in Kalna College. So he'll be speaking on discreteness in SL2H using test maps. Okay. Abhishek Mukherjee, you can go.
So I would like to thank the organizers and Dr. Abhijit Pal for nicely introducing me. So, okay, so I'm not going to waste any time. So this talk is based on work with Dr. Krishnendu Gangopadhyay, and my the title of my talk is Discreteness in SL2H using test maps. So, okay, so the talk based on this basic problem in the theory of friction groups. The basic problem is discreteness. So which means that given any two elements in PSL2R, whether or not the group generated by them is discrete. And what does it mean by a discrete group? So a discrete group means a topological group which is discrete with respect to the topology defined in the group. Okay. And investigations on friction groups was initiated by H. Poincaré in 1882 in connection with the discreteness problem, and he called these groups friction in the name of Fock. Yeah. Okay. Discrete subgroups of the Mobius groups are actually of considerable interest due to their importance in several branches of mathematics. Okay. Now our work was motivated basically by this result by Troel Jorgensen in the year of 1976, and he stated that stated an inequality that the generators of a discrete non-elementary two generator subgroup of SL2C necessarily satisfy. And my primary aim in this talk is to give some ideas to test discreteness of a Jarisch-Giddens subgroup that I will going to define, which will be determined by two generator discrete subgroups in SL2H, having one isometry from the group and another one we can choose suitably and may not be in the group that we have considered. And this two generator subgroup will influence the discreteness of the whole group in view of certain generalizations of Jorgensen inequality for two generator subgroups in SL2H that has been formulated, and those results will be used in this work. Okay. And the motivated result in this work was by Jorgensen, and it is the theorem that states that a non-elementary group of PSL2C is discrete if and only if its two generator subgroups are discrete. That means the discreteness of a subgroup in PSL2C is determined by the two generator discreteness of the two generator subgroups. Yeah. Okay. So I'm not going to, okay, so let me some briefly just describe this space. So I would like to introduce the H2 as a right vector space over the ring of quaternions H, which is a natural example of quaternionic right vector space that can be defined as this with respect to usual addition and scalar multiplication. And let us introduce a relation on the set H2 minus 0 defined as for any two vector ZW. These are equivalent if and only if there exists a non-zero scalar such that W can be expressed as Z lambda. And this equivalence relation partitions the set. And if you consider that this distinct equivalence classes which has been denoted by P1H, and that P1H will be the H cap, that is H union the infinity point, which is homeomorphic to the sphere S4. Okay. And using a standard lift, one can induce the action of SL2H on H cap by left multiplication on the standard lift followed by the right projection as the group of quaternionic Mobius transformations. which is evident from the following equation. Yes, it is, that is Az is actually, so it is P of Az, that is Az plus B Cz plus D inverse. And that actually introduces the quaternionic Mobius transformation. So due to the natural correspondence, this A to Az from Sl to H to the group of quaternionic Mobius transformations, we identify the group of quaternionic Mobius transformations with PSL to H. And now let us define the hyperbolic 5 space by this definition, that is H5 is the set of all those points Z, T in R5 such that the last coordinate is greater than 0. And by Poincare extensions, one can show that PSL to H actually maps H5 onto itself, and the group SL to H acts as an orientation preserving isometric group of the hyperbolic 5 space H5. And note that, as we have already stated, that H cap is the conformal boundary S4 of the hyperbolic 5 space. Now the action by the group SL2H that acts on H cap is extended over H5 by Poincare extension. And the process of construction is more likely as in the case of hyperbolic 3 space by PSL2C. Yes. So the orientation preserving isometric group of this space is PSL2H. Now we can classify the isometry by their fixed points as elliptic, parabolic, and hyperbolic or loxodromic in a similar fashion as that of PSL2C. And this classification can be characterized algebraically by conjugacy invariance of the isometries. Now note that every element in SL2H is conjugate to an upper triangular matrix, and for that reason Professor Gangopadhyay has classified these classes. The complete characterization of conjugacy classes in GL2H, and that can be represented like this. So we may classify those members in usual manner, which has been defined in the next slide. Okay, yeah, sure. So an elliptic or hyperbolic element is conjugate to a matrix of the form lambda 0 0 mu, where lambda mu are in complex number. And if mod lambda equal to mod mu is 1, then A is elliptic, and otherwise it is hyperbolic or loxodromic. A hyperbolic element will be called strictly hyperbolic if it is conjugate to a real diagonal matrix, non-identity of course. A parabolic isometry is conjugate to an element of this form lambda 1 0 lambda, where mod lambda is 1. So our goal that we have achieved to test discreteness of a subgroup G by considering two generator subgroups by means of suitable test maps, which are to be suitably chosen and that need not be in the subgroup G, by the use of Jorgensen type inequalities for a two generator subgroup FG generated by FG in the group SL2H, and the inequalities that we have obtained in our first work. So, okay. So the line of investigation has been initially motivated by the remarkable result of Jorgensen and Kikka that I have stated earlier. And aftermath in higher dimensions, Abikov and Hash, they proved a Jariskidian subgroup G of Mobius transformation group. Mn is discrete if and only if every two generator subgroup is discrete in G. And along this line, Min Chen's work that motivated us, since he proved a Jariskidian subgroup G of Mn is discrete if the group Fg is discrete where G is in the group and F is a fixed non-trivial element of Mn may be chosen outside the group G, which is not an irrational rotation that is of infinite order, or if having finite order that doesn't pointwise fix the boundary. Now I need to define two objects that, so let us suppose that A belongs to SL2H, and let us consider this form, that is A is lambda 0 0 mu. Then we can define argument trace of A to be argument lambda plus argument mu, and absolute trace of A as mod lambda plus mod mu. Okay. Now, so the definition of Jarisch-Giddens subgroups are like that. A subgroup is said to be Jarisch-Giddens if it doesn't have a global fixed point, or neither it preserves a proper totally geodesic subspace of H5. So these are our main theorems. So in our study, we choose a test maps not necessarily belong to the concerned group that we have considered in SL2H. That is, let G be a Jarisch-Giddens subgroup of SL2H. So F be a two rotatory elliptic element, not necessarily an element of G, satisfying this condition, that is 0 less than argument trace F less than pi by 3. Then for every if for every hyperbolic element G in G, if the two generator subgroup Fg is discrete, then capital G is discrete. Okay. Now the second result is like that. If we consider F to be a hyperbolic element, and again, if it is not necessarily in the group G, and satisfying this condition that half of absolute trace square F minus 3 is less than cos of argument trace F. And if for every hyperbolic element G in G, capital G, if the two generator subgroup Fg is discrete, then the whole group capital G is discrete. And the third statement is for the parabolic element. That is, if you consider F to be a parabolic element in SL2H, not necessarily in the group G, and suppose you take the parabolic element as 1 mu 0 1, where mod mu is less than 1 up to conjugacy. So for every hyperbolic element G in capital G, if the two generator subgroup is discrete, then G is discrete. So these are the results that we have obtained. Okay. So I'm not going to just a few lines I want to give. Okay. So actually the scheme of the proof depends on the choice of H, that is this H, yes. So that depends on the hyperbolic, the choice of the hyperbolic element which will exist in the group G if it is not discrete. And that Z0, that fixed point, is not equal to 0 infinity. So that so this existence will ensure the choice of this H for the first and second case. And for the last one, that is for the parabolic case, you need to choose this element as like that. That is 1 0 minus Z0 inverse 1. And then since G is not discrete, then you can have that that using the denseness of G, you can get distinct sequences Hn and Gn, Hn for the first and second case, and Gn for the last one, satisfying these properties. And then you will have this equation, that is Hg H inverse, and that will be like this. Yes. And this matrix will give you the conclusion. That is, since Z0 is a fixed point of G, then that part is 0. Okay. So using the inequality that we have obtained in our first work, then this inequality will leads to a contradiction to the inequality for any non-elementary discrete subgroups that will satisfy. Yes. Yeah. And this theorem says that one may choose certain irrational rotations as test maps, which is a very interesting part of our investigation. And if you go through minutely, then you may observe that you have chosen actually one parameter family of test maps to test desired discreteness of the whole group G. Okay. And then after having this result, you can also have another one that is that looks like the same, but here we are taking one generator to be a test map F, and the other is a conjugate of F by a hyperbolic element of G. And the complete statement is like that here. just we are taking the this one, that is F GF G inverse. So these two generator subgroups we are considering. Yeah. Okay. So I would like to make 2-3 remarks on that. So to prove the above two theorems, we have used Jorgensen type inequalities for two generator subgroups of SL2H, which we have obtained. And the second remark is that it is necessary to impose suitable restriction to the quantities argument trace F and absolute trace F in the above two theorems. And interestingly, these quantities emerged out from the Jorgensen type inequalities that we have obtained in our first work, and these restriction cannot be relaxed. Yes. And the third remark is that if we observe case one of the above two theorems, we see that the quantity argument trace F cannot be 0, because in that case F will be reduced to an one rotatory elliptic. And the fourth remark is that if you look at the case in which argument trace F is pi/3, then we find at once that the arguments we give here become inconclusive. And the last one is that in case 2, if the inequality will become equal, then we must have F is an elliptic transformation of order at least 7. But this leads to a definite contradiction to the hypothesis of choosing F hyperbolic. Okay. So these are the references. Thank you.
Okay, so thank you, Dr. Abhishek, for a nice talk. So any questions? So if not, so let us thank Dr. Abhishek again. Yeah. So so now that is the end for the today. And so any organizers, so are you here? So you can end the program for today.
Yeah. So thank you, Dr. Abhijit, for chairing today's session.
Thanks.
Yeah, thanks a lot. So yeah, we close here for today. We meet tomorrow at 10.
Okay.
Okay.
Good night.
Good night.
Good night.
Avida, good night.
Good night. Okay.